Hey everyone and welcome back to PrepFusion. I'm Anish and today we are having a complete marathon on measuring instruments chapter, which is a very important chapter for electrical and electronic measurements. So this actually is covered in both EE and IN syllabus, and from this only this chapter, right, maximum questions has been asked and you can expect at least 2 to 3 marks from this particular topic. Okay, like I'm just guessing here, but if your luck is good, right, you can expect at least 2 to 3 marks. And if you complete this topic, like your 50% of your measurements subject will be complete, because the other 50% actually has very less weightage than this has the highest weightage. Okay, so just I have few demands. Just I'm giving this much, I'm doing this much like task for you guys, so I can at least expect a like. So I'm expecting at least 100 likes. I know this is a core video, this is not a common subject video, so all the people will not be watching. So you can share it with your friends, you can like the video, so that I understand that like you are getting benefited from this, and like it also helps me, it also keeps me motivated to upload more videos. So please do like it, and you can repost my LinkedIn post. I will post all the notes on my LinkedIn. Okay, so you can go follow me on LinkedIn and repost the post on LinkedIn, so you can support it there. And obviously today is the last day to avail the maximum discount, okay, of special Diwali. So you can like text on this number 70192411819. Okay, you can text on this number 70192411819, or you can go in our website, there is a WhatsApp chat button, you can chat and ask for any other discount. So I have launched a special course on core combo, so today is the last discount where everything will be covered comprehensively, from measurements to MFT and power electronics. So all the 3 core combo subjects, right, which students generally leave out because they don't have enough time to study, all 3 have covered comprehensively. Like few I am uploading, and most of the syllabus also has been done, recording has been done. So you can go and purchase that course today. So today is the last day of the discount. You can text if you have any other queries. So yeah, that's it basically. Enjoy the marathon, and I hope to see you in the next lecture. Until then, happy learning. Hey everyone and welcome back to PrepFusion. So today we will start the second chapter of our electrical and electronic measurements subject. So previously we studied about error analysis, what are the different types of error in a measuring instrument, and what type of features do we want in our instruments, right? What type of static characteristics we want in our instruments. So that we learned. So now we'll learn about the different types of analog measuring instruments and working principles of measuring instruments. And we'll start off with PMMC instruments. What do exactly PMMC instruments do in like basic measurements, right? We use it actually in everywhere, from lab to our like readings, everything, right? We use it everywhere. So let's start. Basically, first I will show you the overview. So overview of analog meters. Basically there are mainly 4 types of analog meters. One is indicating type instruments, recording type, integrating type, null deflection type. Indicating means exactly what it says. It indicates the exact instantaneous value. So this, right, this actually indicates me the instantaneous value of that particular quantity, either instantaneous or DC value. Okay, it exactly says the DC or RMS value. Okay, now in this, right, we have ammeter, voltmeter, wattmeter. If you remember correctly, wattmeter exactly shows the wattage, whatever the power that is being consumed by the load. Voltmeter shows the voltage, and ammeter shows the ampere, right? So that is about the indicating type instruments. What are the recording type instruments? Recording type are, the examples are CRO, ECG. So what they do is, they actually, while indicating, right, they also record the quantity which they were actually measuring. If you remember, in ECG in hospitals you see a graph like this. What does this means? It means at that particular point of time the value of that quantity was this, then it changed, right? So it actually keeps a record. It actually keeps a record of the quantity that it measures. That's why the name recording type instruments. Next is integrating type instruments. What does integrating type instruments mean? Basically the quantity that they are measuring, right, they actually integrate that. That is used in energy meter. Energy meter integrates the power with respect to time. So we know integration of power with respect to time means energy, and exactly that is what energy meter does. So we'll study all of this. Null deflection time means, like, there is a null pointer. If it is at 0, right, that means the bridge is balanced or no current is flowing, something like that. It can go either on the left or on the right. Okay, if there is some deflection from the null point, that means either the bridge is unbalanced or there is some imbalance in the system. So that is why the null deflection type of instruments come into the picture. In bridges connecting the off diagonal 2 points, right, of the bridge, the null deflection type instrument is generally used. So let's read more about this. So the indicating type instruments, these instruments provide reading by displaying the position of a pointer on a scale when the system reaches steady state. They basically indicate the measuring quantity. These recording type instruments, these instruments continuously record the variation in the quantity being measured over time, allowing the user to track the changes. Okay, how much did the heart rate change with time? Next is integrating type instruments. Integrating type instruments, these instruments calculate the total quantity by integrating another related quantity over time. For example, energy is obtained by integrating power. So that is how energy is obtained, right? We simply integrate the power, and that is how we obtain the energy. Next is analog meters. Like inside analog meters, there are another two types of distinguishes, basically two types of variations. That is, one is direct instrument, another one is indirect instruments. Direct instruments means this measure the value of the quantity directly. For example, voltmeter, ammeter, we directly connect them across the load and measure the voltage across the load or the current through the load. What does indirect instrument means? Indirect instrument means these instruments measure the value using indirect methods, such as comparison techniques. Like we use in AC voltage, AC bridges, right? In AC bridges or DC bridges, I will write this here: AC/DC bridges. Okay. What does AC/DC bridge means? Basically here, these instruments measure the value using the indirect methods such as comparison techniques. So AC bridge here, right, if there is some variation in this resistor, right, so obviously if I have placed a null pointer here, this will actually indicate that there is a deflection. If there is a deflection from the null pointer, that means that this resistor value has changed. By how much, we can also write down an equation from which we can derive. So this we'll learn in the bridges chapter. So, and one method of analog meters is direct measurement, direct instrument. Another one is indirect instrument. So this whole thing, right, complete thing can also be known as indirect instrument. Okay, so that was about these two things. Now another measurement type of analog meter is absolute instrument. So what are absolute instruments? These instruments measure the quantity based on fundamental physical principles without needing calibration against a standard material, right? Standard quantity. This should be quantity. Standard instrument. Oh, like this should be only standard only. Like we have a standard, right? This is not compared with respect to the standard. This is actually the standard. These absolute instruments are actually the standard. The energy required for the measurement comes directly from the physical quantity itself. Like just for take the example of tangent galvanometer, which measures current based on the tangent law of magnetism, often used in laboratories for theoretical or experimental work. So this is not that we use originally, like these ammeters, voltmeters, all those things, right, are derived from this tangent galvanometer. Basically they are calibrated from this tangent galvanometer. These are absolute instruments. These does not need any calibration. Okay, but those instruments, right, whatever we use in labs, those are actually calibrated with the help of this tangent galvanometer. Now you might say, sir, if this is so good, why don't we use it? Because this is very costly to make this, right, to make this perfect instrument. It is hugely costly. So what we have to do is we basically have to like those measure instruments, right, those are actually cheap. So we calibrate them with respect to this and we use them because we can use them because those are very, very cheap. But this is very, very expensive. That's why we don't directly use this. Okay. So what are secondary instruments? These instruments provide readings after being calibrated against a standard instruments or scale. So yeah, exactly. Ammeters, voltmeters, all those things, right, are calibrated with respect to this tangent galvanometer. They can be calibrated with respect to other instruments as well. I don't know exactly, but they will be calibrated. The energy for measurement comes from an external source, usually electrical. So yeah, it will come from an external source. It will not come from internally through the instrument. Okay. here some external source is also present that will provide the energy. Example, voltmeter, ammeter, which measures voltage current is respectively by relying on the instrument's internal circuitry. We'll see this circuitry. It will depend on the internal circuitry. It will not depend on the totally circuit. Okay. Commonly used in a practical applications such as industrial or domestic measurement systems. We use this in our case. Why? Because this is cheap and in an industry it works. Okay. This also provides good accurate results, but not as accurate as this galvanometer, right? But good enough for industrial and domestic measurement purpose. Now, there are few forces which are involved in indicating time instruments. What are those forces? One is deflecting force, or as the pointer rotates, right, we actually call it deflecting torque. Another one is controlling force or controlling torque. Another one is damping force or damping torque. So these three, right, these three have their different like use cases and applications, and why all of the three actually are very, very important. We'll learn them one by one. So deflecting force means this force or torque moves the pointer from its zero position to indicate the measure value on the scale. So this force or torque moves the pointer from its zero position to indicate the measure value on the scale. So what happens is that initially I have to move the pointer, right? I have to move the pointer to certain theta degrees. So who will provide that force or torque? This force or torque moves the pointer from its zero. So this deflecting force or torque will actually provide that particular torque. Okay, this deflecting force or torque will actually provide that particular torque. Damping torque means the torque that causes the movement of the pointer proportional to the measured quantity. So this torque, right, is actually proportional to the measured quantity. So if my measured quantity is 5 volts, so it will provide a torque of, let's say, 10 nano Newton meter. If my measured quantity is 10 volts, it will increase, right? It will be 20 Newton meter. Okay, so I am just assuming that it is linearly proportional. Okay, so like that. So this torque, right, will be directly proportional to my measured quantity. Next is this controlling force. So what is controlling force? Controlling force means controlling force means the force. This force opposes the deflecting force and ensures that the pointer comes to rest at correct position on the scale. So if there is a like deflecting force, right, what will happen is that this torque, right, this torque is always present because measured quantity, like current is always flowing, and due to the current I am getting a torque. Okay, so what will happen? Torque, right, it will keep on accelerating the pointer. It will keep on accelerating the pointer. Okay, but I don't want that. I want it to reach on a steady state. I want it to point to my, let's say, 10 amperes. Who will stop it? Because deflecting torque is always providing some force to move. Who will stop it? This controlling force will stop it. Okay, this force will be directly proportional to the deflecting force. Okay, so exactly when both of these will be equal, then the pointer will reach steady state. Simple Newton's law. Okay, both forces are equal, then the pointer will be at steady state and it will not move. And to like make it not move, right, one thing we have to ensure that once there is a deflecting torque, due to its own inertia, the controlling torque is just applied after the deflecting torque. So it will have a tendency to swing around the steady state value. To reduce that swing, we use damping force. Damping force or damping torque also we can say. So this will be F damp. This will be T damp. So the torque responsible for reducing oscillations and stabilizing the pointer damping can be provided by air, fluid or eddy current damping methods. Okay, so what happens is once the deflecting torque and controlling torque are equal to each other, the pointer will just oscillate around its steady state value. So I want to reduce that oscillation because every time I don't want to wait for the instrument to settle. It will take me time to measure then. The time for which the time that I have to measure the particular quantity will increase. I don't want that. So in that case, right, this damping force actually comes into the picture. Okay, so this, right, if you remember, this type of response is from control systems. So this, right, this pointer oscillation can be of mainly 4 types. Okay, because it will be actually a second order system. It can be either underdamped, overdamped, critically damped or oscillatory in nature. What type of damping we want? We actually want critically damped, right? But that is not possible. Critically damped means what? It will totally not oscillate once. It will directly go and reach its steady state. That is not possible. Practical cases, our system will always be underdamped, and we will try to always reduce that oscillation between the mean value. So here, right, if you observe, this is the steady state value, and this pointer is oscillating around its steady state value. That is what we want to stop. Okay, so next there are many principles involved for producing the deflecting torque, due to which my measurement can indicate the particular measured quantity. First principle that we will learn is magnetic effect. Okay, used in instruments like permanent magnet moving coil, moving iron, and dynamometer type instruments. The deflection is caused by interaction of magnetic fields generated by the current passing through the coil and a permanent magnet. So whenever a current passes through a coil in the presence of a magnetic field, the coil actually produces a force as well. Okay, that force will be perpendicular, okay, and it will try to oppose, that we'll see. So example is, this principle is used in PMMC moving iron instruments and dynamometer. So here I have a permanent magnet, that's why the instrument name is permanent magnet moving coil. And this coil, right, these are the two coils. These are actually moving in nature because they can move. So I have two moving coils in the presence of a permanent magnet. So we have two moving coils in the presence of a permanent magnet. Then what will happen is that and this coils, right, actually carry the current, load current, okay, that which I want to measure. So what will happen, as the current flows through this moving coils and there is a magnetic field, what will happen, this moving coils will produce a force. It will produce a force proportional to the current that is flowing through them, and obviously the magnetic field that is being passed. This is constant, but the current, right, depends on the load. So obviously this pointer will deflect proportional to the current that is flowing. Then there will be a controlling torque that will be provided by a spring. There will be a spring here that will provide the controlling torque proportional to the deflecting torque, proportional to the not proportional to the deflecting torque, proportional to the deflection, by how much it deflected. This will provide controlling torque, and finally with the help of damping, this will come down to a steady state place. Okay, so if you want to know more about the working principle of this permanent magnet moving coil, right, you can go to A.K. Sawhney, page 192, I think there is, or you can go to the book, whichever page there is, in where they have explained the permanent magnet moving coil or the other instruments, because I will not go too much in depth of the working principle. I will just touch the basics through which the main equation, deflecting torque equation, is formed. That I will cover, and rest I will not cover, because those are theoretical points and those will be actually not that important for gate examination. So first of all, we understand the working principle of permanent magnet moving coil. The permanent magnet moving coil instrument works on the principle that when a current carrying conductor is placed in a magnetic field, it experiences a force. This force produces a torque, causing a pointer attached to the moving coil to deflect. Same that I explained here, right? So basically, this permanent magnet moving coil, I hope you understand the name, why permanent magnet is there and why moving coil is there. Permanent magnet, because it has a permanent magnet. Moving coil, because it has a moving coil. Okay, two things are same only. Okay, two things are same only, right? Next, what is the working principle? A magnetic field, like a permanent magnet, creates a strong and steady magnetic field between its pole current in the coil. A rectangular coil is suspended between the poles of the magnet. When an electric current passes through the coil, it generates a magnetic field around the coil. Okay, so when the electric field, when an electric current is passes through the coil, it generates a magnetic field around the coil. The interaction between the magnetic fields of the permanent magnet and the magnetic field generated by the current in the coil produces a force on the coil. So what happens when current flows in the coil, right? So it also generates a magnetic field. If you remember, right, like if current is flowing like this, the magnetic field will be something like this, right? It will be like with a cork screw loop, if you remember. So the interaction of two magnetic fields, this permanent magnet field and this magnetic field that has been generated in the coil, moving coil, they will actually produce a torque. This force generates a deflecting torque, causing the coil to rotate, thus indicating the magnitude of the current on the scale. Because it will try to oppose, it will try to go back to its previous state. Whatever the magnetic field there was previously in the coil, it will try to go. So to do that, obviously the coil will rotate. Okay, so this is the block diagram. Basically what will happen is magnetic field will pass through, and this also will have its own magnetic field, right? So these two fields will interact with each other, and then they will simply rotate. Okay, so this magnetic field is like this, so it will rotate like this. Okay, rotate like this. So that is the case only overall. So what will happen is, if you remember, the force on this coil, right, on the back side will be BIL sin theta. For this particular end, right, it will be BIL sin theta, and on the front side it will be BIL sin theta as well. Why theta? Theta is the angle between the magnetic field and the current flowing, so it will be actually 90 degrees. So overall force will be 2 BIL sin theta, right? So overall force, deflecting force, will be 2 BIL sin theta, and we know our theta is actually 90 here because our current flowing and the magnetic field will be 90 degrees with each other because we want the maximum force. So theta will be 90, hence FD will be simply 2 BIL. Okay, so this is the case. Now what is the torque actually? So another thing, this is for a single turn coil. If I have n turns, what will be a total force, total deflecting torque? So this is F dash D. So for n turns, right, for n turns it will be 2 BIL into n. Okay, 2 by BIL into n. Okay, this will be the force, deflecting force, right? Next is torque. So what do we mean by torque? Torque is basically equals to force into the perpendicular distance. Okay, or I can write here so FD into, what is the perpendicular length? Perpendicular length, right? So the force will be along this axis. The perpendicular distance of this from this coil, right, is basically B by 2, right? This will be B by 2. Okay, so this, what is FD? FD comes out to be 2 BIL into B by 2. Now this L times B, right? This is BI, and there is obviously N also there, right? There is a N also. BIL B. So this would, like, N is also there, right? N is also there. So this L times B, right? This L times B will be what? This L times B will be simply area. This L times B will be A. So this will come out to be Bina. This will come out to be Bina. Okay, this will come out to be Bina. This is how we remember. So this formula you have to remember. This is very, very important formula, Bina. I have derived you. Derivation is not that important. Just the formula, main formula is important. So this will come out to be Bina. Okay, where A is the area. A is the area. Okay, area covered by the coil. Area of coil. Not coil exactly. Basically area, this area, right? This area. This whole area is the A, basically L times B. So this is how the deflecting torque is. Now how do we provide the controlling torque? So to provide the controlling torque, right, mostly there are two methods to provide controlling torque. Mostly we will use this method. A pair of control springs provide a restoring / controlling torque, ensuring the pointer stops at appropriate point on the scale and returns to 0 when the current is removed. So obviously when the current is present, it will provide a controlling torque with directly proportional to the distance it moves. So if you know spring, so spring provides a restoring force of K into X, where K is the spring constant and X is the distance moved by the spring. It will provide the same opposite force to make it steady state. So controlling torque will be what? This is the force. Controlling torque will be simply K into theta. Theta means the rotation, right? How much it rotated. Okay, that is what theta is. So this is how we form the controlling torque basically. So theta will be perpendicular to this force. Okay, so this you have to remember also. This also you have to remember. So at steady state, what will happen? Steady state, my deflecting torque will be equals to controlling torque. So what is deflecting torque? Deflecting torque is bina. What is controlling torque? Controlling torque is kc theta. So how much is the deflection? Deflection, right? Theta. Theta is a deflection. So theta will be equals to bin by kc. So I can directly say that theta is directly proportional to the I. Okay, this is the underlining concept, that my theta will be proportional to the current flowing through the moving coil. Okay. Now this current can be actual current as well, or it can be proportional to the voltage, so I can measure the voltage as well. Okay, but this B, N, A, Kc, all these are constant, so this will not change, only I will change. Okay, that is the most important part. Okay, so this theta is proportional to the I. This can be used for current measurement or voltage measurement. Damping torque. Damping is provided by air or eddy currents to stabilize the pointer and prevent oscillations. So how does eddy current damping works? So you can just go and look up in the book Ekisani. They have explained eddy current damping very well. Basically, I will just explain a bit that eddy current damping means whenever it is oscillating, right, that those coils generate some currents, right? So this coil generates some current. So what will happen is they will try to reduce the damping. Okay, we'll actually place a aluminium structure inside the pointer so that it actually has the eddy currents flowing through it, which will also create a magnetic field of its own to reduce the damping. That is what eddy current damping is, or you can go in the book and look up. We don't have that much amount of time to explain everything. Okay, and air damping means, if you know one thing about air, right? If you know one thing about air, is that air damping, I think they have showed here. Yeah, this one, right? So if we observe this, I have an air chamber. So if I just push, like do my hand like this, the air, right? Air also is providing me a opposing force, although that is very less for me. But for this pointer, right, if the pointer is light enough, it will also provide a opposing force to not let it move due to inertia. So air will actually help it to settle down. This air is actually quite different than normal air, so we'll try to do that. We'll have an air chamber through which the pointer will reach here, and then it will deflect, but deflection will be very less. Sorry, the oscillations will be very less because I use air damping, and air actually again provides some opposing force which doesn't let it move, oscillate further. Okay, so that is what air damping is. So yeah, these are the things. You can go and study the basics. We don't have much time to cover that. Now applications. PMMC instruments are used to measure DC quantities like current and voltage due to their high accuracy, sensitivity and reliability. Here, right, actually my theta is directly equals to Bina, B-I-N-A. So if my current is oscillating, what will happen? The pointer will just rotate and then come back. Pointer will just oscillate, right? It will come back. So it cannot measure AC currents, it can only measure DC currents, right? So because if this is negative, I is negative, then what will happen? It will be simply negative. Theta will be negative, which is not possible because 0 will start from here. Theta cannot go less than this. Okay, so I hope you understand. So basically it will measure the I average. Okay, now if my current is Im sin omega t, can you tell me what will happen if I measure this current in a PMMC meter? What will happen is that if my omega is low, okay, if my omega is low, basically pointer will just oscillate. If my, it will oscillate about 0. Like if it is a center type instrument, if it can measure negative currents as well, right, oscillate about 0. If my omega is very high, pointer will not move at all because there will be changes in so high speed that it will not move at all. So pointer will not move. Okay, so that is the case, and this is the theoretical portion. Like the materials used in PMMC is not that important for GATE. You can study this for ESC, right? This control spring as well. You can study this for ESC, damping system as well. All these are important for ESC, not for GATE. We will directly go to numericals now. So let's read this first question. A moving coil of a meter has 100 turns. So N is equals to 100. So this is like mostly formula based questions will come in this measurement. So N equals to 100. Depth is 10 mm and 20 mm respectively. So basically moving coil has two lengths, right? One is the breadth and another one is the depth. So basically the length they have given, length is L equals to 10 mm and depth means you can say the B as well, breadth, right? So B is equals to 20 mm. It is positioned in a uniform radial flux density. So basically the coil is placed in a uniform flux density of B of 200 millitesla. The coil carries a current of 50 milliampere. I is equal to 50 milliampere. The torque on the coil. So what is the torque on the coil? If you know, right? The torque on the coil TD equals to B now. So simply this will be 200 into 10 raised to power minus 3 into 100 into 50 into 10 raised to power minus 3. Okay, so this 10 raised to power minus 3, this 10 raised to power minus 3 actually is micro, but this 3 gets cancelled. Okay, this is in mn, right? This is in mm, but actually we write everything in SI units, that is in meters. So mm times mm is basically 10 raised to power minus 2, because 10 mm is 1 centimeter and 100 centimeter. Okay, this will be 10 raised to power again minus 6, right? Because I have to convert this whole thing into meters. So this 10 raised to power 3 will cancel out. Okay, this 10 raised to power 3 will cancel out. This 100 and how much is this? So how many zeros do I have? 2, 4, 5. 5 zeros, and this is 2 times 5, also another 0, 6 zeros. So this overall thing gets cancelled. What am I left with? Okay, 200. Actually this is 200 millihenry, right? So this will be not 10 raised to power minus 3, 200. I have a 200 here as well. Okay, I have already written it. This 10 raised to power minus 3 is for what? This is for something else, is it? Yeah, sorry, I actually missed a 2 over here, right? This should be 10 into 20. So this should be actually 200. So 200 into 10 raised to power minus 3 into 200 into 50 into 10 raised to power minus 3 into 10 raised to power minus 6. So basically total how many zeros I have? 5 and 6. So this 6 gets cancelled and this 10 raised to power minus 3 becomes micro. 2 times 5 is okay, 2 times 5 is 10 again. So it will be 10 sorry, not 2 times 5. It will be 50. So I will compute this, right? Real quick. Let me just compute this. How many zeros I have? So overall this becomes 10 raised to power minus 12. Okay. And this becomes 2, 2, 4, 5. Yeah, this becomes 10 raised to power minus 10 raised to power 5 into this is 2 times 2, 4 times 5, 20. This is 20. Okay. So what happens? This basically becomes our torque, right? Deflecting torque basically becomes 2 micro Newton meter. So this is the deflecting torque for our particular instrument. This particular instrument, if it carries this much amount of current. Okay. So yeah, I hope everything is correct here. This is 200 times 10 raised to minus 3. This is again 20 into 10, that is 200 times 10 raised to minus 6, because it's in millimeter. Then 50 times 10 raised to minus 3, and I have 100. Sorry, I have 100 turns as well, right? This side I missed. I have 100 turns as well. Sorry, so I have to multiply 100 with it. So this, right, this will become 7 actually. 10 raised to 7. So this actually becomes 200. Okay, this actually becomes 200 micro Newton per meter. That will be the answer to this particular question. Okay, just you have to see the calculations. Let's move on to the next question. So in the next question, a deflection of 60 degrees is observed in a PMMC galvanometer when a current of 1 milliampere flows through its moving coil. So when I equals to 1 milliampere, the deflection is 60 degrees. So I1 and theta 1, they are directly proportional with the controlling torque provided by the controlling spring. So obviously if the controlling torque is provided by the controlling spring, they will be directly proportional to each other. If the magnet in the galvanometer is replaced with another magnet that has twice the magnetic flux density of the original one and the current flowing through the coil is reduced by 1/4 of the initial value, what will be the new deflection? So I know theta is directly proportional to the magnetic field and also the current as well. So my B2 actually has been doubled and my I2 actually has been quartered. So it has been reduced by quarter. So it is I1 by 4. So theta 2 by theta 1 equals to P1 I1 B2, no, not this, sorry, B1 I1 B2 I2. So theta 2 by theta 1 equals to, what is B2? B2 is 2B1 into I2. I2 is 1 by 4 I1, right? B1 into I1. So basically this will become 1 by 2. So half of the previous deflection, theta 1 by 2. So this will be simply 30 degrees. Okay, so the deflection will be half, will be simply 30 degrees. So basically if I want to compute the radians, I will just quickly compute the radians. Just hold on a second. This will be pi by 6, pi divided by 6. So this will be 0.5236 radians. Okay, this will be 0.5236 radians. So let's move on to the next question. So this question is also good. So a PMMC voltmeter with resistance of 20 ohms has a full scale deflection of 120 degrees. So it has a full scale deflection of 120 degrees and for a voltage of 80 millivolt across it. So if a voltage is 80 millivolts, then I know what will be the current. I can find out the current, right? If I know the resistance of that particular overall meter, so IG or IPMMC, I full scale will be 80 millivolts by 20. Four milliamps. Okay. So the coil dimension is 20 millimeter to 20 millimeter. So it is like this, right? Coil dimension is something like this. It is square like coil. So this is 20. This is 20. This is 20 and this is 20, right? So what else they are asking? And having a number of turns of 100, right? So they are having a number of turns of 100. So overall n is 100. Fine. And theta full scale is 120 degrees. That is also fine. Current carrying turns 100 are made of made of specific resistance 1.69 into 10 raised to power minus 8. Find the controls. Okay, all this information I have to write down actually. So the specific resistance, right, or the rho is 1.69 into 10 raised to power minus 8. The control spring has a spring constant of 0.5 into 10 raised to power minus 6 Newton meter per degree. So Kc 0.5 into 10 raised to power minus 6. Okay. The coil resistance is 50% of the total instrument resistance. The value of the diameter of the conductor wire used in the coil winding. So like this is a very good question, actually interesting question. So the coil resistance is 50% of the total instrument resistance. So what will be the total coil resistance? It will be simply RM meter resistance by 2, 50%, right? So what is RM? RM they have provided me as 20 ohms. So basically R coil will be 10 ohms. What else do I know? I know, right? They are asking me the value of the diameter. So what is the diameter basically? So I can write R coil like this. It will be R coil will be equals to what? R coil will be equals to rho L by A. And if you know one thing, that there are n number of turns, right? And all of them will be in series basically. Those coils will be in series, only n number of like these coils are there and they are in series. So each coil has resistance of this, but I have n number of turns. So there will be total n times this, right? All of them are connected in series. So we'll write this. All of them are connected in series. So I know this rho, I know this L. L is what? L is this length, right? That is 20 or what? No, sorry. L is this overall coil length. So this right is a single coil. Okay, this whole thing is a single coil. So what is the length of a single coil? Because this is just a wire, right? Wire is just placed in this shape. So what is the length of a single coil? Length of a single coil is total 20 plus 20 plus 20, that is 80. So L will be equals to 20 into 4, that is 80 millimeter. And what is area? Area, right, is not this area. It's not this area. This is the cross-sectional area of the wire itself. And a wire is always, it is a circle, right? So basically the area, cross-sectional area of the wire or the coil will be pi d square by 2. Previously that area was different. That area was simply this area, right? Overall this area of this rectangle or square. But now it has changed. It is pi d square by 2, and exactly from this I will be able to find out my d. Okay, so what you can do is you can put the values here. So R coil is 10, N is 100, right? We have 100 turns into rho is 10, I think, no, not 1.69 into 10 raised to power minus 8. Okay, divided by L into A into L. L is how much? L is 80 millimeters. So I will convert this into meters. What is A? A is basically the area. It is pi d square by 2. Not 2, sorry. This will be pi d square by 4, right? From pi d square 4. Pi d square by 4. So from here I will be able to find out my d. So what will happen? Okay, this will have a lot of things. We'll try to replicate this as much as possible. This will be 10 raised to power minus 6, 10 raised to power minus 9. D will go over there. So d square equals to 4 by pi into 10 raised to power minus 6 into 1.69 into 80 is also there, and this 10 will get cancelled, so that will be 8 only. So yeah, this will be left out, right? This overall 2 will get cancelled. This will be still here. I will still have 10 raised to power minus 3 here as well. This will be still 10 raised to power minus 3. Okay, this d square, so this 4 will go here. So 10 raised to minus 6, 10 raised to minus 6. So what will happen here? So this thing, right, this thing will become 10 raised to power minus 9 actually, or 1.69 into 8 is how much? 13. So if I take another common, right, so this side will be 4. If I multiply 4 by pi, 4 divided by pi, this will be 17. If I divide this by 10, so 17 d square will be equals to 1.721 So D will be equals to what? 10 raised to power minus 4 equals to D. So this D, right? D will be, if I multiply and divide by 100, this will be in milli. No, this will be 0.312 millimeter. Okay, diameter will be something like this. 0.312 millimeter. This will be your answer to the question. Okay, so this is a very good question. This you should go and revise again. Like here, right? What is happening? I will quickly recap that we know there is a coil, right? And how do we make that coil? Basically, it is a simple wire, and I make tons of it, right? That makes a coil. So I have a single coil, and each coil is square in shape, and total length of this coil is 40 millimeters. And then I keep on rotating it, right? So then and I make number of turns, and with the help of that I make an inductance. That is for another discussion. So but overall length of the coil is how much each turn has 80 millimeters of length. Then I have 100 turns, so overall it will be 80 into 100, so it will be whatever length that is, and those are in series. That's why simply n is getting multiplied, right? That is the reason. And then we just equate with the simple resistance formula and we find out our resistance. Let's move on to the next question. In the circuit shown below, a voltmeter is connected across the points A and B. If the voltmeter has a resistance of 600 ohms, compute error for the following measurement. So if the voltmeter has a resistance of the 600 ohms, then how will I get the error? So what will happen? What will this voltmeter measure? This voltmeter will measure the voltage and current. Okay. So what do we want to measure? We want to measure the voltage is connected across the points A and B. So if this voltmeter was not there, right? If this voltmeter was not there, then what was supposed to be the voltage? Okay, if this voltmeter was not there, what was supposed to be the voltage? This should have been in the error chapter, actually not here, but still that is fine, because we hadn't studied measuring instruments, right? That's why. So ideal case, true value of the voltage, true value, V true value. What will be the case? I will just copy the circuit. It will be the same circuit. This voltmeter will have infinite resistance, right? Voltmeter will have infinite resistance, so that no current flows through this. There is no loading effect, right? This Rm is infinity. So basically they are in series. Then I can simply find out the true value. That will be 200 divided by 250 into 100. So it is 4 divided by 5 into 100. So it is 80 volts. Okay, so 80 volts will be the true value. But what is the measured value? Practical case. Because while measuring the voltage, voltmeter will also have some error. So I will just copy and paste this circuit again. So this, right, this I will replace this voltmeter with a resistance of 600 ohms. So now these two, right, these two actually become combination. So basically what will happen, this will be 200 by I think it will be 600 by 4, something like that, overall resistance. So if I take the parallel combination, right, of this whole thing, this R dash will be 200 into 600 divided by 800. Yeah, this will be 600 by 4, that is 75 ohms. So overall this combination becomes 75 ohms, right? So the circuit can be reduced like this. Okay, so the circuit, what happens to the circuit basically is that this becomes 75 ohms instead of 200 ohms. So there is a huge error here, huge error. So now still applying 100 volts, but now, right, the measured value of voltage, because the voltmeter will actually measure this particular potential. So it will be simply 100 into 75 divided by 125. So it is 4 by 5, 15, 4, 60 volts. Okay, 60 volts. So what will happen here? This is 80 volts and this is 60 volts. So what is the error? If they are asking error in absolute terms, so your absolute error, right, delta V will be simply 200 volts. So that is a huge error. Not 1, sorry, 20 volts, right? That is again a huge error. In terms of percentage, what will be it? So percentage error, right, in voltmeter measurement, it will be 20 by the true value, that is 60 into 100. So it will be 33%, right? 33%. 30% error is huge. Actually, in this case, it is huge. Okay, so this is the error that we will get. Now this question is again interesting. An ammeter has a range of 0 to 100 amperes and gave the following reading. So I'm measuring the current with the help of ammeter, and it is giving following measurements. If the current flow is 0, ammeter reading is 2 amperes, so it is wrong. If the actual current flow is 10 amperes, then it is giving 8, 20, 24, and like this. What is the non-linearity of the scale as a percentage of the full scale reading? So this you have to remember. How do you measure the non-linearity? Non-linearity, right, actually is defined something like this. Non-linearity, because it is not linear, right, because there is always some deviation from the actual value. So non-linearity will be equals to maximum deviation divided by maximum deviation divided by full scale value. So this is the formula. So this thing, right, you have to note it down, take a note of it and remember. So this will be what maximum deviation is, how much throughout all the readings, which one has the maximum deviation, that one you will choose. So here, right, maximum deviation I'm seeing 7. This is actually -7. You will be always measuring like the maximum error, right, it will be measure value minus true value. So here this is 7, this is 3, this is again 3, 4, 2, so this is 7, right, the maximum. So you will take the mod of that, so it will be 7 divided by the full scale value. What is the full scale value? Full scale value is 100. So 100, and obviously if you want to compute in terms of percentage, you will multiply the 100%, so it will come out to be 7%. So the non-linearity of this particular ammeter will be 7%. So like this you can solve. Let's move on to the next question. So again here, a parallel combination of two current sources with waveform is feeding a resistive load of 10 amperes. So I have two current sources. This is I1 and I2. Sorry, this is I1 and I2. They are feeding a load of 10 amperes. So they are connected in parallel and they are feeding a load of 10 amperes. So like how is the circuit drawn? So here I have the circuit. So I have two current sources. One is I1 of t, another one is I2 of t. Okay, so this is I2 of t. So I2 of t, this is 10 ohms. Okay, this is 10 ohms. So basically they are connected in parallel and they are providing current to this particular 10 ohms resistive load. So that is the case. And next is we have a PMMC voltmeter connected across the resistance which reads 50 volts. So I have a PMMC voltmeter connected here as well. So this measures 50 volts, and if nothing is mentioned, you will assume it as ideal voltmeter. That means it, like, through this, right, no current will pass. That is the assumption. It will just purely measure the voltage. So this measures 50 volts. So if this is 50 volts, okay, Then what is the value of X as shown in the figure? So here, right, one thing you have to understand, if a sinusoidal current is passing through a resistor, the voltage will also be sinusoidal, correct? But one thing I remember, that PMMC actually always measures the average, So this, right, actually is measuring the VO average, right? And VO average will be actually combination of two things. It will be one I1 R of T, I1 of T into R average, plus I2 of T into R average. What I know is I2 of T, this average, right, will be simply 0 because this has gone. I need I1 of T into average. What is average of this? This is DC, right? So average will be simply X. This will be the value. So X times R is 10 equals to VO average. They have already provided me the value is 50. So X will be equal to simply 5. What is the unit of X? Unit of X will be simply 5 amperes, right? Because this is in currents. You can understand from here as well. This is voltage by resistance, so it will be current only. So it will be 5 amperes. X value will be 5 amperes. Now in PMMC meters, what we do is sometimes we do the range extension, because PMMC meters cannot handle large amounts of current. But if we extend the range, right, because like then if it can't handle large amount of current, it can't measure large voltages. So we want to extend the range with some different methods. So this is the one of the methods through which we actually extend the range. What we do is the current that is flowing in the measurement, flowing in the instrument is same low current, let's say 10 milliamperes, but through we connect a parallel resistance through which the large current flows, and or some same current flows, and due to that what happens, the overall range of the instrument increases. How it does increase, we'll see that. So in this, right, one analysis we do, this is the actual instrument, okay, and this is the shunt resistance that we connect to extend the range. We'll see how it extends the range. So my I current, right, simple KCL at this particular node will be equals to ISH plus IM. So ISH plus IM, right? So M is equals to what? M is equals to what? M is I by IM, right? M is equals to I by M. M is I by M. Okay. So like this is just a term that I defined, that I will come to later. Now one thing we know, that's this whole resistance is RM, this whole resistance is RS. Now these two are connected in parallel with each other, so voltage will be same. So if voltage is same, basically IM times RSH will be equals to ISH times RSH. So now what I can do, what is ISH? ISH is basically equals to I minus IM, right? So IM, sorry, this is actually not RSH, this will be RM, right? Into RM divided by RSH equals to I minus IM. Now I can take this IM on the left hand side. Then what will happen is, if I take this IM common, this will be RSH plus RM divided by RSH, right? Or like how we can write this? This set RM by, okay, I by IM, right? Okay, I can do this. Okay, fine. This will become this equals to I. So this is the magnifying factor by which I am magnifying the range of the instrument, because originally my instrument was rated for IM, but I am actually flowing a current of I, which is actually not flowing to the instrument, it is flowing to the shunt resistance, but on the outside, right, I am not able to observe that. This is an internal thing. Okay, internal circuitry. So this right, I by Im will be M. So 1 plus Rm by Rsh will be M, and your just hold on, your Rm, like the shunt resistance that we need to connect, right, will come out to be Rm by M minus 1. So I have to connect a smaller resistance so that it can pass more current. So what do we observe from here? That the shunt resistance that I need to connect will actually be lower value, because M will actually be always greater than 1, because obviously I want to magnify the range. That's why M is written, right? So if M is greater than 1, so my RSH will always be less than Rm. I have to connect a resistance which has lower value so that it can take in more current, and the overall range of the instrument will increase. Right? So that is the main purpose of my PMMC ammeter. Okay, so we'll do the same for a voltmeter. What will be the case of voltmeter? So we'll connect a series resistance which will have higher resistance value than this. So basically my M will be what? Again, the magnifying factor will be V by Vm. I am magnifying my voltage range to V. Okay, so what will happen? The current, right, is same. So what will happen? The current is same. So overall V will be equals to what? I into RSC plus Rm. Okay, so V is equals to IRSC plus Rm. So then what can I do is I can write it like this, that what is my Vm? The maximum voltage that this voltmeter can measure. It will be simply I times Rm, right? That will be the maximum voltage. So again I can do the same thing again over here. So I can replace the Vm over here. So this, right, V will be equals to I times RAC plus I times Rm, which becomes Vm. So this becomes V minus Vm by I equals to RAC. So what will be my RAC equals to, this will be V by I and this will be Vm by I. Okay, just hold on. So if I divide by V on both sides, can I divide by V on both sides? No, this will be I, right? So what I can do, V by I, okay, I can replace this. So this I, right? This I is actually what? Vm by Rm. This I is actually Vm by Rm. So this I is Vm by Rm. So this will come out to be V minus Vm by Im, right? Vm by Rm, sorry, Vm by Rm equals to RSC. So what will happen? This will be Rm into V by Vm, that is M, and Vm by Vm is 1. So RSC will be equals to M minus 1 again into Rm. So M is greater than 1. So this time, right, I have to connect a higher value of series resistance than what is connected currently with the meter, than the meter resistance. Why? Because remember this, the maximum current a device can take is fixed. Here, right, I is fixed. Here also I was fixed. But this time what I did was I had to increase the current range. So I connected a parallel resistance so that the I can flow through the other resistor. Here what I did, I had to increase the voltage range. So I will keep the I fixed. I want to increase the voltage. So the like other voltage drop, right? Whatever voltage drop that is left over, that will be come across this RAC. That will come across this series resistance. That will not come across this Rm. That will come across this series resistance. Okay, that will be V. Okay, so this is V. So that's why I connect a series resistance to increase the voltage range. So I hope you understand this point. Simple points only. So I copy this and paste. So again, many educators they tell you to remember. I will tell you no need to remember. These are basic things, right? Basic things. Just remember the derivation, how I derive this part. So let's solve this question. So a 100 microamp ammeter has a internal resistance of 100 ohms. For extending its range to measure 500 microamperes, the shunt resistance, resistance required is of in ohms. This should be in ohms, right? Sorry, this actually came in gate. In ohms required is shunt resistance required is how much? So basically my ammeter has an actual range of 100 micrometers, but I want to measure 500 micrometers. So what will I do? Think logically. No need to remember. Think logically. I have to increase the current range. Maximum current that can flow through the ammeter is fixed. So first of all, I will draw the ammeter. So if I draw the ammeter, there is a resistance. Okay. This is a resistance. So here this is the meter, right? This is the ammeter. This is the RM. So obviously the current through is fixed. I cannot increase the current. So how can I increase the current? I have to make another path. So this is the other path. Okay, this is the other path. So this is the R shunt that I need to connect, so that extra current will flow through this. So overall I want to pass 500 microamps of current. So but this ammeter, right, can only take in 100 microamps of current. So the remaining current, right, will flow through this shunt resistance, that is 400 microamps. So now I can simply equate the things. How to equate? So simply write 400 microamp into RSH equals to 100 microamp into RM. So RM I know, I just need to find out RSH. So this will be 100 by 4. So 1 by 4 into RM. RM is how much? RM is 100 ohms, right? So this will be 25 ohms. I need to connect a resistance of 25 ohms across the this ammeter. Next is this. A current of I of t is passing through this 10 ohm resistor as shown in the figure. Then the reading of the DC voltmeter is connected across the 10 ohm resistor. So what will be the reading across the DC voltmeter? This is not actually this is not actually a range extension question. This is simply a PMMC question. So we'll do all types of question. So what I will do is I will give you few things as homework, and then we'll continue in the next lecture with this, or we can continue in this lecture as well. Okay, we'll continue in this lecture. So this question, right, I will give you as homework. This question you do as homework, and this also you do as homework. Just remember one thing, one logic is that PMMC measures DC. Okay, now we'll understand the sensitivity of a PMMC ammeter. So how can I measure the sensitivity? If you remember the current sensitivity, like these things you have to just remember. Current sensitivity for a PMMC ammeter will be the deflection of the output. Okay, what is the output? We measure the pointed deflection. It is basically theta, d theta upon di, right? Input is current. Ammeter input is current, output is basically deflection. So d theta upon di, that will be basically BNA, okay, by Kc. Why? Because theta is equals to what? Theta is equals to simply BNA by Kc. Okay, that is what my theta is. So if I say I is also here, right? So theta by I is simply BNA by Kc, and exactly that is what is written over here. Output by input, output by input. That is basically thing. Now sensitivity, right, I have explained previously as well. It can be also referred as figure of merit, and figure of merit is actually defined by RM by V. RM is the meter resistance. This thing you have to remember, meter resistance, and V is the full scale voltage. V is the full scale voltage. So that is the case. Or this can be also written as 1 by current full scale, IFST. Okay. So next, this is 200 volts full scale PMMC type DC voltmeter having figure of merits 10 kilo ohm per volt and 20 kilo ohm per volt are contained in series. The series combination can be used to measure a maximum DC voltage of watt. So this you try in homework. I will give you this as homework, and we'll solve in the next lecture. So another thing that we can do is multi-range voltmeter. So previously I was connecting only one resistor with series so that it can measure up until 0 to 500 volts, let's say. let's say this resistor is 100 kilo ohms. I can connect another resistor of 200 kilo ohms that will be of some other range, like 0 to 800 volts, this 0 to 1000 volts. So that's how we do. Basically we switch, like connect the switch according to different points for which we want the range. Okay, so these type of questions can also come. So different settings will have different ranges because the resistances are different. As the series resistances are different, obviously the full scale current will remain same, but the overall voltage drop will change, and overall voltage also will change across the device. Okay, so this was about this lecture, and this is the question that I will leave you with. This is the question that will give you homework, and in the next lecture we'll solve we'll understand rectifier type PMMC meters, and also we'll try to understand MI type of instruments. Thank you for watching, and I will see you in the next lecture. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the second lecture of our measurements chapter, that is measuring instruments. So like today we'll learn about rectifier type instruments, moving iron instruments, and also the working principle of dynamometer. Before starting that, I give you a few homeworks, those we'll cover, and then we'll start with today's topics. So this was the first question, the 8th question that I gave you homework. We had a current I of t that was passing through a 10 ohm resistor as the waveform is shown in figure B. Then the reading of the DC voltmeter is connected across the 10 ohm resistor will be. So what does the DC voltmeter measure? It measures simply a voltage. So the reading of the voltmeter graph will be exactly same as the as this current, but it will be multiplied with the resistor, so it will give me voltage. So but what will the DC voltmeter measure? DC measures average, right? So it will be average of the V of t. So what is V of t? Basically V of t is I of t into R of t. So it becomes average of I of t into R of t, and I know my I of t, R of t is a constant, so I can take that outside. So it will be R into average of I of t. I meant my R is constant, so I can take it outside. I of t is a variable, right? So it will be inside the average. So just the average of the current into the resistance will give me the DC value of the voltmeter. So what is the average of the current? Simple, right? How to find out average of a square waveform? Simply, this is total time period. So what is the area under one time period? So I will do area by time period. What is the area of this first rectangle? It is 12 height times the breadth t, capital T. So it will be 12 times t plus, for the other half cycle it is 5 times t, right? This width is t simply. So it will be 5t divided by the total time period, that is 2t. So it will come out to be 17, right? It is 17 divided by 2, and what is R? R is 10. So it will be 10 into 17 by 2. So it will be 5 times 17. 5 times 17 will be almost, it is 85 volts. So your answer for this question will be simply 85. Okay, this will be the answer. Now let's move on to next question. This question is also like similar concept only. We have, like, this is a recent question. The input impedance of the permanent magnet moving coil PMMC voltmeter is infinite. So that means basically it is an ideal voltmeter. Whenever they say input impedance is infinite or anything is infinite, that means they are talking about ideal. This is the ideal PMMC. I have told you, right, what happens if there is some non-ideality. Then the measurements will differ. We'll learn that, don't worry. Assuming that the diode shown is also ideal, reading of the voltmeter in volts will be. So if the diode is ideal, right, what it will do? Whenever this is in the positive half cycle, this will be on, and in the negative half cycle, this simply will be off. Okay, and the current will flow through this 100 kilo ohm resistor. Okay, whenever we have positive half cycle, simply this diode will be on, so no current will be flowing here. So voltmeter will read 0. So for the duration omega t between 0 to pi, that is positive half cycle, my V, this reading, right, this voltmeter, this is my V of t. My V of t will be simply 0. Now you might ask, how am I understanding that it will be 0? you have to watch analog electronics. I will not explain here this particular thing, how this will be off, how this will be on in the positive half cycle. This has been taught to you in a good detailed manner in analog electronics, so I will not explain that here. So but this I know in positive half cycle this will be off, simple single diode circuit this is. And in negative half cycle, what will happen, my V of t will be simply this will be open circuit. It will be a series combination of these two. Okay, so my omega t between pi to 2 pi my V of t is simply almost equal to this. Actually what is happening is it is Vi into 100 kilo divided by 101 kilo. It's like a voltage divider circuit. This diode will be off basically. It will be like a voltage divider circuit because this 1 kilo ohm is also there. But this is so small, right? I can almost write it equals to Vi. Okay, I can almost write it equals to Vi. So basically what is happening here? What is happening? Basically it is like a half sine wave, right? And it is positive again. It is negative of Vi basically. Why? Because negative? Because Vi, I have assumed my reference potential Vi to be like this. That's why it will be negative. Okay. So now you can understand basically it will be like a half sinusoid. So the VO waveform will be something like this. Omega t for 0 to pi it will be off, and for omega t equals to pi to 2 pi it will be simply on, and it will be almost a sinusoid with a peak of input peak, that is 14.14 volts. This is my VO of t. Okay, so I hope you understand all these things. And how to find out the average of a half sinusoid? It is Vm upon pi. You can do the derivation. All those things have been taught in network theory, so I will not go too much in depth there. So VO average will be simply Vm upon pi. Okay, so what is Vm upon pi? Vm upon pi is simply equals to Vm is this 10 root 2, right? 14.14 means also 10 root 2 upon pi. So I will just bring my calculator. Just hold on. Quickly I will bring my calculator. So if I do this 14.14 divided by pi, I get 4.5, and 4.5 is almost equals to this option A, right? You can do few approximations. Like exact answer will be somewhat less because I have approximated here, but like I hope you understand that point. Why have I approximated? So it will be 4.46 volts almost. Okay, this will be the answer. Okay, these are pretty simple questions, and in measurements mostly simple questions will come, and you will be able to answer those if you know a bit of tricks. Okay, and then we studied about sensitivity, and then I gave you a few questions as homework for sensitivity. So we had 200 volts PMMC type DC meters having figure of merits of 10 kilo ohm per volt and 20 kilo ohm per volt are in series. The series combination can be used to measure a maximum DC voltage of what? If their figure of merits are this, right? And they have a full scale of 100 kilovolts. So what is their internal resistance? Okay, so the internal resistance of, I will say like PMMC 1 M1 is what? RM1 is how much? It is figure of merit, that is 10 kilo ohm per volt into 100 volts, right? It will be simply 1000, that is 1 mega ohm, or 10 cube, or I can say 1 mega ohm only. Okay, 1 mega ohm. And what about the other one? What about the RM2? RM2 is this will be 2 mega ohm. Now one thing you have to keep in mind, that this also tells us how much maximum current can flow. What is the maximum current? So for the first measuring instrument, IM1, the maximum current that the measuring instrument can sustain is simply inverse of this thing, right? Simply inverse. It is simply 1 by 10 milliamperes and Im2 is 1 by 20 milliamperes. So like this definition has come from here, right? All these things I've already explained in the previous lecture. So it is 1 by 20 milliamperes. Now if I connect these two in series, if I connect the M1 and the M2 to measuring instruments in series, the current will be same, right? The current will be same. If the currents are same, that means if I say I want to measure 1 by 20 milliamp of current, this M1 will allow because its maximum current is 1 by 10, that is 0.1. This is 0.1 milliamperes and this is 0.05 milliamperes. So this M1 will allow the current because its maximum is 0.1, so it will say that is fine, totally fine, I will not burn out here, that is totally fine. So 0.05 milliamperes current, I can let that flow. But if 0.1 milliamp of current flows through two of this in combination in series, what will happen? This M1 will say my rated is 0.1 milliampere, I will allow. But once this 0.1 milliamperes reaches here, what will happen? This device will get burned out. Okay, this device will get burned out. This will get damaged. Okay, why it will get damaged? Because its rated capacity is 0.05 milliampere and you are flowing 0.1 milliampere, so it will simply burn out the resistor. So obviously it is not possible. So whenever things are connected in series, you have to choose the lowest of the maximum current rating. So series, you choose min of I full scale 1, that is the full scale of the first instrument, I full scale 2, and so on. Okay, if they're connected in parallel, and what do we do in parallel? We measure the voltage. So while voltage also, you have to understand that you have to choose the minimum there. So that condition will also come. I will derive a formula there, but for now understand this. So obviously here what will happen? I have to choose this as the maximum current, right? So if this is the maximum current, then what is the voltage this combination can measure? The voltage will be the drop across the two. So maximum current will flow, that is 0.05 milliamperes. Okay, this is the maximum current that will flow. So what will be the V full scale? As the current is maximum, voltage drop will also be higher, right? V equals to IR. It is simply proportional to each other. So V full scale of the combination will be simply IFS, that is 0.05 milliampere 10 raised to power minus 3 into the total resistance. What is the combination of resistance? It is simply 1 mega ohm plus 2 mega ohm, right? So it is 3 mega ohm. So 3 into 10 raised to power 6 simply. So this will be 5 into 10 raised to power minus 2. So it will be simply 15. This is 10 raised to power minus 5, right? So it will be 150 volts. So the combination can actually measure total of 150 volts. Okay, if I just put these two in combination, they can measure a maximum voltage of 150 volts. Okay, so yeah, that was the thing. It's not like if I am putting both 100 volt full scale in series, they will both actually measure, like the combination will measure 200 volts. It's not like that, because it depends on the current. If the current is higher, it will burn out the resistor and it will damage the device. I don't want to damage the device. Okay, so then we learned about this multi-range voltmeter thing, that if I have these type of resistors in parallel and I connect one switch with either R1, R2, R3, the voltmeter measurement measuring range also will change. So according to that question, one question came up on gate 2012. An analog voltmeter uses external multiplier settings. With a multiplier setting of 20 kilo ohm, it reads 440 volts. So there can be multiple resistances, right? So what happens? Each cases R1 is there and its own measuring instrument resistance is there. So overall the ratio will be what? Basically it is measuring 440 volts with a multiplier setting of 20 kilo ohms. Okay, and with a multiplier setting of 80 kilovolts, it reads 352 volts. So actually what is happening here? So if I just draw the circuit, you will understand. I will just put this circuit here. Okay, we don't need to remember all these things, no need to remember formulas, just use basic networks. Okay, don't need to remember all these formulas. That's the best thing. Just try to understand the question and use basic networks. That's the best thing about measurements. Just do, it's just the application of network theory, that's it. Okay, So once this circuit is same, okay, once it is connected with this R1, once it is connected with R2. So when it is connected with R1, what does the voltmeter read? It reads 440 volts. Okay, so basically, what is the current in case 1? Case 1, current IG is basically it is unknown for now. It is Vs by R1 plus the meter resistance Rm, correct? And this Ig is proportional to the voltage, right? Ig is proportional to the voltage. So write this sum K times Vg, okay, voltage that is being read by the meter. So this is the voltage that the meter read according to the current Ig1, okay. So because current and voltage are proportional for a PMMC meter, that I have told you during the derivation, okay. Now if this voltmeter, it reads this, actually what does the voltmeter reads? Actually the voltmeter reads the voltage across this Rm, right? Okay, so if the voltmeter reads the voltage across this Rm, what I can do, I can simply use the voltage division. Instead of this, I can use the voltage division. What does the voltage division tell us? So what will be my Vm? Vm is the voltage read across this Rm resistance, right? So it will be simply voltage division. So it will be Vs times Rm divided by R1 plus Rm. Next, this is a Vm1, and in case 2, what is happening? Case 2, again, this is equals to 440 volts, and in case 2, when I am connecting it to R2 is of 40 kilo ohms, R2 is of 80 kilo ohms, then it is reading Vm2, that is Vs into Rm divided by Rm plus R2. Okay, so what will be this equals to? So Vm2, so this, right here I can say that Vm2 is what? Vm2 is 352 volts, right? Now I can say take the simple ratio. If I take the simple ratio, what will happen? If I take Vm1 upon Vm2, so it will be 440 upon 352. Rm will get cancelled, so this will be 1 by R1. R1 is how much? R1 is 40, not 40, sorry, 20 kilo ohms. Okay, R1 is 20 kilo ohms, and 20 plus Rm also I will assume in kilo ohms only, and R2 is 80 kilo ohms, 80 plus Rm. So from here I will be able to find out my Rm value. So Rm will be what? Rm, here Rm will be simply 440 divided by 352. It is 1.25 into this, so it will be 1 by 4, so it will be 20, just hold on, huh? It will, like, if I solve this equation, 25 plus 1.25 Rm equals to 80 plus Rm. So my Rm is simply, this becomes 55 into 4. 55 into 4 is, like, Rm is huge actually. 55 into 4 is 220. Okay, 220 kilo ohms. So Rm is 220 kilo ohms. Now what are they telling? They are telling that if I have a multiplier setting of 40, so this R3 is 40. Now what will the voltmeter read? So if I have a multiplier setting of 40, that means Vm3 will be simply Vs into Rm, this will be remaining constant, divided by R3 plus Rm. So from here, right, if I know Rm, if I put this value Rm here, I will be able to find out my Vs value as well. So I can find out my Vs value. So what will be my Vs? I can use any of the equation, either use this equation or this equation. I just put value of R1 and Rm or R2 or Rm, and I will get my value of Vs. So I will use the second equation. Vs equals to 352 into Rm plus R2. Rm is 220. All are kilos, so kilo will get cancelled because they are in ratio. 220 plus R2. R2 is 40. Correct? R2 is simply 40 kilos. Divided by Rm. Rm is 220. So this will become, I'll just quickly compute this, 260 divided by 220 into 352, 416. Okay, so your Vs comes out to be 416 volts. Now you can simply calculate the measured VM3. So I'll just put this value over here. So I can simply equate this. This will be 416, okay, into Rm. Rm is 220 divided by R3. Now R3 is 80, not 80, sorry, 40. Okay, actually I made a mistake. This should be 80, right? Sorry about that. This should be 80. That's where I made a mistake. It was actually 80 here. Yeah, I made a mistake here. So this will be 300 divided by 220 into 352. Okay, this becomes 480. This comes more 480. Okay, if this is 480, this will be 480 divided by R3 is 40 kilo ohms and Rm is 220, so 220 plus 40. So this will be into 220 divided by 260. It will be 406. So your VM3 comes out to be 406.15 volts. So this will be simply your answer. Okay, so nothing much, just basic use of networks. Just you have to understand what the circuit is. If they're talking about multiply settings, how the circuit looks, that is the most important part, right? Always remember the voltage is measured across this Rm, the meter resistance. Due to that thing, what happens? Some electromagnetic effects happen, and due to that my pointer deflects. Okay, so I hope you understood this point and how I solve this. No need to memorize anything, no need to memorize all this M formulae, no need to do that, just simple use networks. Okay, that's it. So now let's study about rectifier type instruments. What are rectifier type instruments? So there are mainly, like, why do we use rectifier type instruments? Sometimes what happens is we don't want to damage the PMMC meter, because what if I connect a AC signal in a PMMC meter? It can damage the PMMC meter because it is not designed to work for negative values of current. It is only designed to work for DC values of current. So that's why we use rectifier type instruments. And rectifier I have taught very well in power electronics and in analog electronics as well, so you can go through that. Okay, so the main portion is there are two types of rectifier instruments. One is the half wave, another one is the full wave. Okay, so what kind of formula you use? No need to remember this. Okay, so basic, you already know this, that what will be the current whenever this diode is on. It has its own resistance when it is on, forward bias, that is RF. Source has its resistance RS, and PMMC meter has its resistance RM. So the current will be always V by RS plus RM plus RF for positive half cycle. For negative half cycle, it will be off. So for negative half cycle, if it is off, the waveform will be how? Waveform will be simply like this, right? Like this, then again it will be 0, and it will be like a half sinusoid. And do we know the average of a half sinusoid? What is the average? It is simply Vm upon pi. Correct? It is Vm upon pi. So that is what is written over here. Just I have written in terms of I, current, because current with current we understand this better. So like I is how much? Again, all ratios and division. It will be Vm. Vm upon pi can also be written as root 2 into Vrms upon pi. So this factor is simply what? This factor is simply root 2 upon pi. That's why I have just converted Vm to RMS. That's it. So this average value is what? Average value is Vm upon pi. This we already know. This we have studied in networks, and it's good to remember. That's it. You can derive. It's totally up to you. You can derive. It will not take you much time, but as it will come in so many subjects, so it's good. You can remember. And Vm upon pi, I can write as root 2 Vm, not Vm. Sorry, root 2 VRMS upon pi. And this root 2 upon pi, if you do this division, you will get 4.15. 0.45. Okay, not 4.15, 0.45. That's it. That's simply it. Okay. And another thing is that if you had let's say you had an AC measurement, then what would have happened? I am getting like the value that I was supposed to get if I had an AC meter here, and this PMMC type meter was not there, this diode was not there, then I would have got an AC rating RMS. I would have got an RMS value. AC meters measure RMS values. DC meters measure average value, DC values. Okay. So if hypothetically, if I have a RMS measuring instrument, that would have read this full VRMS. But as I have a DC measuring instrument and a rectifier, that is a diode simply. So I am reading 0.45 times the RMS. So I am rating 0.45, very less times the RMS. So they just give you this as a significance that I am reading 0.4 times the this is wrong actually. This should be my DC is 0.4 times AC. So my DC will deflect lesser, right? Because it is lower. AC will deflect more because I am reading 0.45 times of AC. VRMS represents the AC component, right? So I am reading 0.45 times the AC component. That's why this relation comes. Just remember this thing with the help of this formula, and all these things will get automatically clear. So I am deflecting lower. So that's thing. For full wave, what happens? Just a full wave circuit here. The circuitry changes a bit. So whenever this is in the positive half cycle, both D1 and D2 will be on, and hence obviously the resistance of the two diodes will come into effect. That's why there is a 2 RF here and not a single RF. And the average voltage also increases. Why it increases? Because if you remember something about the output of a full wave rectifier, it is for the positive half cycle it is sinusoid, for the negative half cycle also it is sinusoid, but flipped, right? So it is always like a sinusoid. So obviously the average also doubles. As the average doubles, so this 0.45 doubles. This becomes 0.9. That's it. And again your theta DC, deflection for DC will be 0.9 times the AC, right? Whatever AC was there, this RMS was there, it is 0.9 times this. Okay, so I hope you understood this particular thing. That's the simple thing only. So with the help of this, there is one simple concept like question. So this question we can solve. So what are the thing here? We have a sinusoidal voltage with an amplitude of 120 volts. So sinusoidal voltage has an amplitude of 120 volts. So its Vm is 120 volts. Okay, and this is minus 120 volts. Next, and is applied to a circuit containing a rectifying device that blocks current in one direction and offers resistance of 5 ohm in the other direction. So it totally blocks current in one direction and it offers 5 ohm resistance in the other direction. So it is a half wave rectifier, right? It totally blocks current in one direction. So it will be like a half wave rectifier. So I will have a simple circuitry. I will have a input. So again I am applying my network concept. I will not use any formula. I can apply my network concept, right? So that I will do. This is a sinusoid with 120 sine omega t, and then I have a rectifying device. Basically it's a diode, right? That is a rectifying device. That's why I taught you that, just to understand that we can have these type of configurations. So this is a diode which has a forward resistance of 5 ohm, because it is telling when it passes some current, it also gives some resistance as well. So it will be a forward resistance of 5 ohms. And now here, right, let's read the second part. Second part is, if hot wire type instrument and PMMC type instrument are connected in this circuit to measure the current, what would be the readings? So one thing you have to understand is that, don't worry, we'll learn this later on, but for now just understand this concept that hot wire instruments measure RMS. This much I am expecting, that just know this, that hot wire instrument measure RMS, else we will not be able to do this combination type of questions. And what does your PMMC type instrument measures? It measures DC, okay, average. So this is my measuring instrument. Basically here I have a measuring instrument, okay. Are connected, what would be their readings? Okay, if they are connected, if once hot wire is connected, second PMMC is connected, what would be their readings? Now, as they have not mentioned anything about the device, so I will assume all of these are ideal. So these are ideal device. So for ideal device, it will not dissipate any power. As it doesn't dissipate any power, in this case our RM will be 0, okay, as it is ideal device. And in this case, as it is a current measuring device, it will be 0. For voltage measuring device, for an ideal device, RM will be infinity. So you have to understand when to put RM equal to 0, when to put RM equals to infinity, when it is ideal. So just understand this thing fundamentally, that the power dissipated by the device, by an ideal device, will be 0. It will not dissipate any power. So with the help of that concept, you will be able to understand whether it will be voltage or a current, whether it will be RM equals to infinity or RM equals to 0. Here what is happening, it is measuring current, so power will be Im square RM. It has to be 0, so RM has to be 0. Now if it was a voltage measuring device, the power will be Vm by RM square. As power has to be 0, RM has to be higher, so it has to tend to infinity, okay. So here RM will be 0. So my equation becomes simpler, right? So my waveform will be simply half wave rectified, half sine wave rectified waveform. And what will be the amplitude of that current? I will be simply 120 divided by 5 sine omega t for positive half cycle, and for negative half cycle it will be simply 0, right? For omega t, two pi, okay. So this is the waveform. Now I can also draw the waveform, right? I can draw the waveform for you. Omega t, I of t. So the waveform will be something like this, okay. 0, then again something like this. This is 120 by 5, so the peak will be here 24. Okay, this is pi, this 2 pi, okay. So pi, 2 pi and 3 pi, 24 amperes. So now what I can say is, can you tell me the average and RMS of this? This have been taught in network theory, okay. This I have taught in network theory, so I will not go too much in depth here. For a half sine wave, I know the average is simply Im by pi, and RMS will be simply Im by 2. This I have derived in network theory classes, so I will not again go back to that. So Im by pi will be how much? 24 by pi. So we'll just compute that 24 divided by pi. It will be 7.64. Okay, 7.64. And IRMS will be how much? IRMS will be Im by 2. So Im is 24. 24 divided by 12 is 2 amperes. Sorry, not 12. Sorry, 24 divided by 2. 24 divided by 2 is 12. Okay, so it will be 12 amperes. So my hot wire instrument will read 12 amperes and my PMMC instrument will read the average, that is 7.64 amperes. So hot wire is first First is hot wire and then PMMC. Hot wire reads 12 and PMMC reads 76164. Okay, from here also you can verify that relationship that I told you previously here. Okay, your theta AC will be 0.45 times theta DC. So you can verify here that so if I do this right, okay, something is wrong here. 7.64 is pi. Yeah, it is RMS. So it will be Vm by pi. What am I missing here? Okay, this thing is okay. This VRMS, right? This VRMS actually is the VRMS of the sinusoid. This is only with respect to the RMS of the supply actually. So this won't be always valid. So yeah, that was it about this question. Let's move on to another similar type of question. So we have this question. We have a half wave rectifier type instrument with a 0 to 5 volt range. Okay, so the half wave rectifier type instrument has a range of 0 to 5 volts, is to be used for measuring voltages up to 100 volt sinusoid. Okay, the full scale deflection of the current is 5 milliampere. So IG max, the maximum current that the measuring instrument can take, is 5 milliamperes. Assuming the diode resistance is 50 ohms. Assuming the diode resistance is 50 ohms, so we have a half wave rectifying type instrument. So you have to understand how does the circuit of a half wave rectifier looks like. That thing you have to understand. So the circuit of a half wave rectifier instrument is simple, right? It's just here I have a source and it is to be used for measuring a voltage up to 100 volt sinusoid, right? So this will be some 100 volt sinusoid and I will have a measuring instrument here. Okay, the multiplier, that assuming the diode resistance to be 50 ohms. So the diode has its own resistance 50 ohms. The multiplier resistance in kilo ohms. What will be the multiplier resistance in kilo ohms? So what do I need to do? Because its current range is from 0 to 5 volts. So I know the I max, I know its V max, correct? If I know I max, V max, I know my R equals to V by I Rm. So Rm will be simply what? Equals to 5 by 5 milliamperes. 5 volts per milliampere. So it will be 1 kilo ohms. So currently the meter resistance is 1 kilo ohms, but actually I want to read up to 100 up to 100 volts, right? So obviously it is 100 volts. 100 volt sinusoid maximum I want to read. So 100 volt is for the load, not for the input, right? 100 volt, my device should be able to read 100 volt full scale. So what is 100 volt, like what is the full scale here? It should read 100 volt, right? Measure voltage up to 100 volt. That means my average, right? VO average maximum has to go to 100 volts. Okay, although now I feel like this question is bit flawed, because if they're telling that measuring voltage up to 100 volt sinusoid, that actually means they're talking about the input, not the output. Okay, so yeah, that is one thing. So actually this question is bit flawed. This is not 100, this is not this concept is wrong. It is telling 100 volt sinusoid. So if I provide a 100 volt sinusoid input here, it should be able to it should not damage. So 100 volt is the voltage at which it should not get damaged, right? It should remain stable. So if I place like 100 volt sinusoid means 100 amplitude of 100 volts, a sinusoid with amplitude of 100 volts. So if the Vm is 100 volts, right, then what will be the Ig equals to Vm maximum voltage divided by the total resistance of this particular thing when everything is on in the positive half cycle. So it doesn't have any source resistance, so it has 50 ohms of this 50 plus 1 kilo ohm, right? That is 1000 ohms plus the resistance that I will connect in series, correct? RAC, to extend the range. That should be equals to Ig, and Ig maximum can go to how much? This voltage is maximum. Ig maximum can go to 5 milliamperes. So maximum, obviously 5 milliamperes can flow through the device. If I increase the current anymore, the device will get simply damaged. I don't want that. So it will be 5 milliamperes. 5 into 10 raised to the power minus 3 So now I will solve these things. So this will be 20 into 10 cube equals to 1050 plus RSC. So my RC is equals to 1050 plus 20,000. This will be 18.95 kilo ohms. Now, yeah, actually the thing is, when I like the question from where I got the question, I saw there the solution was a bit wrong, because what they are doing is they are assuming that the maximum voltage, average voltage it should measure is 100 volts. So your equation would come out to be Vm by pi equals to 100. But I think that is wrong, because if that is the maximum voltage, instantaneously the Vm will be very high. Okay, and if the Vm is very high instantaneously, it could damage the device. So I don't think that is the correct way to do the questions. So I think that question is a bit wrong. Okay, like solution of that question is a bit wrong. If you have seen this type of question previously, or you can let me know. For me, I think this would be the solution. Maximum voltage that the voltmeter should read is 100 volts. Average voltage will be lower, obviously it will be lower than the peak, but maximum it should read 100 volts. Okay, so now let's start today's topic, that is the moving iron instruments. So what are moving iron instruments? Just first thing is, like PMMC, I will not derive the expression here because that will take too much time and effort, and that derivation is of no use, trust me. Just understanding the concept and the formula is the more important part here. Okay, so what we know, PMMC was what? PMMC was permanent magnet moving coil. But here, if I change this permanent magnet to a electromagnet, I will change this permanent magnet to a electromagnet, then this will become moving iron instrument. Okay, so moving iron instrument operates on the principle that a soft iron piece placed in a magnetic field experiences a force that causes it to move. So if a iron is placed in a magnetic field, right, it can experience a force, it can go north south depending on the magnetic field variations, right. So that principle we use here. The movement is proportional to the current flowing through the coil, and the deflection is used to measure the electrical quantity. So movement will be current flowing through the coil, like there will be some current that will flow through the coil, and the deflection will use the deflection to measure the electrical quantity. So there are two types of MI instruments. One is attraction type, another one is repulsion type. Attraction type means a piece of soft iron is attracted towards a coil carrying the current. Two iron pieces, both magnetized by the current, repel each other. So one uses the concept of attraction, another one uses the concept of repulsion. Okay, so not that important, these types are not that important, mainly the equation that we will derive is the most important thing. But you should just get a brief idea what is a attraction type and a repulsion type MI instrument. Now, what we know is in PMMC, right, the flux was constant because it was a permanent magnet. It was a permanent magnet, right? But here, the coil itself can act as electromagnet. Okay, it is a function of the current. Okay, so as it is a function of the current, the equation will be a bit different. The torque equation, the deflection equation will be a bit different. Okay, so like here, basic picture of a moving iron instrument is given. Here we have a moving iron that is placed in a magnetic field. Okay, so these are all just control weights. We learn about control torque later on, but this moving iron is placed in a magnetic field, and due to that it simply experiences a force, and due to that we get a deflection on this pointer, and that's how we measure. That's the main important takeaway you should understand from this moving iron concept. So how does the deflecting torque happen? The movement of the iron piece generates a deflecting torque that is proportional to the current. As the current increases, the magnetic field strengthens, causing more movement of the iron piece. More current, more deflection, and more movement. Okay, so simple matters. Then control torque is provided by spring mechanism which opposes the deflection. This ensures pointers moves to a steady position and returns to zero when the current is removed. Okay, so simple Kc into theta is the controlling torque. And damping, here we use air or fluid damping. This you should know. Why? Because our core, this core is the concept that we are using is moving iron, because it uses the concept of magnetic field we will not use eddy current damping, because if you use eddy current damping, there will be huge error. So we will not use eddy current damping. And don't worry if you don't know about eddy current damping. We'll learn about damping, 3 types of damping: air, fluid, and eddy current damping at the end of this chapter. It is not that important. Mainly one thing you should understand, that air friction damping uses the concept of basically air drag, right? If this pen is moved like this, right, air is opposing this movement, right? If I move it on the left hand side, air will say it is opposing. That's why there is some friction between the air and this particular movement, although it is very less, but there is some friction. Okay, and we use the concept of air drag for air friction damping. For fluid friction damping, again, if I place a particular ball in water, in bowl of water, and then I pick it up, right, the fluid will also have some friction, right? It will try to keep the ball inside, and due to that concept as well, we use that concept in damping. So we learn that at the end. It's just theoretical thing, not that important. Okay, and just one thing you have to understand, we will not use eddy current damping. This is the most important thing that you need to understand. We'll not use eddy current damping here. Okay, eddy current damping is not used. Yeah, sorry for the interruption, I had to drink a bit of water. So this is the torque equation for a moving iron type instrument, and this is the most important thing that you should know. Okay, so I will want to I wanted to emphasize that this is the most important equation for moving iron instrument. Okay, no need to remember the theory, because once you get into the PYQs, okay, you will see they are not emphasized towards theory. It's morely emphasized towards the numerical approach. Okay, so one thing I have to derive, if we just, you need to learn that we use a control spring, right? So we use a control spring for controlling torque. So I know the deflecting torque is this. What will be the controlling torque? It will be Kc times theta. Theta is a deflection, which will be equal to the deflecting torque at steady state. It will be equal to half I square dl by d theta. What is dl by d theta basically? So as this moving iron rotates, right, as it deflects, its inductance changes. So as its inductance changes, the magnetic field also changes. Okay, so due to that reason, this dl by d theta is here. Okay, that is the intuitive explanation that I can give you. And I square is the square of the current. It's proportional to the square of the current and the proportion to the dl by d theta. So in our cases, most cases, although inductance will vary, but we'll assume it to be almost constant. Okay, that is what our assumption is. Like, we'll see few questions there, we'll understand what do you mean by like almost constant. I will also explain that. Okay, this one to be almost equals to some 1, 2, 3 value. It doesn't vary. If it varies, then the equation will be, then this torque equation will be different. Why? Because from here I can identify my theta is equals to 1 by 2 kc I square dl by d theta. Now if my dl by d theta is assumed to be constant, I can say my theta is proportional to the I square. If theta is proportional to I square, I can design my scale as such it will be able to measure the RMS value, because if theta was proportional to the I, for positive current it will give positive values, for negative current it will give negative. So overall my average current will become 0, so it's of no use. But if it is proportional to the I square, so I can take help of mean square value, through that I will be able to calculate my RMS, right? So actually my theta will give me RMS. But there is one catch here, that I have assumed that dl by d theta to be constant, but dl by d theta can be a variable as well. It can vary as well. As the coil moves, the inductance can change. Okay, so that's why we tend to say that this is non-linear. Okay, my torque is simply non-linear. That is the thing. So like few things are written here. My moving iron instrument, obviously it can measure AC, it can measure DC as well. Why? Like the square also it will measure, right? If some waveform is this constant waveform, the square also it can measure. But it is primarily used for AC, because we calibrate the instrument for AC. We don't calibrate it for DC. So that's why obviously it can measure, right? It can measure DC because it's a constant value. It will be easily able to measure that. But DC measurement will not be that accurate. Why? Reason is calibration. uh, because deflection depends on the magnitude of the current or not on the direction. Okay, it can, that's why it can measure DC. Okay, that is a simple reason. It does not depend on the direction, and DC anyways is single direction, right? Now, non-linear scale, this is the one of the important point that I was talking about. The scale is typically non-linear, more compressed at the lower end and expanded at the higher end due to nature of the magnetic force. Also, it has hysteresis error and eddy current error. So why is it cramped towards the near end and more spacious towards the higher end? If I do this, right, if I want to find out 0.1 whole square, what will be this? This will be 0.01. If I want to find out 0.125 whole square, what will be this? I just quickly compute this 0.125 whole square. Okay, so this will be equals to 0.125 whole square is 0.015625. Now, actually my instrument measures the square of the actual value, right? My actual value, let's say, is 0.125, but as it is proportional to I square, it will measure the square. So if I do square, it is 0.015. If I do square here as well, it will be 0.1. Okay, so the distance between these two are very small, and it will be same if I do 0.15 square as well. Again, the distance will become very small. Okay, so that is the reason why initially the scale will be very cramped, and as we move along, the scale will be more gradual. Why? If I do 50 square, it will be 2500. If I do 75 square, it will be very high, very higher than 2500, right? So it will be more spacious at the end. Okay, so that is a simple reason. So now we will do few questions, and in gate examination you don't have to stress much. Just you can go in autopilot mode, just if you understand this equation and understand the string constant thing. Okay, deflection thing, that's it. In gate examination, not the other theoretical knowledge is not required. So here the inductance of a certain moving iron instrument is expressed as this. So here we are observing that the inductance actually varies with deflection. So this is a case of a variation of inductance, right? Where theta is a deflection from radians, theta is in radians. Remember, the control spring torque is 25 into 10 raised to the power minus 6 radians. The deflection of the pointer in radian when the meter carries a current of 5 amperes. So it is constant current. So that's why now current cannot vary. If current also varies, then it will be very difficult to to do a accurate measurement. Okay, as inductance is varying, so we can do accurate measurement of this 5 ampere current. So what equation I know basically my control torque should be equal to deflecting torque. So control torque is Kc into theta, that is equals to deflecting torque, that is half I square dl by d theta. So out of this I know what is my dl by d theta. dl by d theta is 3 minus theta by 2. Remember, this is in microhenries and theta is in radians, right? Microhenry. Okay, so this is my dl by d theta, right? So I will just replace everything, and they have told me the control spring torque is 25 into 10 raised to the power minus 6 per radian. Okay, per radian. So this basically means per radian means it is the spring constant. That's it, right? It is a spring constant. Okay, so because you can, by the units you can understand that this is not the controlling torque, this is the unit of the kc unit is newton per meter, newton per radian. Okay, so this will become 3 minus theta by 2. This is my dl by d theta, right? This will go on the right hand side, equals to half is there into I square. I square is this 5 ampere, so it will be 5 square, and half I have already put, and on the left hand side I have 25 into 10 raised to the power minus 6 into theta. This is the kc and this is the theta. So now this is a simple equation I can solve. So this 25 will get cancelled. This will be 2 into 10 raised to the power minus 6. Remember, this is also microhenry, right? This is in micro. So I will convert this into standard SI units. half 3, okay, 2 has already gone there, 3 minus theta by 2 and into 10 raised to power minus 6. So this will be 2 theta, and this theta by 2 will go on that side. This will be 5 theta by 2 equals to 3. So theta equals to 6 divided by 5. So it is 1.2 radians. Okay, so this is basically the answer for this particular question. They have asked in radians only, the deflection of the pointer in radians. So the answer will be 1.2 radians. Okay, so these type of question can come in the examination hall. And next, this is the question that came in GATE 2014. A sawtooth voltage waveform shown in the figure is fed to a moving iron voltmeter. Its reading would be close to what? Remember, always just the equation. You need to remember the Rodk equation, and a moving iron voltmeter reads the RMS. These two things you need to understand. So only these type of question will come. They will not ask you working or something like that, right? So if you fed this voltage waveform, you have to find out the RMS of this waveform, and that will be the reading of my voltmeter. Now I have taught in my network theory AC how to find the RMS. Okay, I will not again teach here. That is not the task here. So I will just say that my current will be simply IRMS, right? I meter will be simply IRMS. So the reading will be simply, what is the IRMS of a sawtooth type waveform or a triangular type waveform? It is simply the peak divided by the under root 3. Okay, this is the sawtooth this is the result for a RMS of a sawtooth waveform. And this have already been taught previously, so I'll not waste my time and derive all these things. You can do it because you are at the end stage now. If you are studying measurement, you have studied a lot of subjects, so you know all these things. So it will be peak upon root 3. So this will be 100 by here we are measuring in terms of voltage. Basically a resistor is there, so it will be like it is proportional to the current only. So everything will change to voltage here. Voltage. Just it is raised. We have just placed a resistor. Okay, and through the resistor we are measuring the current, and that current is basically proportional to the voltage. That's how we are measuring the voltage. VP. So VP will be 100 by root 3. So 100 by root 3 is, this will be equals to 100 divided by root 3 is 57.7. Okay, volts. So the answer will be 57.7. This will be the answer simply. Okay, so these types of questions actually come in the examination hall, not that difficult. Let's do the next question. This question came on GATE E 2013. 3 moving iron type voltmeters are connected as shown below. The voltmeter readings are V, V1, V2 as indicated. So this is the total voltage V, and this voltage across the -1 J on is V1 and V2, and all three are moving iron type voltmeters. And what does moving iron type voltmeters measure? They measure the RMS. So that's why I am seeing a AC signal here, right? That's why this is a AC impedance. The correct relation among the voltage readings, V will be equal to this. What is the correct relation? So we can simply, like, this is nothing but a simple application of KVL, right? Simple application of KVL. So if I current is flowing, so the voltmeter reading by V1 will be minus J1, like the voltmeter reads always, remember, voltmeter always reads the RMS. RMS is a positive quantity. It will never read a negative quantity. So V1 will be magnitude of VJ1 times the current. Correct? What will be the magnitude? It always reads the RMS. So I will assume that current is RMS. This I is the RMS current. Okay, this is not any average or something. It is just the RMS current. So this will become simply I. V1 is simply I. What will my voltmeter 2 read? Voltmeter 2 again will read the magnitude I times R. Like I times J. J is J2 and I is simply I. So it will be simply 2I. Okay. Now, what is the correct relationship between V? So what will be V actually? V will be the magnitude of that drop on minus J into I plus J into I. Okay, the whole magnitude. So this will be equals to what? This will be simply I only, because this is the voltage drop, right? This I current is flowing. So what is the drop here? It is minus J into I and plus 2J into I. That's the drop, right? And I will write down the magnitude of that. That will be I. Okay. So now can I write down a relationship between these two? I can observe that V1 plus V will be equals to V2. V2 will read more. So V1 plus V equals to V2. So my V will be simply V2 minus V1. Okay. Remember, all of these are positive. All of these has to be positive, right? So V will be equals to V2 minus V1 and option D will be correct. So did we use any theoretical concept here? No. We use network and few basic things like RMS, and RMS should always be positive. That's why I'm taking the magnitude. These things we used. We didn't use any theoretical knowledge here, right? Just that's what I want you to take away from this lecture, that what type of questions comes and what area you need to focus on. Okay. So that is the important point. Now we'll come to range extension. Again, I will derive some formulas, but you can solve using basic network. You don't need, I will derive using basic network only. You don't need to remember the formulas. Just idea you should have. This is how I do range extension. This is how I add resistance. This is what a rectified type instrument is. That basic idea you should have, except that you don't need to remember any formulas. So if I want to extend my range, okay, so how will I do it? So let's say initially this meter was only able to measure only IM amount of current. So initial measurement was IM amount of current, but I want to extend it. So what I have to do, whenever I want to increase the current rating, I have to add a shunt impedance that will take the extra current, right? That's the concept basically. That's the concept, right? So my this is my IM, and actually I want to measure I current. I want to measure I current, right? That is my aim. So I current will come here. This is the current I want to measure, and my meter can take a maximum current of IM. So how can we solve? One thing I know, that this current will be what? With KCL, this will be I minus IM, and the voltage will always be same. The voltage here and voltage here should be same. So what is the top voltage? Top voltage is J omega into if I want to say just the magnitude, right? If I want to talk about the magnitude of the voltages must be same. So IM into magnitude of Zm should be equals to I minus IM into magnitude of this shunt impedance. Okay. So from here I can directly say that my, what can I say, this IM I can take common will be Zm plus ZSH equals to I into ZSH. So my I can safely say here that, or like if you want to find out ZSH, right? If I want to find out ZSH, and I will define a parameter. Okay, you don't need to do this. You can directly solve with basics in the examination on that. My magnifying factor will be I by IM. This is the initial current that I was able to measure, but finally when I put a shunt impedance, I am able to measure I current. So this will be my magnifying factor. So now if I take common IM on both sides, this is what I will get. This will be magnitude of Zm equals to, this will be 1 minus if I take IM common on both sides, if I take IM common on both sides, this will be I by IM minus 1 into magnitude of ZSH. So my ZSH will simply be this, like this some formula, but I don't want you to remember this formula. Just try to remember how I derive this. That's the most important thing. ZSH equals Zm, magnitude of ZSH equals Zm by M minus 1. Okay, and if I want to do what? I want to understand what will be M. M, like you can replace this whole thing, right? M will be equals to what? If I want to write M, right, I can write M as well. So like, I hope you understand what is magnitude of Zm. Magnitude of Zm will be simply magnitude of omega Lm square plus Rm square under root, and magnitude of Zsh will be omega Lsh square plus Rsh square. Okay, so this I hope you can understand. Now if I want to find out the value of M, what I can do, you can again do this, that M will be simply magnitude of Zm by Zsh, magnitude of Zsh plus 1. Okay, now as M is very high, M is very high, what I can do, I can ignore this one. This one will not do much of a difference, so I can ignore this one. That's why M is almost equals to this, right? M is almost equals to this, basically the ratio of Zm by Zsh. What is Zm? Zm is Rm whole square plus omega Lm whole square, simple magnitude of a impedance. And what is Zsh? Rsh whole square plus omega Lsh whole square. And what I can do is, I can actually write this in terms of resistance as well if I want to do this. So what I will do, I will take common Rm square here and Rsh square here. So if I take common Rm square and Rsh square, this will be Rm outside 1 plus omega Lm by Rm whole square divided by Rsh one plus omega Lsh by Rsh. Okay. This whole under root. Now if this particular terms are equal, okay, then this will be independent of frequency. So we generally try to do what? We generally try to make this ratio equal, right? Why? We try to make Lm by Rm equals to Lsh by Rsh. Why we do this? To make this whole M multiplier factor independent of frequency. Because let's say I am giving some 50 hertz of signal, and for that the multiplying factor is 1000, then I will give a signal of 50 kilohertz, and then the multiplying factor will change, because this omega, it is a function of omega, and as it is a function of omega, it will vary. And I don't want that. As a consumer, would you want that? Would you want the, like, first of all, you understood that, okay, I want to measure 50 amps of current, it can measure 50 amps of current, but suddenly the multiplying factor has changed. As a consumer, will you want that? Because you have changed your frequency of signal? No. So they have to do something. So this is a design parameter, design feature, that if this ratios are same, so obviously everything will get cancelled. So this term will become frequency independent. To make this frequency independent. Okay, so that is the most important point that we have to understand, that to make this frequency independent, these ratios must be same. Do you need to remember? No. But is it easily rememberable? Why? Because you have derived this. If you have derived this, you will be able to easily understand, okay, the time constant must be same, because this is the, like, this ratio is also known as time constant. Although this is not a DC circuit, so no concept of time constant there, but sometimes they tell this is a time constant. But what the main thing takeaway is, this ratio must be equal so that you can make it frequency independent. Now this was for the current extension. Okay, this was for current. What about voltage? For voltage, we have to add resistance in series. So this is for voltage extension. Okay. Same thing again. If I want to extend the voltage, right, the maximum current is through the measuring instrument is Im. That is fixed. Im is fixed, right? Now if I have connected a series resistance, what will happen? It can take in more voltage drop, right? So what will happen is, my Vm is equals to Im into magnitude of Zm, okay, and my V will be what? V will be equals to Im into a series resistance RAC plus like I can take the magnitude as well here, RAC plus RM. I will take the magnitude, actually this will be whole square plus omega Lm whole square into whole under root 2. Okay, so from here you can derive the expressions. Okay, you can do it. So basically what we do, actually we don't, again this is a frequency dependent parameter, right? Frequency dependent parameter. Again I don't want that. So to remove frequency, what I do, I add a capacitor. Okay, that is what I do. So if I add a capacitor, then what will happen, like whole impedance will be Rm plus j omega ml RAC plus 1 by j omega c. So although this will not totally remove the frequency dependency, because still there will be some frequency dependency, but somewhat I can neglect, like somewhat I can approximate the frequencies, okay, for this certain value. So this has been experimentally found out, okay, that if I keep my capacitor value 0.41 times the meter inductance divided by the series resistance, the frequency dependence will be almost reduced. Okay, so this is not that important, because actually mathematically it is not possible to totally eliminate the effect of frequency unless and until you add a inductor. Okay, so which is again not that feasible. Okay, like inductor of negative inductance, which is not possible, right? So that's why we cannot totally cancel this one out. So don't need to remember this, don't worry about this. Mainly they will ask for current extension only. So anyways, this extension topic is not that important, but still, let's, like recently a question came on GATE 2018. Let's do this question. A 0 to 1 ampere moving around ammeter has an internal resistance of 50 milliohm and inductance of 1.1 millihenry. So I will just draw the circuit. It is a meter moving around instrument. It is a current ammeter which has a resistance of 50 milliohm and an inductance of 0.1 millihenry. Okay, so its inductance is 0.1 millihenry and its resistance is 50 ohms. A shunt coil is connected to extend its range to 0 to 10 amperes. So a shunt coil means it has its own inductance and its own resistance. Okay, this is RSH and LSH. Now what are they telling? They're telling the time constant in milliseconds and resistance in milliohms of the shunt coil respectively. Although there should not be a term for time constant because we are operating in AC, but time constant generally they tell it that it is L by R, and they are specifically talking about the coil. So what is the time constant? Time constant is simply for the coil, shunt coil, it is LSH upon RSH. Shunt time constant is LSH upon RSH. Okay, this ratio they want such that it actually works for all frequencies. Okay, this should work for all frequencies. Again, to make it frequency independent, this ratio should be same, right? That is the need. And resistance also we need to find out. That we will find out later on. So I know, right, that this ratio must be same with the meter time constant. I have derived. Again, you can derive, you can solve using the basics, all that you can do, but I will write it directly. Basically the time constant, two time constant must be equal. So LSH by RSH must be equals to LM by RM. So my LSH is what? LSH is where is it? LSH is okay, LSH RSH I don't know, but LM is 0.1 millihenry. So this tau SH, right? Tau SH. tau sh is 0.1 millihenry divided by 0.1 not 0.1 sorry 50 milliohms. So this will become 1 by 10 1 by 500. Okay, this will be a time constant. And what are they asking? They have asked in milliseconds. So if this is in seconds, so I will multiply 1000 to convert this into milliseconds. This will be 2 milliseconds. Okay, so 2 milliseconds is in these two options. So option C and option D are gone, but I have to still find out the shunt coil resistance as well. So for that I need to simply solve this thing. So I know this is the particular configuration. So here 1 ampere is flowing. Okay, 1 ampere is the maximum current, and maximum current that I want to measure is 10 ampere. So the extra current will flow here. Okay, 9 ampere will flow here. So what will happen is I can equate this thing, that my these two voltage drops must be same. So basically here I can say 9 into just hold on, this will be LSH omega RSH whole square plus omega LSH whole square whole under root will be equals to R meter resistance, right? This will be RM whole square plus omega LM whole square. Okay, now what I can do is simply I can take this RSH term common, right? Because I know these terms are same. That's from where that equation came. So if I take this RSH square common in the left hand side, this will become 1 by omega LSH by RSH whole square whole under root equals to RM. I will take common here, RM square. This will become RM only. This will be 1 plus omega LM by RM whole square under root. Okay, so automatically what will happen? This ratio and this ratio are same. That's what I did, right? That's what I did here, right? That was the reason basically, to make it frequency independent. So this will get cancelled. So my RSH will be RM by 9. Okay, so it is equals to, I'll just write this, it is 50 divided by 9. So it is 5.55 milliohms. Okay, so option A will be correct obviously here, that 2 and 5.55 milliohms. So these type of simple question come, but you should know, like, you don't need to remember the formulae, you don't need to remember this formulae, but you should know these type of formulae exist. So when in the examination hall, when you will solve the question, you will be more familiar. Okay, it will not be something new to you. So that's why you should know all this concept. It's okay to not remember, but it's not okay to not know. So now let's study about the dynamometer type instrument. So again I will say that the theory is not that important. Again, the main torque equation is the most important thing, but if you want to read about theory, you can read about it here. So mainly I will recommend you go through the A.K. Sahani book. There they have mentioned the theory very well. So what is a dynamometer type instrument? A dynamometer is an instrument used for measuring mechanical power, torque or force. The term commonly associated with devices that measure the rotational torque in motors or engine. Okay, so like it is used to measure torque or force, but electrical dynamometer is something different, also known as dynamometer wattmeter. We actually use this concept, dynamometer instruments, also known as electrodynamometer instruments, in wattmeters. So in the next lecture we'll study wattmeters. There we'll use this dynamometer type instruments. So it, like, this instrument is used as a wattmeter. So wattmeter type question can also come, and question from dynamometer also come separately. Okay, once we go through the questions, there you will understand. What happens is, now there are two coils. One is the two coils. So there are two currents. So instead of the torque ratio being almost proportional to I square, it is proportional to I1 into I2, the current through fixed coil and the current through the moving coil. Okay, so there are two coils. One is the fixed coil that doesn't move, and due to that a magnetic field is generated, and one is the moving coil that actually moves, and due to that as well the magnetic field is generated, and the interaction of the two magnetic field actually generates a torque on this moving coil, and due to that this coil moves. Okay, the working principle is not that important. You can go through the Ekasani book, there it has been explained excellently, so you can study that. Okay, mainly what is important is the torque equation for us, that I will come to. Okay, so yeah, the working principle of wattmeter I will just say here, like we use it in wattmeter. The dynamometer type wattmeter operates on the principle of electromagnetic induction. There are two coils as I mentioned, fixed coil, it carries the current, and another one is moving coil, it carries the voltage. It is connected in series with the load, so it carries the current of the circuit. This coil produces a magnetic field proportional to the current. Now why is the fixed coil carries the current, and why the moving coil actually measures is the voltage coil? Why is it so? Because for measuring power we need to measure the voltage and the current, right? So the main reason I will say is that fixed coil carries the current, and current is very high, right? So what happens is this voltage coil also actually it carries a current, but the current will be very low. Okay, as it is connected parallel to it, it will have its own shunt impedance which will be very high. So current through this coil will be very low, and current through the fixed coil will be very high, as it carries the main current of the device, right? So what I am explaining, so if I have a resistor here, okay, I am measuring the current and the voltage, correct? And what you know, generally voltmeters are very high resistance. Why? Because if it has low resistance, all of the current will go here and it will cause a loading effect, and I don't want to have a loading effect. So voltmeter have very high resistance, so here the current will be IV, and the current that I want to measure through the device must be a considerable current, right? Because it is a load, it is dissipating the power, it must be considerable. So IA will be very higher than IV. So if IA is very higher than IV, that means the current carried by the fixed coil is higher, so it will be more thicker, so it will be more difficult to move it. That's why we don't use this current coil as moving coil, because if it is thicker it will be more difficult to move this coil, right? So I keep it in the fixed section, and for moving coil I use the voltage coil. Why? Because in voltage current is very lower, so the wires can be thin, so it can move around very easily. So that is the reasoning behind moving coil and fixed coil. Okay, so this much you need to know. Whatever theory you need to know, I will say that about that, don't worry about it. Okay, the deflecting torque in the moving coil is proportional to the product of the voltage and the current, meaning it is proportional to the power being consumed. So actually it is totally proportional to this term. Energy stored in the coil will be half L I1 square plus half L2 I2 square plus half into M I1 I2 plus half into M I2 I1. So it becomes M into I1 I2 only. So the total energy stored in this device will be this much. Okay, and this I1 is the current coil which will be helpful for measuring the current, and this I2 will be the voltage coil which will be helpful for measuring the voltage. Okay, so actually what happens is that deflecting torque is actually proportional to the change in the deflection. What happens is, if I differentiate this thing, this is the total energy, and the deflecting torque is actually proportional to the rate of change of energy with respect to deflection. So if I take the differentiation of this whole equation, what happens is, these terms I assume it as constant. Okay, and my magnetic mutual inductance, right, changes. Why it changes? Because this coil changes its orientation, changes its geometry. So as the geometry is changing, so the self inductance due to this own coil, it will be constant, and this coil also it will remain constant. The fixed coil and the moving coil, their own self inductance will be constant. But as this coil move coil, what happens? The mutual inductance, the inductance between this coil and this coil changes. Why? Because the geometry is changing, the distance is changing, all those things are changing, so it will change basically. So due to that reason, if I differentiate, all these terms will be 0, just this term will be non-zero, and it will depend on this theta. So that's why if I differentiate it, I will get my torque. So TD equals to I1 I2 dm by d theta. This much you need to know. That's it. This much you need to know. You don't need to know anything else. This is the torque equation, and you should know this equation. For a dynamometer type instrument, the torque equation is this, and you have to remember this. Okay, because I'm saying this. So this will be used in the like currents in the questions. Now what type of controlling torque we use? We use spring type controlling torque. Okay, mostly maximum cases we'll use spring to control the torque. Okay, and damping torque, again air or fluid friction damping will be used. Why? Because again it is operating in the change of magnetic field and inductance, right? So we will not use eddy current damping. So again this thing also you need to remember, that we will not use eddy current damping. Okay, so we will not use that. So now this can also, dynamometer type wattmeter also can measure DC and AC. DC means what? Both I1 of t and I2 of t both will be constant, both is I1 I2. So what will be my deflecting torque be? TD will be simply I1 into I2 dm upon d theta. Now if both I1 and I2 are like somewhat related, right? So it will be linear. So if I just want to measure the current, my TD will be proportional to I square, which gives me non-linear relationship. It is not directly proportional to I. So obviously it is not good for measurement of just current or measurement of just voltage. I would not want to do that. Okay, I would not want to do that, as this dynamometer type mostly is calibrated for power measurement. So I will use it for power measurement only. So for RMS measurement of voltage or current, I will use MI type instrument because it is calibrated for it. Okay, that is a simple reason. Again, if I have AC and I have two signals, one is IM1, another one is IM1 sin omega t, another one is IM2 sin omega t minus phi 1. So they are phase shifted by phi. So my torque will become what? Deflecting torque will become what? It will be, use some color. It will be IM1 IM2 sin omega t minus phi So again my torque will actually be proportional to, now it will be proportional to two things. It will be proportional to IM1 IM2 and sine of this, right? Now if I want to break this thing down, can I break it? It is sine A into sine B. So what was the formula for sine A into sine B? So it is proportional to this, right? It is proportional to this thing, sine omega t into sine of omega t minus phi. So there is the peak currents as well, and there is a sine component, and the sine component will be actually helpful to talk about the power. So what will be my deflecting torque in actual expression? So the deflecting torque in actual expression, TD of T will be simply IM1 IM2. This will be there, the sine omega t into sine omega t minus phi into dm by d theta. So what we can use a simple trigonometric formula of sine A sine B. If we recall the formula, it was cos A minus B, cos A minus B minus cos A plus B whole divided by 2, right? If you remember, it was whole divided by 2. So I'll use that same formula only here. Okay, so this will become Im1, Im2. This will become sine A, cos A minus B, right? Cos A is this and cos B is this. So cos A minus B will give me basically omega t minus of omega t minus phi. So it will be plus phi and minus cos A plus B. Cos A plus B will give me what? 2 omega t minus phi. Okay. Cos of 2 omega t minus phi dm by d theta. Now my assumption is this is not varying, right? This dm by d theta is not varying. Now if I talk about average torque, if I talk about the average torque, because it will oscillate somewhat because this is a 2 omega t frequency. So average, what will happen? I will take the average of this whole expression. What will be the TD deflecting torque average? Okay. Simply it will be this. These are constant. This is also constant. Average of a cos omega t, sin omega t, average of that is simply 0. So this average will be simply 0. And my assumption is dm by d theta is not varying. That is my assumption. Okay, that is my simple assumption. How do you write the average torque? Simply use the average formula. It is equals to what? It is 1 by time period divided by 0 to t of dt d omega t, or this time I have used time, so you can use dt. This will become what? If you put all these values here inside, this will become simply I can write Im1 as I1, Im2 as I2 into cos of phi, and dm by d theta is also there, which I am assuming it as constant. And there was, remember, there was a by 2 as well. So where did this by 2 go? So basically what I did was, I know Im1 by root 2 is what? I1 RMS, right? So that's why I1 is basically Im1 by root 2 and I2 is Im2 by root 2. Simply it's just the RMS. That's it. Okay. So my deflecting torque is actually proportional to, my deflecting torque is proportional to two things. Deflecting torque is proportional to average deflecting torque. I am talking about TD average. It is proportional to I RMS whole square, and it is also proportional to cos phi. Okay, this is what my TD average is proportional to. So these things you should keep in mind, whichever you need to keep in mind, that I have explained. Okay, but my assumption here was it is constant somewhat, dm by d theta is constant, but sometimes it will not be constant. Then also you will use this equation only, because with respect to time, with average respect to time, this equation will always be valid. So this equation, whatever I wrote here, this equation is the most important one. This equation I1 I2 dm by d theta is the most important equation that you should remember. Okay, that you should remember. That's the only takeaway that I wanted to explain in this particular section, right, of explanation. So now let's do a bit of questions. So for an electrodynamometer ammeter, the mutual inductance M varies with deflection angle theta. So here they are telling it varies with the deflection angle theta, and I have a electrodynamometer ammeter. So now I am using it as a ammeter, although it will not be perfect, but still in the question they have told me, so I will use that. So if I am using it as an ammeter, what I will do, my I1 will be equals to I2 will be equals to the current. So same current I will let the same current flow. Okay, so then that's how I use it as an ammeter. The same current flows, although it will not be perfect, but still. So my deflecting torque will be equals to what? It will be I square dm by d theta. It will become I square dm by d theta. Deflection angle is in theta. So here, right, deflection angle is in theta. What will be the deflecting torque when a direct current of 50 milliamp flows and the deflection is 60 degrees? So what will be the deflecting torque when a direct current of 50 milliamperes flows? So I, they have told me, is 50 milliamperes, and deflection also they have told me is 60 degrees, right? What will be the deflecting torque? So I will use this particular equation. So here it will be 50 into 10 raised to power minus 3 whole square into dm upon d theta. Okay, so dm upon d theta is, I have to differentiate this thing. So differentiation of cos is minus sign. Already a negative is outside, so it will become plus sign. So 6 into sine theta plus 45, right? Theta plus 45, theta is basically 60, so I'll put 60 here and I will get my answer. So what will be my answer basically? So my answer here, this becomes 10 raised to power minus 6. So I have a micro, I will put a micro outside. Okay, and this will be 2500 and m varies with angle theta like this. Okay, I think one thing I forgot to mention, this will be in millihenry. Okay, mutual inductance will be in millihenry. This unit I forgot to mention, this should be millihenry. So I'll just write everything in properly now. So this will be 10 raised to power minus 3, not minus 3, minus 6 into 6 sine of 60 is 105 degrees. So it will be equals to 105 sine into 6 into 2500 and a 10 raised to power minus 3 is also there, right? This is in millihenries into 10 raised to power 3. So this will be 14.48 microhenry. Okay, so not henry, sorry, this will be 48.48 newton meter, newton meter. Okay, or you can write it 10 raised to power minus 6. So this will be the answer for this question. So as they have asked the deflecting torque, you can tell that the deflecting torque will be 14.48 micronewton meter. Okay, now let's solve this next question. Next, if I have a electrodynamometer type ammeter, again my I1 will be equals to I2. So basically my deflecting torque will be I square dm by d theta. When a current of this much is passed through it, what will it read? Okay, what will be the reading of that particular meter? Again, I have talked about this, right? So if I use it as an ammeter, here I forgot to mention that if I use it as an ammeter, right? If I use it as an ammeter, then it will measure RMS value, because it again follows the square law. So if I am using it as an ammeter, it will give the RMS value of the particular measurement that I am doing. But generally we don't use it because the calibration is not good. But if it is being used, then it will follow the square law, and nothing has been mentioned about dm by d theta. So I'll assume it to be constant. So obviously my torque, not torque, my measurement, right? Meter measurement will be the IRMS. So simply if I am able to write the RMS value of this, I will be able to calculate. And what is the RMS? I have told you how to find out the RMS in the networks chapter for simple signals. So this will be what? DC square plus the AC's RMS whole square. So 6 is the maximum divided by the root 2 whole square. This is the AC RMS whole square divided by the whole under root. Okay, this will be equals to, just quickly calculate this, 8 square plus 6 divided by whole under root. Just hold on, 8 square 36 divided by 2 plus 8 square under root. This will be 9 ampere, 9.06 amperes. 9.06 amperes. Now you might say, sir, how are you calculating this so easily? This have been taught in network, so I will not again explain here, because that will just defeat the purpose of measurements, because all these things you know how to calculate. RMS value you know how to calculate, but the measurement portion I am just explaining. The RMS portion I am not explaining. My expectation is you have already studied network theory, so you already know how to calculate RMS. So here option D will be correct. Okay, in signals also you learn how to calculate RMS. Okay, So what are the advantages and disadvantages of dynamometer type instruments? Advantage is it can be used for both, again same as MI as well. It can be used for AC and DC to measure both current voltage, but obviously it is not that accurate. It provides precise measurements for electrical power, not for voltage and current. It provides accurate measurement for electrical power. That is the most important point. Why electrical power? Because I told you, right, the torque, differential torque is proportional to I1, I2. So one of the currents will be proportional to the voltage, so it will be proportional to the voltage. One of the currents will be proportional to the current through the load, so the deflecting torque will be proportional to the current and the cause of the angle between the voltage and current. Because what was the phi? Phi was the, here if you remember, phi was what? Phi was the angle between the two currents. So one of the currents will be voltage, proportional to the voltage, other current will be proportional to the load, so current. So phi, it is proportional to the angle between voltage and current, cos phi, cause of angle of between voltage and current, and also it is proportional to the voltage and current, product of the voltage and current. So it is proportional to Vi cos phi, which is the equation for power. So yeah, that was the important point. So for non-inductive designs, it ensures accurate readings in circuits with varying frequencies. Because even though the frequency varies, if my dm by d theta is not that varying, right, it is constant term, so it will give me like accurate readings. So this is very good for non-inductive designs. Okay. Next is disadvantage. It is expensive. Dynamometer type wattmeters are more expensive than simple type wattmeters. Like, okay, this statement is a bit wrong. Okay, this statement is actually wrong. This is wrong. Just one statement I want to say is it cannot measure voltage and current accurately because calibration is needed. Calibration is required. Extra calibration is required. So that is the advantage. If you want to measure, obviously you can measure the RMS value, but you need to do extra calibration. Okay, that thing you need to take in mind. Application is ammeter, voltmeter, wattmeter. It can be used as a power factor meter as well. Once we learn power factor meter, this dynamometer type instruments only will use as a power factor meter. It can be used as a frequency meter as well. Sometimes it is being used as a measure as well. Okay, so this has its application. It can be used for many things, but we have to calibrate the instrument. We cannot use a dynamometer type wattmeter as a power factor meter. We cannot do that. We have to calibrate the instrument. Okay, so here like I have written what it does and what it doesn't do. Okay, those things are there. You can read it. Let's do few questions on this dynamometer type instruments, and then we'll wrap up today's lecture. Or what I can do is I can give these questions as homework, and in the next lecture I will solve before starting this, right? Because next lecture we'll study about wattmeters only. So I will just take the screenshot this question. Okay, you have to use that same formula only. What was the formula? It was TD equals to I1 I2 dm by d theta. Okay, that was the formula that you need to use. Okay, so you can take screenshot of these questions, and then like in the next lecture we'll solve all these 3 questions. Okay, so yeah, that's it for today's lecture. I hope you enjoyed the lecture, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I am Anish, and today we will be starting the lecture 3 of this measurements chapter, right? Measuring instruments chapter. So we have up until now learned about PMMC type instruments, MI type instruments. We have done the questions. The questions are the most important thing in measurements. Treat measurement just like a questions practice session, right? No need to go too much in depth on the theory, because like there is infinite amount of theory and that will just waste your time, and you need to get good marks in measurement subject, and through practicing questions only you will gain that knowledge. So let's start with the homework questions. So this one was the first question that I gave you homework. I will just check quickly if I gave other questions as homework as well. I most probably haven't. No, I haven't, right? I have solved all these questions. So all these questions we have solved actually, yeah. So this one was the first question that I gave you as homework. Let's start this question. So here in this question, what are they asking? They are asking, I have a 10 ampere range electrodynamic ammeter is controlled by a spring with a torsion constant of 10 raised to power minus 7 Newton meter per degree. Whenever these type of units come, what is this? This is the unit of spring constant. So torsion constant, spring constant, all those things mean the same only. It means it is Kc. But do take in mind that this is in per degree. Generally, it's in per radians. If nothing is mentioned, we'll choose it per radians. But if they have mentioned it degree, so I will obviously choose my theta as degrees. So my spring constant Kc, controlling spring constant, is 10 raised to power minus 7. Now the electrodynamometer type ammeter is 10 amperes. The full range is 10 amperes. That means my I is full scale. If I give it full scale, I will get full deflection at 10 amperes. And the full scale deflection is 110 degrees. So IF theta F SC is 110 degrees. The inductance of the instrument when measuring a current of 10 ampere will be, if the initial inductance is 2 microhenry. Initial inductance means the inductance here, as it is a electrodynamic type ammeter, so I will talk about mutual inductance only. They are talking about mutual inductance. If my mutual inductance initially was 2 microhenry, when my theta was simply 0, there was no deflection. That is what it means by initial inductance. The inductance changes linearly with deflection of the moving coil. So if inductance changes linearly, that means it follows a equation of a straight line. That means my inductance will be, M will be equals to M initial, okay, some constants M initial plus K into theta, right? So like you can write it other way. If you recall this form, it is y equals to mx plus c. That's it. This is a constant m into x. This theta is varying it. As this theta varies, the mutual inductance varies. So that is happening, and this is the initial inductance. Okay, at theta equals to 0, my mutual inductance equals to mi. So all this information I have. So how will I do it? Okay, I know current flowing is 10 amperes. So can I find out, can I write the torque equation? What is the torque equation? Torque equation TD equals to I square dm by d theta. Correct. So what is TD equals to? At steady state, TD should be equals to controlling torque. So it should be equals to Kc into theta. Okay. So I square is 10. So it is 10 square into dm upon d theta. That is Kc is 10 raised to minus 7. Okay, sorry, not this. Sorry, this I have to identify, right? Dm by d theta is what? Dm by d theta. If I differentiate both sides with respect to theta, I will get k. So I will find out the value of k. So this will be k into Kc. Kc is how much? Kc is 10 raised to power minus 7. 10 raised to power minus 7. Everything is in SI units, so I don't need to do anything. And theta is in degrees. Remember, it's in 110 degrees. So what will be my k? My k will be 1.1 into 10 raised to power minus 7. Okay, and remember this thing is in microhenry, right? So now this is Henry per degree. Henry per degree. So now I want to find out my MF. What will be my MF when there is 110 degrees of deflection? MF when there is 110 degrees of deflection, it will be 1.1 into 10 raised to power minus 7. But as this is also in micro, so I will not do anything right now. I'll just solve it simply only. So this is this into 110 plus this is in degrees, right? This is in degrees and this is also in degrees. So degree gets cancelled. Okay. So plus initial. What is the initial? Initial is 2 into 10 raised to power minus 6 Henry, right? All this is in Henry. So now if I want to simply write down the values, what values I will get? So this will be equals to simply if I take 1 0, this is 10 raised to power 110 degrees. So this will be 1.1 is there. So this will become, if I take out 1 0, 11 into 1.1, 11 into 1.1, 11 into 11 is 121, right? 11 to 11 is 121. It will be 1 point, not 1 point, sorry. It will be 12.1 into 10 raised to power minus 6, correct? Yeah, 1 0 has been gone, so that's it. And plus 2 into 10 raised to power minus 6 Henry. So this will come out to be 14.1 micro Henry. Okay, so this will be your solution for this question. Pretty simple. Just what you have to identify is that, understand that what is the question asking us. As it is a electrodynamic type ammeter, whenever you read the word electrodynamic, you just instantly go back to that torque equation. Torque equation is what? TD equals to I square dm by d theta. Okay, and if you solve it, then your answer will come out to be this. Simple, you equate the spring constant, control spring torque with the deflecting torque, and that's it. You will get your answer. So these two things you need to keep in mind: spring constant torque and your deflecting torque for electrodynamic type instruments, which is not wattmeter. Wattmeter will study separately in today's lecture. So let's solve this other question. So this question is again interesting. For a dynamometer ammeter, the mutual inductance M varies with the deflection angle theta in degrees. Again, they have told theta is in degrees. Okay, so that's not a problem. Mutual inductance is this. What is the deflecting torque produced by direct current of 25 milliampere for a deflection of 50 degrees? So how do you find out deflecting torque? Again, you'll simply write the torque equation. What is the torque equation? TD is equals to I square dm by d theta. So this is equals to just hold on, what is the deflecting torque produced by this? Okay, so they have given me the condition, right? Current flowing is 25 milliamperes, so it will be 25 into 10 raised to power minus 3 whole square into dm by d theta. So this will be 12 sine theta plus 10 and this is in millihenry. Remember, this is in millihenry. Okay, 10 raised to power minus 3. So from here they have told me that deflection is 50 degrees, so I'll put 50 here. So if I put 50 here, this will be 625 into 10 raised to power minus 9 into 12 into sine 60. What is sine 60? Sine 60 is root 3 by 2. So it will be into root 3 by 2. So I'll just write down the values. Just hold on, we'll just write down the values here. Okay, this value will be 625 into 12 into root 3 divided by 2. So if I take another 10 raised to power 3 inside, it will be 6.495 into 10 raised to power minus 6 Newton meter, or I can write this in micro as well. In the examination they can ask this in micro. So this will be equals to 6.495 micronewton meter. Okay, so let's solve this next question, which actually came in gate. So electrodynamometer type instruments question can actually come in gate, which are not wattmeter, because mainly we study electrodynamometer type instruments for wattmeters only, but by its own in isolation the question can also come. Okay, let's read this question. A DC current flowing in a circuit is measured by two ammeters, one PMMC, another electrodynamometer type, okay, connected in series. So one is PMMC, another one is electrodynamometer. Both are connected in series, so both have same current, I PMMC and I dynamometer type. Okay, dynamo will have same current. Okay, the PMMC meter contains 100 turns in the coil. So PMMC meter has N equals to 100. The flux density in the air gap is 0.2 Weber. It is 0.2 Weber per meter square. And the area of the coil is 80 millimeter whole square. Area of the coil is 80 millimeter whole square. So area will be 80 millimeter whole square. Okay, the electrodynamometer ammeter has a change in mutual inductance with respect to deflection 0.5 millihenry per degree. So it's dm by d theta. So these are all the parameters of the PMMC meter. Okay, and I will write the parameters for electrodynamometer. So they have given me the dm by d theta. Again, it is given in degree per degree, right? Millihenry per degree, that is 0.5 millihenry per degree. So I will write this in SI terms. It will be 0.5 into 10 raised to minus 3 Henry per degree. Okay, the spring constants of both the meters are equal. The spring constants of both the meters are equal, that is both of them have same controlling torque. Okay, same controlling torque, not same controlling torque, sorry, Kc is same. So this also has a spring constant of Kc, this also has a spring constant of Kc, same Kc. They have not mentioned what is that value. The value of the current add with the deflections of the two meters are same. So the deflection is same. Deflection means what? Deflection is represented by what? How much the pointer has turned, right? And what parameter defines that? Theta. That means they want to equate the theta. Okay, so they want the theta to be same. So for the theta to be same, what needs to happen? So here what is the theta in the case 1 for in the PMMC case 1? So theta 1 will be what? I have to equate the controlling torque and the deflecting torque. So controlling torque is how much? Kc into theta 1 equals to B now, right? It is B into N into area into current, right? I. What is the current? Current they have not told me, but I know it is same across, right? Same because they are both of the devices are connected in series. I will assume it as I for now. So theta 1 will come out to be this value divided by Kc. Okay, fine. What about here? Here again Kc into theta 2 will be equals to I square dm by d theta. Here it will be I square dm by d theta. So which will be equals to 0.5 into 10 raised to power minus 3 into I square, because I don't know the value of I. So now what needs to happen? This will, like, this Kc will come down here, this Kc will come down here. So both of these will be simply equal, right? So my theta 1 will be equals to theta 2. That means what will happen? 0.5 into I square equals to 0.2 into 100 into 800 into I. This was in centimeters, right? If I remember, no, this is in millimeter square. So if this is in millimeter square, right, I have to convert this into SI units. So I have to multiply, and this is not 800 actually, this was 80, right? I made a mess of it. It's not 800, this is 80, and this will be into 10 raised to power minus 6, and here as well it will be 10 raised to power minus 6. So my I will be what? It will be, this is 1 by 2, so it becomes 8 into 10 raised to power, this totally becomes 8 into 0.4. So I comes out to be 3.2 amperes. But do I need I? No. In the question they have asked me, okay, the value of current, they have asked the value of current itself. So I. So from here you can directly say what will be the value of current. The value of current will be 3.2 amperes. So they should have mentioned units as well. It should be 3.2 amperes. Okay. Now for you to find out the deflection theta, you need the spring constant. If you don't get the spring constant, you will not be able to find the deflection. How much it deflected, okay, in degrees. So those were few questions in GATE. Like these type of questions come. I hope you are understanding the level, what level of question they ask, and what things you need to know to solve the questions basically. So that was it basically about the questions. Now let's come to today's topic, that is electrodynamometer type wattmeter. So what is electrodynamometer type wattmeter? Although I gave you a brief overview in the previous lecture itself, here I will go into it in more details. So there is one coil, one is fixed coil, one is the moving coil in electrodynamometer type wattmeter. Now what if we measure the same thing? Okay, instead of instead of measuring the same quantity like current or voltage with both the coils, what if I measure voltage with one of the coils and the current with other coil? Because both are proportional, right? Both the currents are proportional always. And in the previous lecture I told you that if one of the currents is proportional to the voltage and the other current across the coil is proportional to the current across the same load, then there will be a factor of cos phi, and that phi is the angle between voltage and current. So like that I get the power equation. Okay, that my power is VI cos phi, that we learn in network. In the today's lecture as well, I will prove that your deflecting torque expression was VI cos phi, and that VI cos phi is actually power expression. That I will prove just in the next slide. Okay, so the fixed coil is connected in series with the load and carries the load current, and is also known as current coil. As it carries a load current, it is known as the current coil. It will be thick. Fixed coil will be thick. Why it will be thick? Because it has to carry more current. That means its cross section area must be higher. That's why it is thick. And the moving coil, the moving coil connected across the load carries a current proportional to the voltage and is referred to as voltage coil, potential coil, or pressure coil. As the current is proportional to the voltage, what it happens is it is connected in parallel to the load, right? Generally. So if it is connected in parallel to the load, it should take in minimum current, right? Because I don't want any loading effect. So let's say some current IC is flowing through the load. I don't want some of this IC to go in the voltage coil as well. So here the current will be very, very lower, and that is my ideal characteristics. But obviously I cannot minimize it. We'll learn in today's lecture the errors in wattmeter. There we'll see what kind of errors I get due to this placement. Okay, that we'll see. Don't worry about that. For now, assume ideal. Okay, and this is taking some very low amount of current. As this is taking very low amount of current, that's why the wire here can be very thin. But as the wire is very thin, what will happen is there can be inductance. To minimize the effect of inductance, obviously we make this resistor R as high as possible. Okay, to minimize the effect of inductance. So that I have few things I have told. Don't worry, we'll come to this later on. But just understand the basic formation of a electrodynamometer type wattmeter. Okay, so now we'll derive the power expression. Okay, for a load. So if a load has some voltage Vm sin omega t and current as Im sin omega t minus phi, what will be the power expression? So if I write the power expression, my P of t will be simply V times phi, right? This is the instantaneous power. What is the instantaneous power? It is Im Vm Im sin omega t minus phi. Okay, so this is the instantaneous power, right? This is the instantaneous power. This I have already taught in network as well, in complex power as well, the power expression. But still, I will here again, I will just quickly derive it. Just quickly, what will be the average power over a cycle? Because in AC, right, we have to measure average over a cycle, how much power actually I am consuming. So if I compute the average, what will I get? It will be total time period 1 by time period integration from 0 to 2 pi of P of t, right? P of t d omega t. This is equals to what? This is equals to my Vm Im by 2 sin omega t to sin omega t minus phi integration from 0 to 2 pi. Because Vm and Im are constant, I can take it outside of the integration, right? And if you integrate this, obviously I will not do this sin A minus sin B formula. Previous lecture I solved. If you integrate this totally, you will get back your result as Vrms into Irms cos phi. I will not totally derive it, like this basic integration you can do. Okay, so from here I get the result as power expression as Vi cos phi, and that's why my electrodynamometer type instrument will directly be proportional to the power. Because in the previous lecture I already mentioned that if I have a current, okay, I1 and I2, because in electrodynamometer type wattmeter there are two currents basically, and those two currents interact with each other and one of the current is proportional to the voltage and I1 current is proportional to the current. Okay, proportional to the load current. So I1 is equals to Im sin omega t, I2 is equals to what? Vm by R sin omega t. This R is the resistance that is connected here. So it is just proportional, right? This R is just a constant. So I2 is actually proportional to voltage, right? Proportional to the voltage. Okay, that is the most important one. Now, in the previous lecture also I derived the expression. My torque average, TD average will come out to be what? TD average will be I1, I2, Im maximum peak of this divided by 2 into dm by d phi. Okay, so this will come out to be, what is the peak value? Im. Previous lecture I have derived the expression, so I am taking that expression from that. This will be Im, this will be Vm, this will be R. Okay, and obviously the angle between these two, that is cos of angle between these two, cos of phi. And do remember there is this dm by d phi as well. Okay, and I want this to be constant. If this is constant, then what can I say? I can say my torque, right, is directly proportional to power, because this R is a constant term and it is equals to Vm Im cos phi, which I derived here as well. This should be 2, right? This should be 2. Okay, so my torque, average torque, will be equals to will be proportional to the power, right? Will be basically proportional to the power. This is the important point that I want to take away, is we have assumed this to be constant. If this is not constant, there will be errors in the measurement, and that's the main thing. So for it to be constant, what needs to happen? Obviously my inductance will vary, but if it varies linearly, then there is no issue, right? If my M with respect to deflection varies linearly, then I will get a constant slope, correct? So my dm by d theta will be simply constant. Dm by d theta will be simply constant, and that is not an issue. So that is what I want, right? With respect to theta, this dm by this mutual inductance should vary linearly. If it varies linearly, then I have no issues. If this doesn't vary linearly, then I have issues. Okay, so that is a problem, that is a drawback of this particular thing. Okay, so there are two types of configuration. Okay, if I have for a low load current, both fixed coil are connected in series. For high load current, both sections of fixed coil are connected in parallel. So what happens is in case of low load current, your fixed coil, like generally this is just for construction purpose. In our wattmeters, our fixed coil, they generally divide it into two coils. Okay, fixed coil 1, fixed coil 2. Now if the load current is low, what they will do is they will connect these two coils in series with each other, so they will carry the same current. So let's say I have, like, my load current is 5 amperes, which is, assume in our case, is pretty low. So if it is pretty low, what I will do, I will connect these two fixed coil in series, and this 5 amperes will flow through both the fixed coils. But now if my load current is very high, let's say 50 amperes, okay, and each of my fixed coil can only take 30 amperes, so I cannot connect that in series. If I connect in series and 50 amperes of current flows, they will simply burn the fixed coils out. So what technique I do, I simply connect them in parallel. So this actually happens in our measurement. If you go into the lab, right, and you will see those coils will be connected in parallel in your measuring instrument. If you go to the wattmeter, there are two connections. If you remember, you used to change the range of the wattmeter. That's basically what is happening inside. What is happening, the two coils are getting connected in parallel. Okay, just hold on, I will just check if everything is recording or not. Yeah, everything is recording. Two coils will be connected parallel. So that's how we increase the range. Okay, and one more important point is our current coil and pressure coil are both air core coils, so there will be no chances of saturation. There will be minimized saturation, as the current will be not that high. If the current is very high, obviously it will saturate. Okay, the core will saturate, but it will not saturate according to the given range. Okay, and as mentioned previously, our potential coil or pressure coil must be highly resistive to minimize the inductive error. Okay, but in case of energy meter, which we will learn later on, our pressure coil must be highly inductive. Okay, but here in case of wattmeter, for wattmeter, our pressure coil must be highly resistive. Okay, so this dynamometer type instrument we actually use in many places, right? For wattmeter, for ammeters as well we can use, as we learned through the questions. For voltmeter also we can use, for measuring energy as well we can use. So that will be covered in after 2-3 lectures. Okay, so now let's come to the two types of connections of a wattmeter. There can be two types of connections, because I think you might have this confusion that whether to connect the current coil directly in series with the load or the pressure coil directly across the load. Which one to do? This is known as the main side connector, or this is known as the load side connector. No need to remember the name. Just understand these basic fundamental thing, that my pressure coil can be, like, my current coil can be connected directly in series. If it is connected directly in series with the load, then I cannot connect my pressure coil here, right? Then it won't be series. This will be the connection then. So I have two options: either connect the current coil with series with the load, either connect the pressure coil with parallel to the load. Now in these two cases, which one is the best? The answer is, it depends on the load voltage and current, because in both cases there will be some error. What kind of error there will be, which we'll derive right now. I will derive those errors right now. From that we'll understand what kind of errors there will be for these two types of connections. So let's first understand this connection where my current coil is in series with the load. No need to remember this main and name and all those things. It's okay if you don't remember the name. So if my current coil is connected in series, so I had two currents, right? Here I had two currents, I2 and I1. So my I1 or IC, my true value will be what? True value which I want is VLIL cos phi. This will be my true value across the wattmeter. So my this is my actual value, and I will compute the error with respect to this true value. So my ICC will be what? Simple equals to IL, because it is directly connected across the load. So it will be equals to IL. Okay. What about my IPC? What is my IPC? IPC, how you can compute? So this coil, right, will have some small resistance RC. Okay, generally they will give you this resistance. Obviously, any coil, any wire has its own resistance, right? RC. So what will be my VPC basically? What will be my VPC? VPC will be this load voltage VL plus ICC into small RC, which will be very small. That's why the error also will be very small, but it will be some volt, well, right? And this ICC is equals to what? This ICC is equals to L. So now my wattmeter will measure what? My wattmeter, measured value wattmeter, okay, is the, like, I will calibrate my wattmeter as such. It will measure the voltage across the pressure coil, the current across the current coil, and the cause of angle between those two. So that is my calibration. Okay, so it will measure this VPC, ICC, and the cause of the angle between IPC and VPC. Correct. This is what my wattmeter will measure. Not IPC, sorry, ICC. So this I can write in different term as well, because it will be required here. This I can write like what? This will be equals to, if you have studied complex, very well. If you haven't, then you have to go and watch my complex lectures. So this I can write it like this, that this will be equals to VPC ICC real of VPC ICC conjugate. So if you find out real, right, what is VPC IPC? It is the apparent power, and the real of that apparent power is the, gives me the actual power, right, and that will be measured by the wattmeter. Okay, and this is the angle, this is the current, VPC and ICC and all those things. Why I had to make this format? Because like there was simply like this phases and all, or if you want to measure this, right, you can directly measure this as well, but this is not that important. We can solve it with the help of this thing only. So real part of this. So what can you write here? So what is my VPC equals to? What is my VPC equals to? My VPC is simply equals to VL into IL RC. Okay, so my VPC is equals to this. So VPC will be VL, I will write the power only, my measured value of wattmeter, real of this part, which is equals to VL plus IL into RC into, and ICC is IL itself, right? ICC is IL itself. So it will be this value. Okay, so what I can write is this is the conjugate, right? IL conjugate. So this is real of VL IL conjugate plus, now this is IL times IL conjugate. What is IL times IL conjugate? If you remember some property, Z times Z conjugate, complex number, is simply the magnitude whole square. So this will be IL magnitude whole square into RC. Now if I write the real of this, what will happen? This is a real term, and this is, if I want to write the real term of this, what will be the real term of this? It will be VL cos phi. That will be the real component of this, right? So I can convert this VL cos phi. If I just want to write the real term, if I want to ignore the imaginary term, because it will have two terms. It will have this term, that is magnitude of IL square RC plus J VL sin phi. Okay, so this will be equals to what? I just want the real part. Real part is this, so it is equals to VL cos phi plus magnitude of IL whole square RC. Now this is the expression of my measured value, correct? So there is some error, right? This was the true value actually, VL cos phi, that I wanted. Okay, but there is this additional term. So my wattmeter will actually measure this additional term. So from here I can actually derive the expression for the error. Okay, But before going into that, I just wanted to understand if I can derive this expression, right, some other way, my measured value. So the other method is basically, if I have written down the thing that your measured value, right, power measured across the wattmeter will be the loss due to this current coil plus the power measured across the load, correct? So here what we do is we ignore, yes, there is some loss in this pressure coil as well, but we ignore that. Okay, and if you do this, right, our error will come out to be this IL square R, which I derived here previously, right? IL square R, this one was the error. Okay, so yeah, I derived using the basics as well and using direct intuition as well how the power loss will be. We ignore the loss due to the pressure coil. That's just a assumption that we take. Okay, next is load side connection, or if my pressure coil is connected directly across the load. Again the same thing, right? Here my VPC will be directly equals to VL, but this time my IL will not be equals to my IC will not be equals to my IL, correct? My ICC, it's a vector quantity, it will be equals to IL vector plus IPC vector. Okay, so here what will happen is that my power will be what? Again, I can write this IPC like this. ICC will be equals to IL plus VPC divided by IPC. This is just a vector quantity, right? All these are just a vector quantities or phasor quantities, you if you want to say like that. VPC divided by RP. Okay, now what will my wattmeter measure? My wattmeter will measure the real power, right? So real power I can write in two ways. One is this real of VPC ICC conjugate. There is a other way as well. I can write it like this as well. Real of VPC conjugate ICC. Okay, this will not change the real power. The reactive power can change, but real power expression will be same here if I take the conjugate. Okay, it won't make a difference, because if I take the whole conjugate of this, it doesn't make a difference, right? Because it is a real quantity. So now if I replace my terms here, what is what is VPC? VPC is simply equals to my VL, right? So my wattmeter measure value, this is my measured value, right, from the wattmeter. Wattmeter measure value is what? Wattmeter measure value is simply real of VL conjugate, okay, which is simply 0 degrees, so it doesn't matter much. And ICC, what is ICC? Equals to IL plus VPC, or VPC is VL itself, VL by RP. This is also vector quantity, right? So okay, all these are vector quantities only, it doesn't matter much. But still if you want to do it like this, that it will be equals to real of VL conjugate IL plus magnitude of VL whole square by RP. Okay, so this is basically the real power, right? This is basically the real power. This is if I just write this in terms of real terms, so what will this be? One of the term will be, so here I can write real of VL IL cos phi plus J VL IL sin phi, right? Sin phi plus magnitude of VL whole square divided by RP. Now obviously I will ignore the imaginary term, I will just take the real terms. So here my real term will be VL IL cos phi. What is VL IL cos phi? It is the true value, right? VL IL cos phi, it is the true value that I actually want to measure, plus an extra error. What is the extra error? That is magnitude of VL square divided by RP. So this is my measured value. So my error will be VL square by RP, which can be proven here as well, that the total power will be again P load plus IP square plus RP square. What is IP? IP is the pressure coil current and the resistor is the pressure coil resistance. So I will again here ignore the current coil current now. Okay, the error due to the current coil I will ignore. So if I ignore that, so the this will come out to be P load plus V square by RP. So V square by RP will obviously my be error. So here it will be V square by RP. That will be my error. I can write this VL as well. That will be better. So the error percentage will be VL square by RP by divided by the true value is P load into 100% in percentage terms. Okay, so these are few things that you need to understand. I have proven to you, okay, that actually this comes to error in basics, and with intuition also I have told you. I will recommend you to remember this. I generally don't tell you to remember many things, but this one I will recommend you to remember, because obviously it will take you huge time to derive all this. Just remember, when the voltage coil, how will you remember? When voltage coil is near the load, error will be due to voltage coil. So when pressure coil is near the load, PC near load, so error will be due to pressure coil. Now if my CC, that is current coil, is near the load, if CC is near the load, okay, CC is near load, error will be due to CC. Okay, so there are two cases here. So that is the thing that I wanted to say. So I hope you understood the error thing. And there is another term known as the multiplication factor. If you have ever used your wattmeter in labs, you will see there is a multiplication factor. Now what is the multiplication factor? Basically it is the voltage range into current range into the power factor. There will be a power factor setting as well, divided by the whole range of the wattmeter. Okay, so this is the term that they use if in the question this term comes out, multiplication factor. Its definition is like this. Generally they will define it, but if they don't, you will understand the definition by this thing. Okay, voltage range into current range into power factor divided by the range of the wattmeter. Okay, the voltage range and current range can be increased by use of potential and current transformers, that we will study later on. PC and current transformers, that we will study later on. Okay, so this is one question that came on GATE 2015. So we'll solve this question. The coils of a wattmeter have resistance 0.01 and 1000 ohms. Okay, now can we say which one I will use as current coil and which one I will use as pressure coil? So obviously I will choose this one as current coil and this one as pressure coil. Why? Because the high resistance one will take low amount of current, right? And the low resistance one will take high amount of current, and it will have less voltage drop. Okay, that's just intuitive. I want to measure voltage. The voltage measuring device should have high resistance, as I am connecting it in parallel with respect to the load. The inductance may be neglected. The wattmeter is shown in the figure below to measure power consumed by a load which draws 25 amperes. So IL is 25 amperes and cos phi they have given me, power factor is 0.8. The voltage across the load terminals is 30 volts. Okay, the voltage VL is 30 volts. The percentage error in the wattmeter reading. What will be the percentage error in the wattmeter reading? Here, can you tell me error will be due to which? Do you remember the name? No, I also don't remember the name. How do you remember the formula? Whichever is near the load, error will be due to that particular thing. So here I can see the pressure coil is near the load. So error will be due to pressure coil. So my wattmeter measure value is true value plus Vp whole square or VL whole square by Rp. So what is the like they are asking just the percentage error. So my percentage error will be simply something like this. Percentage error, it will be Vp or VL whole square by Rp divided by VLIL cos phi into 100. So here one VL will get cancelled. So I will be left with VL divided by Rp IL cos phi into 100 percentage. So what is my VL? VL I know it's 30. Okay, what is which one reaction I should check? That's why I mentioned specifically which one will be pressure coil and which one will be current coil. Current coil will have low resistance. Reason is simple, as it is connected in series, I don't want to have a huge voltage drop across it. Let's say this is 10 ohms, current is how much? 25 amperes. So 250 volts drop will happen if the resistance of the current coil is 10 ohms. If it is 0.01, how much voltage drop will happen? Only 0.25 volts. Okay, so it is very minimized. So I hope you understand the reason why current coil has lower resistance and pressure coil has higher resistance. So this will be 30 into 1000 into the current, 25 into the cos phi, that is 0.8 into 100. Okay, so I will just quickly compute these things. This 2 zeros will get cancelled here. Okay, this 0 will also get cancelled. So 3 by 25 into 0.8. Okay, so this will be 0.15%. So my percentage error will be simply 0.15% of error. Okay, 0.15%. So in the answer, what you will put? You will put 0.15. So I hope you understood this concept of percentage error. Let's solve another question. So this is the other question from the same topic, related topic only. The circuit in the figure is used to measure power consumed by the load, power consumed by the load. This is a unity power factor load. So UPF means what? UPF, whenever there is written UPF, right? UPF means unity power factor. And what does unity power factor means? Unity power factor means my cos phi will be simply 1. The current coil and the voltage coil wattmeter have 0.02 and 1000 ohms resistor. Just similar like this only. Just like this only. So obviously current coil has the lower resistor. So RCC has 0.02 ohms and pressure coil or the voltage coil has almost 1000 ohms of resistance. The measured power compared to the load power will be, basically they are asking me the percentage error. So this time what is connected across the load? The current coil is connected across the load. So my P measured, right? Wattmeter measured value will be what? Wattmeter measured value will be simply P actual, not P actual, sorry, P ideal or W true value plus the error. Error is what? I magnitude of IL square R CC. So I just want to have, I just have to find the error. So the error will be, percentage error will simply be IL whole square RCC divided by the true value, right? True value. So what is the true value? They have already given me the VL and IL. So VL into IL will be the true value. VL into IL into cos phi will be the true value. Here cos phi is 1, so it will be 200 into 20, and this will be 20 whole square into RCC. RCC is 0.02, and obviously we have to compute in percentage, so we have to multiply 100. So what will this become? So this will be 20. This will go away. This 20 will go away. 20. Another 10. So this will be 0.2. 0.2 means 1 by 5 or 0.2 percentage, right? 0.2 percentage, and 0.2 percentage what? The measured power will be 0.2 percentage more, right? It will be more than the true power, because obviously there is some error in the wattmeter. So it will be 0.2 percentage more. Option C will be correct. So these were a few questions that these type of question can come in wattmeter. Okay. Next, the errors in wattmeter. So they can ask question from errors in wattmeter. So there can be two types of error. We'll discuss them one by one. One is the error in the current coil. So actually in the current coil, if what happens, obviously there is the error due to the resistance of the current coil. That is one thing. Another error is due to the magnetic flux. So initially my connection is this, right? If initially my connection is simply this, that my pressure coil is connected like this. I'm just showing you the rough. Okay, so my pressure coil is directly connected across the load and not my current coil. So if pressure coil is directly connected across the loads, what is the current that will go to the current coil? So current that will flow to the current coil is IPC, just hold on, IPC plus IL actually, because whatever you observe here, right? Why? Because this IPC plus IL current, one of the current will get divided into IPC and the other current will flow to go to IL, because IL wants that its own current, right? IL is that current is fixed, so extra current demanded by the voltmeter obviously will have to come to current coil. So if that extra current is coming through current coil, so due to that there will be some magnetic flux, because I know what is my flux formula. Flux psi equals to Li, correct? As my current increases, psi will also increase. Okay, and there is another like MMF formula is there, that N times I gives us the magnetic force, right? So that formula also you can use. So net your flux is increasing, but that flux increase is unwanted because that is error, right? That is not the actual load current due to which the flux is getting generated. So obviously flux has increased. Now if flux has increased, what will happen? So here I can say that extra flux, right, will actually cause some error. I don't want that error to happen. So what I will do, I will connect like this from the point through which I am taking the current. I will have a coil which will be in the opposite sense to the actual current coil, which will actually oppose the flux. So that's why my current coil was producing NCC, that is the number of turns in the current coil, into IL plus IPC. I will connect a coil that will have turns known as the coil name will be compensating coil, and it will have number of turns equals to N comp, and the current will be multiplied, that is IPC current will be multiplied. Okay, so now this N comp into IPC will be in opposite fashion, opposite sense. So if this is in opposite sense, then what I can say is basically this will totally cancel out this extra component. I only want NCC into IL, I don't want NCC into IPC. So this will cancel out the extra component. So net EMF will come out to be NCC into IL. So from this particular equation I can say that my number of turns in the compensating coil should be same as the number of turns in the current coil, and if I place it in the opposite sense, it will totally cancel out the extra EMF generated by the current coil, due to which I will get some error, and I don't want that, right? So that is what is written. To correct that extra MMF in turn which will create the extra torque, I connect a compensating coil which take like through which the current flows is IPC, which is in the opposite sense to the actual coil. Okay, so that it cancels out the net MMF. So this is a bit of theoretical thing that you should know, and remember, out of this equation my number of turns in the current coil and number of turns in the compensating coil comes out to be the same to cancel out this extra MMF. Okay, I hope you know the equation for MMF. Now let's come to another type of error. This is due to the current coil. Now what is the error in the pressure coil? So as you might have noticed by now, the pressure coil has some inductance. Okay, so and its inductance is actually considerable. Current coil also has some inductance, but its inductance is not that considerable, but it has good amount of inductance. Okay, so what happens is this is not totally like this should be very highly resistive, this pressure coil, but due to the inductance and due to frequency components I will get a bit of error, which we will compute right now. So first of all, what is my impedance of the pressure coil? Impedance of the pressure coil will be the resistance component plus the impedance plus the inductance component. So resistance is RS plus RP. RS plus RP is my resistance, and what is the inductance? Inductance, it is plus j omega LP. Inductance is plus j omega LP. Okay, now I approximate that my like RP is the resistance of the coil, which is very low compared to this RS. RS I connect externally, which is a very high resistance, which is also known as the current limiting resistance, because due to this obviously I am connecting a resistor parallel to the load, obviously I would not want the resistor to be low value, else most of the current will flow through this low value resistance and none of the current will go to the load, which I definitely don't want. I don't want to have a loading effect. I want to just measure the voltage. That's my only purpose. So that's why this RS is known as the current limiting resistance. RP is the resistance of the pressure coil, and LP is the inductance of the pressure coil. And if you just ignore this RP, I can safely say that my impedance triangle will be something like this. This is the magnitude of ZP and RS omega LP phi. Okay, so this impedance triangle already you know. Now what will be the error actually? So the error will be here. So initially, if for ideal case, okay, my VL, the voltage that I will measure across the load, and the current flowing through the pressure coil, right, assumption is there is no inductive effect, so they will be in the same phase. Correct. If there is no inductive effect, they are in the same phase. So the angle between IPC and ICC, that actually decides the cause of that angle we take, right? Because the angle between these two, we take the cause of that, and that comes in the final result. So the angle between IPC and ICC will be simply phi, because IPC is measuring what? IPC is what? In the ideal case, IPC is simply V by R, right? V by RS. Because what we are doing, we are just connecting this RS resistance directly parallel to the resistor, directly parallel to the load. So whatever the voltage across the load and divided by the resistor, that will give me the current. This is VL. Okay, that will give me the IPC current. And through the help of IPC, I generate a magnetic field. So this IPC is proportional to the voltage, and I know my IPC generates a magnetic field. So my magnetic field is proportional to the voltage, and this is VL. Okay, and ICC is equals to what? It's simply equals to IL. It is simply the same current that is flowing. So it will, in the phasor diagram, ICC will be here, IPC will be here, and the wattmeter, what it measures, it actually measures the angle between IPC and ICC, current through the pressure coil and current through the current coil. Okay, all this is fine. So here I can simply replace my ideal torque equation. So this will be IPC, that is V by RS, into ICC, that is IL, into cos of angle between ICC and IPC, into dm by d theta. Okay, this is my actual torque equation that I will get. Okay, but if my inductance is considerably higher, I cannot ignore the inductance. So then there will come, this angle is not phi actually. This angle is simply a beta. This is just an angle, power factor angle for this particular impedance triangle. This is not phi, this is beta. Okay. So now what will happen? The voltage in the pressure coil, this is the voltage in the pressure coil that it will measure, and the current will actually lag somewhat, right? They will have some angle, they will have some phase displacement, because my inductance this time is non-zero. Due to this inductance, whatever current flows, this current and the voltage across the pressure coil, both of them will have some phase difference. It will not be zero anymore. Due to that, what happens, my IPC is here and my ICC will still remain at the same place, right? Its power factor angle is fixed, it is phi. It is phi from the load voltage, because I am connected across the load. So this angle is phi, this angle is beta, but what does the torque equation say? Torque equation measures the cause of angle between the IPC and ICC. So what is the angle between IPC and ICC? It is simply phi minus beta. Correct, because this mass angle is beta and this mass angle is phi, so it is phi minus beta. So my torque equation will now become, what is the current through the pressure coil? It is V by magnitude of ZP, right? It is not anymore V by RS, because I cannot ignore the omega times LP. So to write V by magnitude of ZP into IL, this will remain same, that is the current coil current, and into cos of angle between ICC and, now what is the angle between ICC and IPC? It is simply phi minus beta. So it is phi minus beta. So this will be cos of phi minus beta into dm by d theta. Still I am not able to compare it to my previous expression. So what I do, I simply write this ZP in terms of something else. So from here, can you tell me what you can write ZP and RS? So this ratio RS over magnitude of ZP will be simply cos of beta. Okay, So this will be simply cos of beta. So what I can do is I can write Zp is equals to Rs by cos beta. So I will replace my Zp in terms of Rs. Why? I just want to have a good comparison between the ideal torque and the actual torque what I'm getting. So if I replace Zp with Rs divided by cos beta, so cos beta will go to the numerator and Rs will stay as the denominator. It will become V into IL cos beta cos phi minus beta divided by Rs into dm by d theta. Okay. So now if I want to find out the correction, because how much do I need to correct? Because I need to correct some amount because I am getting some error. What is the correction? So correction factor, it's also known as correction factor. Okay, as written here, it is equals to true value divided by P measure value. So if I do what is P true value, it will be the ideal torque that I want divided by the actual measured torque that I am getting. So everything else will cancel out except this cos phi and this cos beta and cos phi minus beta. Okay, so after this we do a bit of simplification just for the sake of it. Okay, just to get to some formula, but it's not that important, but this concept is important. Just remember the phase diagram, remember the power triangle, how am I converting, what is the actual torque equation that I'm getting, what is the ideal torque equation I'm getting. That's it. If you don't want to remember the formula which I will derive right now, it's totally fine. Just remember the step. Okay, that's it. So what I can say is I can further break this down. This is cos phi minus beta, right? So I can further break this down. So I can write my correction factor will be simply this is cos phi divided by cos beta. Cos of this is cos A minus cos B. So this will be cos A cos B plus sin A sin B. So cos phi cos beta plus sin phi sin beta. Okay. So now what you can do is if you just simply take in common this cos square beta thing common. Okay, if I just take cos beta common, so this will come out to be cos beta cos phi cos square beta into cos beta plus I can divide by cos phi as well on both sides. If I divide by cos phi on both sides, right, both numerator and denominator, what I will get? So just write this in the bottom only, that would be better. I have just divided cos phi on both numerator and denominator. So here what will happen? Or you can take the cos phi and cos beta common. Both cos phi and cos beta if I take common, this will be 1. Okay. If I take cos phi cos beta common, and this will be tan phi tan beta. So after this what I can say is that I can do a bit of approximation. What type of approximation I can do? I can say that my cos beta will almost be equals to 1. Okay, how I can say that? Your beta is what? Beta is the angle between this impedance triangle angle, and I know beta will be very low value because I want to idealize it. So my RS will be generally very high, so beta will be very low. Okay, beta will be very low. So my cos square beta I can approximate to be it equals to 1. Okay, so from here what I can say is, how can you approximate? You just put cos cos square 0.01 or cos square 1 degree. It will be almost equals to 1. It will be almost nearby 1. Okay, so then this formula correction factor will come out to be what was correction factor? Correction factor was simply true value divided by measured value. Okay, it is 1 by 1 plus tan phi tan beta. Okay, so from here we can get an expression for like how much error I am getting. So from what is the error expression? So what is my measured value? Basically my measured value from here I can directly say it will be true value plus p true value into, like, to get this neat expression I had to do all those juggling, tan phi tan beta. So I can say my PTV by PL, not this, my error, right? Percentage error, if you want to say, it is equals to PMV minus PTV divided by PTV. So it comes out to be simply tan phi tan beta into 100. So this neat expression I get. So that's why we had to do all those simplification. Okay, it's okay if you don't remember, it's good if you can remember, that is also fine. Okay, either way, just like one thing you should remember is the concept, how am I deriving it, that is the important part. This will be simply percentage error. So like this is the absolute error and that was the percentage error, simply multiplied by it. Okay, so now there can be two things. Okay, if my if my power factor is lagging, that means my phi will be greater than 0, and if phi is greater than 0, that means my tan phi will also be positive, correct? So if tan phi is positive, this term is constant, right? Then my PM minus PTV will be positive, that means my PMV is greater than PTV. Okay, so if my power factor is leading, then what will happen? Then things will change. Then my phi is 0 and hence my tan phi will also be negative. Now if tan phi is negative, that means my measured value minus true value is less than 0. It is negative. So my measured value will actually be lower than the true value. So I will underestimate. So this can also happen, right? It depends on the power factor angle. This can also happen. So just be careful about it. If in the question, this can be also a possibility that my measured value of power factor can be lower than the true value. Okay. Previously, those were not the case. Generally, my measured value was always higher. Okay. Here it was always higher because this is a unity power factor load. But if they would have talked about the inductance of the pressure coil as well, then I had to take care of those things. It can be lower as well. Okay, just be careful. So that was it about the error due to inductance in pressure coil. Here I've just given you a graph with the variation of power factor. So if my phi is positive, this subtraction, the measured value minus true value will be greater than 0. If my phi is less than 0, then obviously my measured value will be lower than the true value. Okay, so the effect of low power factor on the error in wattmeter reading is significant. At low power factors, the error due to the inductance of the potential coil increases, leading to higher measurement inaccuracies. So at low power factor, I can observe that error is huge, right? This error is huge. This is actually playing a significant role. So I cannot just simply use these type of wattmeter to measure low power factor load. For like normal power factor loads, power factor greater than 0.5, that is fine. But for other types of loads, right, which are low power factor, I cannot simply use this instrument. This happens because the phase angle between the voltage and current increases and the inductance of the potential coil introduces more phase error. Why? Because as the angle increases, right? As the angle increases, what will happen? This will more dominate. The inductance will dominate more because it will have more lagging component of current. Okay, so as this phi, like what will happen? The angle will reduce. No, the angle will increase. If the angle increases, the power factor will be worsened, and if the power factor is worsened, it will like make it more unusable, right? More error prone, because if this phi increases, this phi minus beta will increase. So as the phi minus beta increases, basically your tan phi will increase and the percentage error will also increase. Okay, so that's why we don't want that. So in ordinary dynamometer type wattmeters, this error becomes more pronounced at lower power factor, making them less accurate under these conditions. So we actually don't use these type of wattmeters for low power factor measurements. We use this type of wattmeters. A low power factor wattmeter is designed to provide accurate measurements when the power factor is low. In such conditions, the deflecting torque is reduced due to low power factor, making it difficult to measure power accurately. What will happen is that as the phi will increase, right? As the phi will increase, what will happen? This cos phi will reduce because it is inversely proportional to the torque developed will reduce. And if the torque developed is reduced, it actually reduces the accuracy of the wattmeter. The wattmeter is not that accurate anymore. So to measure low power factor, what do we do? So to increase the deflecting torque at low power factors, one approach is to reduce the series resistance, but this increases the phase angle error. So if I reduce the series resistance, what will happen due to that? I know, but here if I reduce my series resistance, the current will increase, right? Current through the pressure coil will increase because IPC was equals to V upon magnitude of ZPC. Correct. So ZPC is a combination of RS and the inductance. So obviously, if my resistance reduces, current will increase. See, current increases, the magnetomotive force will increase, and the flux will also increase, right? So torque develop will also increase. But in doing so, what happens? I add in more error, right? As my RS reduces, the more error I get. Okay, why? Because this beta angle will keep on increasing because RS has been reduced, the real component has been reduced, and imaginary component is fixed. So obviously beta will keep on increasing. So next, what will happen is that that's why it will introduce more phase angle errors. To mitigate this, we have to add another component, a compensating capacitor that is placed across the series resistor to cancel out the effect of inductance. To cancel out the effect of inductance, we had to place a compensating capacitor as well. So it is not that simple. We need to do more calibration and all those things as well. But just to get the brief idea, I had to add a capacitor, and inductance was already there. And with the help of these things and reducing the RS, I am able to make a low power factor wattmeter. It's quite different than an actual wattmeter, which generally measures power at normal power factor. So low power factor wattmeter, I need to have a separate instrument. To measure low power factor loads, I need to have a separate instrument known as low power factor wattmeter to reduce the errors, because at low power factor these type of errors can happen. Okay, so let's do a few basic question on this, and after this we'll wrap up today's lecture, and in the next lecture we'll start with the new topic, that is measurement of power in three-phase systems. Now here let's do this question. If the reactance of the pressure coil in a wattmeter is 1% of its resistance, so my reactance of pressure coil is 1% of its resistance, so XLP is RS by 100. Okay, now calculate the percentage error caused by this at power factors 0.8 and 0.5. So we'll observe the errors that I will get, right? So either you can solve with the basics, or as I have derived the formulas right now, I can directly solve. So this is XL is equals to RS by 100. So I can write my XLP by RS equals to 1 by 100. That is equals to tan phi. Okay, not tan phi, sorry, tan beta. This is my tan beta, correct? What about my phi? So already they have given me cos phi for two values. So I will take for the first case what cos phi they have given me 0.8. Okay, they haven't told me lagging or leading. I don't need that as well. I do need that actually. I will assume here. We'll tell assume lagging loads, else the error will be just negative. Okay, assume so cos phi will be 0.8. So cos phi 0.8, and what will be my phi will be it is 4 by 5, right? So it will be 37.13. okay, so if you remember, like few values you should remember, it was 37, no, not 37, 36.87, something like that, right? And it was 53.13. yeah. So phi is this value. So what is tan phi? Basically tan phi will be simply 3 by 4. okay, this will be tan phi. So few values I remember. So now what you can do, you can directly write the percentage error, because they are just asking you the percentage error. I have derived this formula. It's okay, totally fine to not use this formula, just use the basics, these things. okay, you can use derive. okay, these things you can remember, and from there you can derive, or you can directly use the formula. okay, as I've just derived the formula, I will use it. okay, in the examination hall, few things you should know, you can put this in your short notes just to keep in mind, and this is easier to remember, right? It's not difficult, that not that difficult to remember. So this thing you can remember. So it will be tan phi into tan beta into 100. So it will simply become 0.75 percentage. okay, not that huge. 0.75 percentage is still pretty low. okay, not that huge. Now let's solve it for the second case. If my cos phi is very low, right? They have told me cos phi is simply 0.5. okay, I will solve it for a third case as well. If my cos phi is 0.2, then what will happen? Then from here I can say, what will be my tan phi? It is half, right? So that is phi equals to 60. So tan phi will be simply root 3. So my error, percentage error 2, this is percentage error 1. This will be root 3 into 1 percentage, basically, because it is 1 by 100 into 100 percentage. So it will be 1.73 percentage. Now let's say my power factor is more lower. okay, let's say it is 0.2 here and it was 0.5. okay, so this I can say cos phi here is 0.2. so for this I don't actually remember what is the angle, so I have to find out the angle actually. So we'll quickly compute the angle. Just hold on 1 second. It will be almost 4.5. okay, or 4.88. so tan phi will be 4.88. so my error will be what? Percentage error 3. Now it is increasing huge, right? It is going to 4.88 percentage. okay, so I can observe that my error has went up 5 times. So as my power factor reduces, it reduced by like 1/3 or something like that. The error increased hugely. So obviously for lower power factors, this will impact heavily. So I have to use a separate device to properly measure the power for low power factor devices. So that's it basically for today's lecture, and in the next lecture we'll start with power measurement for 3-phase systems using 2 Wattmeter method. So that is the very important topic, and that is a very conceptual topic as well, and coefficients come from the topic, so it's a very important topic. So we'll start with that topic in the next lecture. Until then, happy learning. Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be starting the lecture 3B of our power measurement, right? Electrodynamometer type wattmeters. So in this lecture we'll learn about 3-phase power measurement with 2 wattmeter methods. So obviously to understand this, you need to understand how does my 3-phase system works. So there is a lecture on the power electronics course, so I will try to link that at the prerequisites, or if you have my power electronics course, you can go and watch that, or it is present as a marathon format as well, the 3-phase rectifiers marathon. Just search 3-phase rectifier marathon PrepFusion. Okay, and then in the just a starting, I have explained what does 3-phase systems are, how do they work. Okay, basis of 3-phase. So I will not go too much in depth here. Basis of 3-phase. I will just explain a brief. If you know, then you can continue. If you don't know, you can go and watch those videos and then start here. Okay, right? Because to understand measurement of 3-phase systems, measurement of power of 3-phase systems, obviously first you have to understand the basics of 3-phase systems. Okay, what are the parameters there? So basically in 3-phase, right, there are 3 phases and each phase is 120 degrees apart from each other. So if I have a red phase, it is sinusoidal. So the other next phase, right, that is a yellow phase, it will be 120 degrees lagging. Okay, then the next phase will be again 120 degrees lagging. Okay, so each phase will be 120 degrees phase apart. So in case of star network, so we are talking about star network. So for a star network, what happens is I can assume the voltage as a reference. So star network looks something like this. If I have some picture, yeah, this is a star network and this is a delta connection, right? In star network, what happens, like the line voltage and phase voltage will be different, but the currents will be same. But in delta, it's just the opposite. Here the line and phase voltages will be same, but the currents will differ. Line current and phase current will differ. Okay, so just a few basic things that you should know. So here, if I assume my red phase as the reference, then my yellow phase will lag by 120 degrees. That's why there is minus 120 here. My blue phase will lag another extra 120 degrees. So that's why there will be minus 240. And minus 240, I can write it in terms of other angle as well. That is, if I add 360 or subtract 360, overall the format doesn't change, right? So there is minus 240. I will add 360. I will get plus 120. So my blue phase voltage will be VMP sine omega t plus 120. Okay, so these are the basic things that you should know, like what are the phasors, how are they defined, and how each of them lag. Now my current, by default we'll assume it as a lagging load. So if my current will lag from the this voltage, right, as it is a symmetrical system, and generally we will discuss only for balanced 3-phase system. So in balanced 3-phase system, all the loads in the 3-phase are same. Okay, so that is for what we will do the analysis. So in case of balanced 3-phase system, so if my IR is lagging by 5, then my IB will also lag by 5 of its own phase voltage, that is VB. Okay, and same for IY as well, and each of these currents will also be phase apart by 120 degrees. Okay, that is also another thing that you need to keep in mind. And what will be your line voltage, that is VRY. VRY will be simply the subtraction of the phase voltage here, VRN minus the VYN. And if you do this subtraction, a very good thing will come out. So this what will come out, you can do the simple phasor subtraction. So here, this is my VR and this is my minus VY. If I add these two, I will be lying somewhere around here. So what you will get is this overall angle will be 60, and this will totally come out as an angle bisector. So your line angle, like line voltage, will come out somewhere here. The VRY will come out here, and this will be leading the red phase by 30 degrees. So to lead the red phase by 30 degrees, so it's a very, very important portion for you to understand. That my VRY is this, and how you can write your VRY? You can write your VRY I will just show you the format how you can write the line voltages. Right? So here I have shown you the format how you can write the line voltages. First of all, like you can do the simple phasor calculation. You can do VR minus VY, and you will get sine omega t minus sine of omega t minus 120. And from the trigonometric formulas, you can do your manipulations. You will get this value. And in my lecture as well, there I have explained how you get to this value. Okay, here we don't have time, so I will not explain. So you get root 3 VMP. VMP is a phase peak voltage into sine omega t plus 30. So as I told, right, it will be leading by 30 degrees. So it will have a phase lead of 30 degrees. So line voltage will lead the phase voltage by 30 degrees for a star connection, for a balanced star connection. Okay. So your VRY will be this, VYB will be this, VBR will be this. Okay. They will be also 120 degree phase shifted. And line current and phase current are same. And your VML is basically root 3 times the VMP. So these are a few basic things that you should know. Okay, but why am I giving more emphasis? I will just come to that later on. But let's first understand how do I compute the power in a 3-phase system. What will be it, as it is a balanced system, right? I can simply find out the power in single phase and multiply it by 3. I will get the 3-phase power. So what is V phase into I phase conjugate? So it will be V phase RMS into I phase RMS into cos phi, right? So V phase RMS, I phase RMS, I can replace with peak values and it is V phase RMS is Vm by root 2, I phase RMS will be Im by root 2. Okay, so it will be Vm Im by 2, 3 by 2 cos phi. Okay, equals to root 3. Like this term, right? I can take this Vmp Imp. I can convert this into what? I can convert this particular thing into root 3 VLL into ILL RMS as well. So how it works is, this one is RMS only. So in this format also you can understand. In this format, these two are RMS, right? So how do I convert? How do I get to line RMS? Simply I have to multiply root 3. So what I will do is I will VML IML. So VML is root 3 VMP, right? So in case of star connection, I know I phase is equals to I line. So this I can directly convert. Here I phase is equals to I line. So I can directly convert this into line. And this is what? This is I phase RMS. I want to get to I line RMS. How do I do it? I divide by root 3. So it will be V line RMS divided by root 3. So a 3 is already there. So overall this will be root 3. So power, 3 phase power can have many formats. This is one of the formats. This is one of the formats. This is one of the formats. And this is also another format, right? So that's how you get your 3 phase power. We are not like the supply power factor. You can simply divide with respect to the apparent power, and you will get your supply power factor. We are not concerned. This was mainly for the power electronics. So I have explained you the power formulae. Okay, I have explained you how am I getting line voltages, all the things. This is simple derivation, and in that lecture I have explained. So I will link that lecture. Okay, and you can go and watch that. So what does Blondel's theorem say? So Blondel's theorem states that in an n-phase unbalanced or balanced system, the number of wattmeters required is n-1 to measure the total power of the system. So to measure the total power of the system, we require only n-1 number of wattmeters if it is an n-phase system, regardless if it is balanced load or unbalanced load, right? So that is what Blondel's theorem states us. You can read all these things, like it is not important. The main crux is he said, like it's like a law that to measure the power of n-phase system, if it's balanced or unbalanced, you only need n-1 wattmeter. So obviously you will need one less wattmeter. So why will you use 3 wattmeters? So let's say your load is unbalanced, right? Phase 1 has some power 500, phase 2 has some power 600, phase 3 has some power 700 watts in watts, right? So you will say, sir, I have to put wattmeter for phase 1, 2 and 3 to measure the power separately and then add that 3 up. But like Blondel said that we don't need to have 3 wattmeters, 2 wattmeters will do, but connections you need to take care. How do you do the connections? That you need to take care, and you will be sorted. Okay, so obviously we are saving our costs, so we will obviously learn this. So now let's actually come to the derivation. So if I have connected my wattmeters as such, then I will be able to measure 3 phase power with only 2 wattmeters. I will derive that, don't worry. So how do you remember the connection for a 3 phase like 2 wattmeter method? How do you remember the connection? You need to remember that in the 2 phases, 2 current coils will be connected. In the other phase, the common point of the potential coils will be present. So this potential point will also come to the phase B. This potential coil will also come to the phase B. So one of the point will come here, and the other point will be connected to their respective current coils. That's how you remember. 2 current coils, 2 phases. Done. The phase that is left out, in that phase, the common point of the potential coils will connect, and the other point of the potential coil will basically connect on the other side. That's basically it. Okay, that's basically it. So that's how you remember, because many times in the examination the connection diagram will be given. You have to identify whether it is a 2 wattmeter connection or it is a non-standard connection. That also you have to identify. So that's very important. How do you remember that? Okay, so now let's come to the derivation. So what will be my reading of my wattmeter 1? Wattmeter 1 will obviously read the line voltage, right? It is connected across R and B, so it will read VRB, and it will read the current is IR, and the angle, cos of the angle between VRB and IR. That's a simple thing that my wattmeter W1 will read. What will be my W2 will read? W2 will read VYB IY into cos of angle between VYB and IY. Okay, that is what my W2 will read. Now what you can do is identify this angle. How do you identify this angle? So here I have like the phasor is already here, right? You can from here you can directly say, or I have already written the expressions. From here also you can identify the angles. So what is my VYB? VYB, if I see here, what is my let's do for the VRB first. So VRB is exactly this but flipped, because it is 180-degree phase shift. So BR is this, VRB will be just the opposite, right? So I have to subtract or add 180, then I will get my VRB. So I will subtract 180 with it angle, so it will be omega t. VRB angle will be omega t minus 30. Great. Now what is my IR angle? IR is lagging by phi with respect to my reference. Okay, IR will lag by phi with respect to my reference, so its angle will be minus of phi. Okay, so and what will be the angle that I will get? I will get this angle minus this angle. Sorry, omega t is also there, right? Omega t minus phi. Okay, so I will get this angle minus this angle. If I do this angle subtraction, the angle that will get is minus 30 plus phi. But this minus 30 doesn't look good, right? So what I will do, because cos of minus theta is equals to cos theta, so I can take the negative common. This will become 30 minus phi. Okay, so that is what I do, because I know this is my theta. Basically, let's assume this as theta, and cos of minus theta will be same as cos theta. That's why this minus doesn't look good. That's why I have taken common. So this VRB will be V line. IR is also V line, because in star I line and phase current are same. Cos of 30 minus phi. Now what about VYB? YB has an angle of omega t minus 90. This has an angle of omega t minus 90. IY has an angle. IY is here, right? It will lag my VY phase, right? It will lag my VY phase basically. So it will lag by 30 degrees, right? So it will be minus 120 minus phi, because IY will simply lag VY. So it will be minus 120 minus phi. Omega t minus 120 minus phi. So this will be omega t minus 120 minus phi. Now if I subtract these two, I will get 30 plus phi, right? The angle will be 30 plus phi. So again, this will become VLIL will be same, but this will become cos of 30 plus phi. I will also show you that version where if these are not equal, then also you will get the same power measurement only. So you get these two values. Now your active power will this point is the very, very important portion. Just remember this. You have to remember these two, that your two wattmeters will measure these two things. And from here onwards, everything is important. Your active power will be just the algebraic sum of the two wattmeters. It will be the algebraic sum of the measurement of the two wattmeters. W1 plus W2. So what is W1 plus W2? It is VLIL cos of 30 degrees minus of phi plus VLIL cos of 30 degree plus phi. Okay, so that is the case. And like I can do simple trigonometric operations. It is cos A plus cos B, right? Cos A cos B. Cos A B will give you what? Cos A cos B is also like this is, I think, 2 cos A cos B. This is the expression for 2 cos A cos B, right? So this will be 2 VLIL cos A, that is 30 degrees, like B is phi, simply, right? Like this is cos A minus B, cos A plus B, cos A minus B, cos A plus B. What is cos A minus B? Cos A minus B is cos A cos B minus plus sin sin B. It is cos A cos B plus sin sin B. And what is cos A plus B? Cos A cos B minus sin sin B. So sin sin B gets cancelled. Only I am left with 2 times cos A cos B. So that is what it is, cos A and cos B. Okay, this is 2 VLIL cos phi. So this will be equals to, now what is cos 30? Cos 30 is root 3 by 2. So this will come out to be root 3 VLIL Now let's come to the reactive power measurement. So how do I calculate the reactive power? So reactive power will be W will be equals to W1 minus W2. that will be equals to what? Now this again is VLIL. I can take common. This will be cos 30 minus 5 minus cos of 30 plus 5. Correct? So now obviously it is cos A minus B minus cos A plus B. This time the cos component will get cancelled. Sine component will be staying. So it will become 2 VLIL sine A sine B. That is sine 5. And what is sine 30 is half. So it will be VLIL sine 5. So with the help of two wattmeter method, because what is VLIL sine 5, right? What is VLIL sine 5? It is simply the reactive power, right? VLIL sine 5 is reactive power, but it is the reactive power of not the three phases, because my reactive power formula, if you remember, my Q is supposed to be root 3 VLIL sine 5. But here I am getting only VLIL sine 5. So I just need to multiply here root 3. Root 3, this will be actually, this will be my Q. This will not be Q actually, this will be like W dash, and this will be W, this is W double dash, this is W dash. Root 3 into W dash, basically W1 minus W2. And this is, you can write this as P, power, active power, correct? So you got a reactive power, you got a active power. There is other way as well. You can go through website and there they have shown the proof with the help of other method. But this is enough. This much proof is enough. So you get the reactive and active power, and this is valid for both unbalanced and balanced load. It doesn't matter. Okay. Now let's calculate the power factor. So I have found out the reactive power. I have found out the active power. With this, I can simply find out the power factor. How will I find out the power factor? If I divide this Q by P, I will get tan of that angle. Tan of phi. So what is my tan of phi? Tan of phi is Q divided by P. What is Q? Q is simply root 3 times W1 minus W2. P is W1 plus W2. So you get this good formula. So from here I can directly write my phi. Phi will be tan inverse of root 3 W1 and minus W2 divided by W1 plus W2. Now you need to remember where did the W1 was connected and where was the W2 was connected. Once we solve questions, there we'll understand. But it is very, very important to understand, because W1 and W2, both of these can come as a negative value as well. Okay, how will it come negative? All those things I will get to. Don't worry about that. Okay, so from here, you can see you have got the angle, power factor angle. So you can easily find out the power factor. It will be cos phi. Okay, if you already don't know the apparent power, then without knowing that you can directly compute, right, with just two wattmeter method. Okay, just the two readings, W1 reading and W2 reading, you will be able to identify these many parameters. Also, if my W1 is greater than W2, then my load is lagging. Why? My phi becomes positive, and my initial assumption was it is lagging. So it is positive, that means my assumption was correct, that means the load is lagging. If my W2 is greater than W1, that means my load is leading. Why? Because the angle will come out to be negative, and if the angle is negative, that means it is upper half of the IR of the VR, not the lower half. So obviously my initial assumption was wrong. That's why the load will be leading. Okay, so that is the important portion. Like delta connected load, you can derive the expression for delta connected load as well. You will get the same answer. Few key points that I want to mention is, like as I was explaining there previously, at times the reading of a wattmeter may be negative, but since wattmeter generally cannot display negative values, how can wattmeter display negative values? We reverse the connection of the potential coil to obtain the positive readings. So because if the negative signs come, right, the wattmeter pointer will go towards leftward. If you have ever done two wattmeter method experiment in your college lab, you will see, if it is like, if you have connected if you did the connections other way around, what will happen? The wattmeter pointer will go leftwards. Okay, and how it will go leftwards? It tries to go leftwards before 0, right? It can't go before 0. So, but just by seeing that particular condition, you will understand that, okay, I have made the connections wrong. I have to flip the connections. So then we reverse the connections. But in the equation, however, during the calculations, the value should be considered as negative. Okay, even though I did the connections, but value should be considered as negative. So as mentioned here, right, as W1 is this. W1 was connected between the red phase and the blue phase, right? RYB rate first phase and the last phase. Okay, so if in the first phase and the last phase this W1 reads a negative value, that means the wattmeter pointer is going leftwards. That means what is happening is that can happen. That depends on the load condition. That depends on the power factor angle. Okay, and what you'll do, you'll just flip this connection. This R point will come here and this B point will go there, okay, of the potential coil. Now you'll get a positive reading, but actually it was supposed to give you a negative reading, but wattmeter cannot measure a negative reading. But in the calculation you write minus 50. Wattmeter, after flipping the connections, wattmeter read 50 watts. That's fine, but in the calculation you write minus 50 because it was supposed to give you negative number, but wattmeter cannot measure negative numbers. So we flipped it, we measured the positive number, and we just in doing our calculations we wrote that it is minus 50. That's the thing that I wanted to say here, and that is the thing that they have explained. So if I vary my power factor, the wattmeter readings will also change, and from here we can observe that how am I getting negative values. So if phi is 0, then cos phi power factor will be unity power factor 1. Okay, so my wattmeter W1, its reading was VLIL 30 minus 5, correct? 30 minus 5. So phi is 0, right? It will be simply VLIL cos 30 is root 3 by 2 of VL, and W2 will also be same. So if it is unity power factor, both the wattmeters will read the same measurement. Okay, same measurement, root 3 by 2 VLIL, and the overall sum will be again root 3 VLIL. W1 will be equal to W2. Now if my power factor is 30 degrees, just hold on. Yeah, sorry, I had to pause because I had a bit of sneezing, coughing. So as I was explaining that in the first case everything is fine. In the second case, if my phi is 30 degrees, my cos phi will be cos 30 root 3 by 2. What will be W1? This will be cos of 30 minus phi, right? So phi is 30, so this will be cos of 0. So W1 will be VL into IL. That's it. That's my W1. What about W2? W2 will be VL into IL cos 30 plus phi. So phi is 30, it will be cos 60. Cos 60 is half. So it will be VL IL by 2. So what will be my active power? It will be W1 plus W2, that is 3 by 2 VL IL. Is this correct? So my overall power is supposed to be root 3 VL IL cos phi. That is my active power, right? So root 3 into VL IL into cos phi is root 3 by 2. So yes, it comes out to be like root 3 into root 3 by 2 is 3 by 2, and VL IL is constant, it is there. So yeah, it is giving me the correct results. So one important observation we see is W1 is reading twice of W2. So you have to take care of the ranges as well. So if your W1 has a maximum capacity of, let's say, 100 watts, and your W2 is reading 200 watts, right? Or W2 is reading also 100 watts. You cannot simply use like that wattmeter as W1, right? Because it will read 200 watts, okay, and it's out of range of the maximum value. So you have to think about that. So that's why this 2 wattmeter method is, yes, it's elegant. We can use only 2 simple wattmeters and derive all the parameters, but you have to be careful while measuring as well where you're putting the value, because the measurements vary with respect to the phi. Now 60 degree, it will be 0.5, and this you can observe the last one that I am most interested when my power factor is totally lagging. So if my it is totally lagging, so phi is 90, so I don't have any real component, cos phi will be 0. So my W1 reads VLIL by 2. Okay, W1 reads VLIL by 2 and W2 reads minus VLIL by 2. It reads minus, but can a wattmeter read negative? No, it cannot read negative. What will happen? Your pointer will go towards leftward. Your pointer will flip leftward. So you will see that, and then what will do? You will just interchange the potential connections. Interchange the potential connections. Once you interchange, your pointer will then again go on the right hand side, and it will show a reading, let's say 50 watts. But internally, you know that you have to flip the connections to get it to give positive results. So obviously, actually it is negative 50. So you write in the reading minus 50, which can be seen from this formula as well. If I put here 30 plus 90, it is cos 120. Obviously, cos anything greater than 90, cos of anything greater than 90 gives me some negative value. So it will be minus VL IL by 2. Okay. So what about P3 phase? P3 phase will again be sum of those two, and it is 0. And it is correct, right? Because why? It is a purely lagging load or inductive load. Okay. It can be negative as well. If phi is negative, it will be leading. As here we are only analyzing for positive loads, it is lagging. So always my W1 will be greater than W2. That will be always the case. You can take for minus phi. For negative values of phi, you will see your W1 will always be less than W2. Okay, that is the one observation you will see. So you will see that your W2 is exactly the negative of W1. These are few observations. Okay, so just one thing, that whenever the power factor is less than 0.5, one of the wattmeter will read negative value. So you have to be careful. You have to be careful if the power factor is less than 0.5. Okay, so these are the few observations that I wanted to go take away with. Now we will solve few questions. Let's do this first question. So I will not use that formula. Okay, I can use my simple own formula as well to analyze the things. Okay, I can use my own formula. So we'll see that. So the line to line input voltage to the 3-phase 50 Hz AC circuit shown in the figure is 100 RMS. Okay, so line to line RMS is 100 volts. Line to line RMS is 100 volts. Okay, assuming that the phase sequence is RYB. Okay, it is RYB. The wattmeter would read what? So what would the wattmeter read? Now remember, they have not given you the standard connection, right? So what we derive for B common point, but here it is not common. So it's okay. You don't need to mug up the total connections. But what you need to mug up is understand that yes, this is a 3 wattmeter connection, 2 wattmeter method connection. Why? Because there are 2 phases which are calculating the current, and one of the phases totally common. Okay, one of the phases totally common. So that is the point that you should understand. So there are 2 wattmeters. What would each wattmeter read? So this is a 2 wattmeter method connection. Okay, so this is a standard 2 wattmeter method connection. I know, because one of the point is common and the other 2 points are simply other 2 phases. Okay, so either you can use the phasor method or you don't need to use the phasor method. Okay, either way works. So first I will do it with method 1. Just use the formula. What is the formula? Method 1. One of the wattmeters will read VLILRMS into cos 30 minus 5. If you are able to remember this formula, that's good. And I will recommend you also to remember this formula, but we will solve it without formula as well. What will be this? This will be VLRMS, I know. And what is ILRMS? ILRMS will be simply VLRMS divided by IL, right? VLRMS divided by ZL. Magnitude of Z is 5. So it will be 5, like 100 divided by 5 into cos of 30. And what is 5? 5 is 60. 5 simply 60. So it will be 60. So you will get your value. This will be cos of minus 30. Cos of minus 30 is simply root 3 by 2. Correct. So it will be root 3 by 2. So if it is root 3 by 2, I will get my value as this, right? It will be root 3 by 2 into 100, right? Yeah, cos of 30. Yeah. So okay, actually one cos plus 30. It was cos. So it was cos minus 30. It was 30 minus 5, right? That's why formula gets confusing. It was 30 minus 5. For the first one, it was 30 minus 5. You can choose either one of them, doesn't matter. So if it's 30 minus 5, my 5, remember 5 is actually here. It is lagging. So 5 will come out to be minus 60 degrees, right? Am I correct? No, it will be plus only. It will come out to be plus 60 degrees. So if it is plus 60 degrees, so yeah, this will be negative only. This will be negative only. Okay. So cos of minus 30 is root 3 by 2. So this will be 100 into 20 into root 3 by 2 to 10. So this will be 1000 root 3. So this is what one of the wattmeter will read. W2 will read what? W2 will read VLIL cos of 30 plus 5. So what will be 30 plus 5? It is simply 30 plus 60, that is 90. Cos of 90 is 0. So it will simply read 0. One of the wattmeter will read 0, other wattmeter will read this much amount of value. Okay. Now what is the important point? The important point is if I want to do it otherwise. So they have just asked us what each wattmeters will read. Each wattmeters will read this. Okay. So if I want to do it using method 2, that will be lengthy obviously, but from that you will also understand exactly what is happening. So my red phase is connected, right? So wattmeter 1 will read what? Wattmeter 1 will read VRY into IR. So it will read VRY into IR into cos of the angle between VRY and IR. And wattmeter 2 will read VBY and VIB, right? VBY and cos of angle between VBY and IB. Now I will assume a reference. This is a star connected network, so I will assume VR as my reference. So my VR is reference, right? If VR is reference, obviously my current IR, it's a phase current and line current is same. It is lagging by 5. Phi is 60 because they have mentioned this is a lagging load. Okay, it is a positive angle, that's why this is lagging load. So I will not go into too much depth here about lagging leading loads. Those we already know. So what will be my VRY? VRY will be simply, what is my VY? So VR will be simply, let's say VMP 0. I'm just writing phasor. VY will be the same thing VMP but phase shifted by minus 120 degrees. And VB will be VMP and phase shifted by plus 120 degrees. Okay. So what will happen is that VRY is this, which will be what? So VRY will be VR minus VY, correct? VR minus VY. From here you can directly say, if I subtract this is minus 120, my phasor will be something here. This is minus 120 is here. So I will just take the minus of VY and add these two up. So if I add these two up, I'll get somewhere here in between, and this will become root 3. I already know this result. Just for the angle I am doing this, VMP, okay, angle of plus 30 degrees. It will lead. I already know this, but still for the sake of it I am doing it. I know this, right? But what will be then? What will be my VYB? VYB will be just 120 degree lagging out of this, right? It is totally balanced system, so it will be 120 degree lagging. So it will be 30 VMP minus 120. But what do I need? I need actually VBY. VBY will be flipped 120, right? So VB, not 120, 180. So VBY will be simply root 3 VMP. Either you can subtract 180 or add 180. I will add because I want to keep it like around 90 range. So I will add 180. So this comes up to plus 90. And what current I need? IB. IB will be what? IB will simply lag IR by 120 because they are also phase shifted. So IR is minus 5. IR angle has its own magnitude. IM angle minus 5. Okay. And phi itself is negative, so that's fine. Yeah, phi itself is negative. Yeah. So and my IB will simply okay, IB will not simply lag. Actually, IB will lag. IB will be IM plus 120 minus 5. I hope you understand why, because my IB this VB is VMP plus 120, right? Because it will lead. VB is plus 120. So obviously from this plus 120 my current will lag another 5. So now I am able to find out the angles. So now I can write the angle differences. So W1 will be VRY. VRY is again that is root 3 into VLRMS. Not VLRMS, sorry, root 3 into VMRMS. Or they have already given me, this is the line voltage, right? VRY is the line voltage. They have already given me the line voltage 100 volts. They have already given me the line voltage. So I will directly write here V line to line RMS into I line to line. This is IR, so I will write here IR into cos of the angle. This is the most important one. So what is the cos of the angle? So VRY has an angle of what? Plus 30. And it has an angle of IR has an angle of minus 5, right? So it will be the angle will be 30 minus 5, so it will become 30 plus 5. Okay, what is this? So phi is 60 simply. So if phi is 60, this will become 0, correct, as phi is 60. So from here you can directly say which wattmeter is reading one. So I can perfectly say W1 is reading this much. Okay, and what will be W2? W2 will be again this thing will be copied. Okay, few things, the angle will change just, right? This will not be the same and this will also not be the same. So this thing is same only. VVY is line to line voltage magnitude. IB is IB. Okay, IB we can find out later. But what is the angle? Angle is VBY and IB. VBY is what? VBY is here. plus 90, and IB is minus 5 plus 120 minus 5. So I'll subtract the 2. So I will get minus 30 plus 5. Correct. So you can put the value here. You can put 60 here, or you can take the minus common. You will get the same result. Okay. You can do 30 minus 5, or you can put 5 here. 5 equals to what? 60. So you'll get cos 30. Right. Cos 30 is what? Root 3 by 2. So it will be VLRMS. VLRMS is 100. What is my ILRMS? ILRMS is this 100 divided by 5, right? Impedance into cos of 60. Like not 60, sorry, minus 30 plus 60, that will be cos of 30 only. So this will give you root 3 times that. So it will be 1732, something like that, right? 1 watt. Okay. So if you ever get stuck, I do understand that this method is lengthy, obviously, but if you ever get stuck with the first method, right? Because with the first method, it is just formula 30 minus 5, 30 plus 5. If you ever get stuck with the first method, you will use the method 2 using phasors. So you will be able to exactly say which wattmeter is reading how much. Okay. So exactly you will be able to see this. And here you won't be able to see, because I assume W1 is equals to 30 minus 5 and W2 is 30 plus 5, which was actually wrong. So that is the beauty here. Yes, 2 wattmeters, one of them will read 30 minus 5, one of them will read 30 plus 5. But which one is it? You will not be able to say until you understand the phasors. If you add those two up, here also if I add those two, I will get the power as required. And here as well, if I add those two up, I will get the power. The power answer will be correct. It will not be incorrect, right? But you will not be able to understand which one is reading what. And when calculating the reactive power, you will be wrong, because reactive power has a significance in sign. Active power can never be negative, right? It can the load can never supply the power, so it will always be positive, that we know. But reactive power can be negative. It defines either it is leading reactive power or lagging reactive power. So when that will happen, you will mess up. So it's better to solve it using phasors when you are calculating the reactive power, because you will mess up with the sign, because there it is W1 minus W2, and W1 needs to be W1 and W2 needs to be W2. You cannot just swap them. Then the significance will change. It will become leading reactive power. Okay. So that portion is very, very important to understand. Whenever these type of question comes, you don't know, you will just directly solve using the formula. Okay. You don't have the circuit diagram. You will directly solve using the formulas. 2 wattmeters which are connected to measure the total power in a 3-phase supplying a balanced load read 10.5 kilowatt and minus 2.5 kilowatt respectively. The total power and the power factors respectively are. So total power will be simply the sum of the two. So total power will be W1 plus W2, that is 8 kilowatts. Okay. What about the power factor? Now here, if they have given the values, right, you will directly substitute W1 with respect to 10.5 and W2 with respect to minus 2.5. But where you will go wrong, I will explain that here. Okay. Like here it will be not wrong, but if gate examination wants to trap you, he or she can trap you. So what you have to do, you have to use tan phi, that is reactive power of the active power. And what is reactive power? Reactive power is Q, that is root 3 times W1 minus W2, W1 divided by W1 plus W2. So this is root 3 times W1 minus W2, that is 10.5 minus of minus 2.5 divided by W1 plus W2, that is 8, right? So this will convert, this will be basically 13. I will just have the quick computation. I will just bring my calculator. So it's almost 70 degrees. So phi is, I get my phi as 70 degrees. And if I do the cos of this, it will give me 0.33. This answer will be correct. This won't be wrong, right? This will be correct. But if someday, if a multiple select question comes and they ask you that is the power factor leading or lagging, you won't be able to say, because you have assumed that W1 is positive, like W1 is greater than W2. Whenever W1 will be greater than W2, you can say that your angle phi is coming positive, it is lagging. But we don't know. So this question also cannot ask us the type of the load, whether the load is lagging or leading. But if they want to trap you, what they will do, they will give you these connections. Okay. And you will solve it using this thing. Okay. You will say W1 is 1000 root 3 and W2 is 0, right? Then you can simply find out the angle. If you find out the angle, you will go wrong. Okay, because the power factor will get correct, but the type of the load you will go wrong. Either it will be lagging or leading. Yeah, sorry for the interruption, I just had a call. So this is the basic thing that I want to talk about, is you have to be careful about the angle as well. Okay, because remember, just it's good to remember what is your W1. W1 is always 30 degree minus 5 and W2 is always 30 degree plus 5, and from here you can derive the power like reactive power formula. Reactive power formula, the first component W1 will always be this minus W2, this. Okay, because your wattmeter readings can be negative, so remember this W1 will come first, then W2. And what is W1 associated with? 30 minus 5. So wherever you see 30 minus 5, that will be your W1. Okay, like in the computations here, just say for this is 30 plus 5. This is actually not my W1. Okay, my W1 is this, I just named it, but that's some important point that I wanted to emphasis on, that 30 minus 5 will be a W1 and 30 plus 5 will be a W2. Then only you will be able to use this tan phi formula. Okay, this formula that I derived, right? Then only you will be able to use this, because we derived, right? We derived from this W1 is 30 minus 5. That's how we derived it. Else your answer will come out to be negative. So the angle that you are supposed to get, let's say you are supposed to get 60 angle, you will see minus 60. So instead of lagging, you will say leading. It can go wrong. Okay, so just be careful about that. So yeah, we'll solve more questions and you will understand this thing slowly. So let's solve the next question. So a wattmeter reads 400 watts when its current coil is connected to R phase and its specific coil is connected between this phase and a neutral of a symmetrical three-phase system. Supplying a balanced star connected load of 0.8 inductive load. The phase sequence is RYB. What will be the reading of this wattmeter if its pressure coil alone is reconnected between B and Y phase, all other connections remaining as same? Now this is interesting. Here what they are telling, that this is not a 2 wattmeter method of measurement. This is a symmetrical system, and wattmeter reads 400 when it is connected between the R phase and between the R phase and the neutral. The voltmeter is the pressure coil is connected between the R phase and the neutral. So my wattmeter reading is currently wattmeter reading is currently VRN IR cos of phi, that is a power factor angle between the current and the voltage, that is equals to 400 watts. Now what they are telling me is they have done few modifications, that instead of connecting it between red and neutral phase, what they are doing is they are connecting it between the B and the Y phase. So now it will be VBY. The current coil is remain unchanged, so it is IR into cos of what? Cos of angle between the voltage and the current coil. I don't know yet what is the angle between the voltage and the current coil. So for these type of questions, you need to understand that method 2. If you don't understand method 2, you won't be able to solve this. Okay, so here what will be the angle between VBY and IR? So again I will go by the phasor. This is 3-phase balance system, so I'll assume my VR to be reference. Again, if my VR is reference, my VRY will be what? It will lead. So by now I know all these things, right? So I will write directly. It will lead and it will have a magnitude of √3 VM phase plus 30. My VYB, they want YB or BY? They want BY, right? VYB will be just lagging VRY by 120 degrees. So it will be minus 90. Okay, but I want VBY. VBY will be what? VBY. Okay, I will just add 180. If I add 180, I will get VMP plus 90 degrees. Okay, so I'll get plus 90 degrees. So this is my VBY basically. So this is VBY. What can I say is, what is my IR? IR is still, IR angle is still what? IR is still IM angle phi. Okay, so this will be what? My like my reading will be what? My VBY. What is my VBY actually? What I can say is, they have given me this 400 watts. Also they have given me cos phi. Cos phi has been given in 0.8. So I can get this multiplication, right? This is VR. So what is my VRN into IR? It is 400 by 0.8, that is 500. Okay, volt ampere. This is the apparent power. But here what is given is, this is my wattmeter reading will be VBY into IR. So to get VBY into IR, I can multiply on both sides √3. So if I multiply both sides on √3, this will become VRY into IR will be 500 into √3. Correct? So this will be what? Just this product will be what? This product is same as this product because the magnitude is same. VVY, VRY, all the magnitudes are same. So this I can replace with 500 root 3. So my W will be 500 root 3 into cos of angle between these. So what is the cos of angle? This angle is 90 and this angle is 5. So this will be 90 minus 5. Okay. So it will be actually 500 root 3 by 2 sine of phi. And what is sine of phi? Cos of phi is 0.8, sine of phi is 0.6. Okay. Or you can find out the perfect angle. From that you can put the phi value. Everything will work. So it is 0.6. So it will be 300 into root 3. Okay. So if it is 0.6, right? Yeah, 0.6 is this. So it will be 300 into root 3. Now what will be the value? So if I want to calculate the value, right? It will be 300 into root 3. It will be 519.6 watts, right? 519.61 watts. So this method actually works for everything because they won't give you just laddu type question, right? Just simply, okay, W1 is this, W2 is this. Can you say the active power? No, gate won't do that, right? Gate will twist the question. So you know to wattmeter method. Can you solve it if I just twist the question, right? I don't want 2 wattmeter method. I want something else. So they want to see, are you able to understand this? Because if you are able to understand this, then you have understood the 2 wattmeter method. They want to differentiate who have mugged up the formula and who understood the concept and then mugged up the formula. Okay, so there is a difference between these two. Who just have blindly mugged up the formula, but who have understood the concept as well. Okay, so they want to differentiate. That's how they will differentiate, because they will not simply ask the one word question, right? One liner question. Okay, then how will they differentiate? How will they understand that this guy is good for IITs? So they have to understand that. Okay, so I hope you get this point. So yeah, that was basically it. Now let's move on to the next question. So if I have a next question, this is the next question, right? So this is the next question. So here I have a wattmeter, correct? And this wattmeter reads 5.54 when its current coil is connected to R phase. Okay, so when the current coil is connected to R phase and its voltage coil is connected between R and the neutral. Fine. So again, it the same like previous question only, just same as previous question. So it reads VRN IN cos of phi, right? Yeah, load angle basically cos of phi. It reads 5.54 into 10 cube. R phase is symmetrical and its voltage coil between neutral and R phase of a symmetrical 3 phase, supplying a balanced load of 30 ampere at 400 volts. So it is supplying a load like my V phase RMS. It is supplying a balanced load at 30 ampere. So V phase RMS will be 400 volts and I phase RMS is 30 amperes. What will be the reading on the instrument if the connections to the current coil remain unchanged and the voltage coil be connected between B and Y phase? So interestingly, if you observe, this expression actually comes out to be what? It is VLIL sin phi, right? So this comes out to be VLIL sin phi, which is the reactive power. So like this is also another way to measure the reactive power using only single wattmeter. So we had only single wattmeter. So like this is also another important theory I forgot to mention, that what expression I get? I get the expression W is equals to VL IL sin phi. This I can write as Q divided by root 3. Correct? So with a single wattmeter, I can actually measure the reactive power of the 3 wattmeters. Okay? So this is also a good thing that you should know, that yes, if in the question they ask, can a single wattmeter measure the reactive power? Yes, it can measure the reactive power of all the all the 3 phases with a single wattmeter. So okay, so this is another quick key point that you should get to know. So here like we're doing the same thing, exact same thing. Okay, ditto, same concept we copied. So this one I will leave it out to you. This one is the homework for you. Okay, everything is same. Previously it was RN and now it has been converted to B and Y. Everything is same. So this one I think you can solve it by yourself. Okay, so let's move on to the next question. When two wattmeters W1 and W2 are used to measure power input to a AC load, each of them indicates 60 watts. So each of them are indicating 60 watts. So both are W1 equals to W2 equals to 60 kilowatts. When can they indicate same? When the power factor angle phi is 0. If phi is 0, then cos 30 minus phi and cos 30 plus phi, both of them will be same. So this indicates totally my phi is 0 degrees. Okay, it is unity power factor load. If the power factor is to be changed to 0.866 leading, keeping the total input power same, then the reading of W1 and W2 will be. So total input power must be same. So what is the total input power? P total is W1 plus W2, that is 120. So now also it should remain same. Okay, and I want my power factor to be 0.866. So if my power factor is 0.866, that means my phi is what? Phi is simply it will leading, right? Leading means it is negative. Phi is negative. Phi is negative. It is root 3 by 2. So it is cos inverse of root 3 by 2 is cos 30. So this will be minus 30. Phi will be minus 30. Now if you replace 30 minus 5. So like what will be cos of 30 minus 5? Cos of 30 minus 5 and cos of 30 plus 5, right? 30 minus 5 and cos of 30 plus 5. So this will give you cos 60. Cos 60 is how much? Half. And the other reading will give you what? Cos of 30 plus 5. This will give you how much? This will give me cos of 0. Cos of 0 is simply 1. So now what they have told me? They have told me that the power should be same. So initial power was how much? This, right? W1 plus W2. It is 120 kilowatts. So it should be same in the current power. What is the current total power? Current total power should be root 3 into VLIL into cos of the angle, right? Cos of phi. Now my power factor angle is how much? Phi is minus 30. So cos 30 will be under root 3 by 2. So this will be 120 divided by 120 into root 3 into VLIL into root 3 divided by 2. So this will be 3 by 2. So your VLIL will actually increase now because my power needs to be same. Previously my load was unity power factor. Now it has become leading power factor. Obviously the active power will change if I keep everything else same. So what I did was I changed my VLIL. So this time my VLIL is simply, this will become 40 into 2, 80 kilo amperes, not kilo amperes, sorry, 80 kVA. Okay, so this is your VLIL. This one you will replace in this equations. If you replace in this equations, you will get your wattmeter readings. So this will be VLIL by 2, that is 40 kilowatts, and this will be VL into IL, simply 80 kilowatts. So the active power need remains same, so it will be 80 plus 40, that is 120. Okay, or you can understand from the options as well. If you calculate the power factor in each of the cases, you will get your answer. So what, this is the method 1. Method 2 is simply options. How do you analyze using options? So what you do, you just compute the power factor angle. What was the power factor angle? Tan phi was equals to root 3 into W1 minus W2 divided by W1 plus W2. So here W1 minus W2 is 60, correct? It is 60 into root 3 divided by the total addition. Addition is 120. So it will be tan inverse of root 3 by 2. It is some weird angle. It is not phi equals to 30. That power factor angle that they have told me to get the expression. So it is not correct again. And here as well, if you see, it is 30 and 90, the same thing only, right? But this time, like, you will get the power factor angle to be some weird angle, that is tan inverse minus root 3 by 2, which is again not the required power factor angle. My required power factor angle is simply 30 degrees. Here if you observe, it will be W1 minus W2, that is 40 minus 80. It will be minus of 40 divided by 120, so it will be minus of 1 by 3, and obviously a root 3 is at the top, so it will be minus 1 by root 3. Tan inverse of minus 1 by root 3 gives me minus 30, which is my power factor angle. Okay, this one will also not give me that value. Okay, so you understand the significance. If this were flipped, right, it is, if this is 80 and this is 40, the answer, your the answer will be correct. This option will be correct. Why? Because then it would have specified for lagging power factor, because my W1 was greater than W2. Okay, remember, if W1 is greater than W2, that is cos of 30 minus phi term with which the power term is associated. If it is greater than the cos 30 plus phi, obviously you will say that it is a lagging power factor load, but they have explicitly told that we need to find the value for leading power factor angle. Okay, so this is a very important point. Here W1 is less than W2, that there is a significance. What does it say? It says load is leading. Okay, I hope you understood the point. Like next, there is a question for delta connection, so we can solve this question. So again, interesting question, because delta connection questions you generally don't solve, so we'll solve this. A figure shows a 3-phase delta connected load supplied from a 400 volt 50 hertz 3-phase balance source. Okay, so it is a 3-phase balance source and we're getting a delta connected source, and this is a 3-phase balance source. The potential pressure coil and the current coil of the wattmeter are connected as shown, with the coil polarity suitably selected to ensure positive deflection. So all of them are giving me positive reflections. The wattmeter reading will be what? So what does the potential coil measure? Potential coil actually is measuring the voltage difference between VBC. Okay, so I will assume it is like my positive polarity only. Potential coil is measuring VBC, and what is the current coil measuring? Current coil is measuring the current through IAC. Okay, current through IAC. So what will be the value basically? So what I can say is IAC, I am saying it is a purely residual load, so it doesn't have its own angle. So this will be cos of angle between VBC okay. So now I can say that what I can say is this VBC IAC. So what is IAC? IAC will be simply, this is a residual load, right? It will be simply VAC divided by its own resistance, VAC divided by R. Okay, so VAC divided by R. So it doesn't have its own angle, right? So now I will write the phasors. So what I will say is I will assume that I am going by ABC. I am following ABC, right? ABC phase sequence. Generally we follow the ABC phase sequence. So VAB, I will assume it as reference some V angle 0 degrees. So my VBC will be equals to, it will lag first, minus 120, and my VCA will be V plus 120, right? This you have to remember. How to remember this I have explained. So but what will be my VAC? VAC will be just flipped. So VAC I have to subtract 180. VAC will be just flipped. So it will be V of minus 60 degrees. So VAC is minus 60 degrees and VBC is minus 120. So what is, I need the angle difference between VBC and IAC, and IAC is simply VAC. It is proportional to VAC. So I need the angle difference between VBC and VAC. So what is the angle difference between VBC and VAC? It is minus 60. It is minus 60. So it will be my wattmeter reading. Wattmeter reading will be, they have already told me the line voltage magnitude, that is 400 volts. So it will be 400 volt into 400 by the resistance R. R is 100 into the cos of angle between these two. What is the cos of angle between these two? Minus 60. Okay, the cos of angle between these two is minus 60. So it's that simple. Like delta load can seem intimidating, but if you solve with the basics, it's that simple. They will not ask that much difficult questions. Okay, so this will come out to be what? This will come out to be 16 into 10 raised to power 2 into 1 by 2. So it will be 800 watts. This will be a simple answer. Like how much time did it took me? But this particular thing you need to understand. If you are not able to understand, please go back and watch the 3-phase basics lecture. There, this will be cleared better way. Okay, and trust me, no one will teach you like this. Okay, no one will teach with the help of phasors. So now let's move to the next question. So this question is also similar, but that's why I tell you always basics is the king. Because if here, right, if you don't understand the basics, you will not be able to solve this question. So what is the question telling us? A single phase load is connected between R and Y terminals. So single phase load is connected between R and Y terminals. Fine. This is a single phase load. Okay. And there will be the terminal voltage is 415 volts. So I will write this down. VLL is 415 volts. So this is important to me. Okay. Because generally when they will not specify any term, right? Just specify the voltage. You will assume that it's a line voltage. That's the important thing that you need to take care of. Symmetrical 3-phase 4R system. So this is a symmetrical 3-phase 4R balance system with phase sequence RYB. This is also important, right? Phase sequence is RYB. Why? How I write the phasors. That's why this is important. A wattmeter is connected as shown in the figure. The power factor of the load is 0.8 lagging. So my cos phi is 0.8 lagging So if my cos phi is 0.8 lagging, my phi will be what? Phi will be simply 36.86, and please remember this will be plus 36.86. If let's say this was leading, then things would have changed a bit, right? Then this would have been negative minus 36.86. So you have to take care of this. The wattmeter will read what? Okay, so how is the wattmeter connected? So current coil is connected in series with the load. So whatever the current that flows through the load, that will be my current. Voltage is actually connected across a B phase. Okay, so how will you read the voltages? So here what you'll do, first of all you calculate the current ICC. ICC will be what? ICC is simply VRY divided by Z, right? VRY divided by Z. So I can say what? I can say what here? I know I can assume again a reference of VR, that is, let's say V by root 3, right? Why V by root 3? Because V is the line voltage. That is why I'm taking the reference VML by root 3. Angle of 0 degree. It is a RYB sequence, phase sequence. So VY will be VML by root 3 minus 120, and B will be VML by root 3 plus 120. Okay, so my V, what do I want actually? I want VRY. So what is my VRY? VRY will be, again, if you remember, VRY is VML plus 30. It will lead the phase voltage, right, by 30 degrees. What about the Z? Z is actually 100 plus 36 degrees, because it is also a phasor quantity. It is 100 plus 36.86 degrees. So here, right, I can write with angle. I can write the current coil with angle. This will be VML, and VML is what? VML is simply 415, right, plus 30 degrees. So this will be 415 plus 30 divided by Z is 100 divided by 36.86 degrees. So this will come out to be, if I just do the computation, this will be 4.15 angle minus 6.86 degrees. Okay, so this will be 4.15 angle minus 6.86 degrees. So this is the angle. Now what about the voltage? Voltage is simply VBN, right? Voltage is simply VBN. And what is VBN? VBN is this, right? So VBN is simply this, 415 divided by root 3 angle 120 degrees. So what will be the wattmeter reading? It will be VB into I CC, whatever it is, into cos of the angle between VB and ICC. So VB is 400. I will just write the magnitude. It is 415 by root 3, as 415 was line voltage. Into, I will again write the magnitude of the current. That is 4.15 into cos of the angle between these two. What is the cos of the angle? So it is 120. 120 minus of minus 6.86. So just be careful. This is minus 6.86. So this will come out to be 126.86. It will add up. So if it adds up, what will I get as my result? So it 126.86 into, not into, sorry, 126.86 cos of this into 4.15 into 415 divide by root 3. I will get minus 597, almost minus 597. So my wattmeter will actually read negative value minus 597 watts. So the current answer will be minus 597. Okay, although obviously you cannot measure current like this. What you will do, you will flip the potential like points of the potential coil, so that you get a positive value. That is the important portion for you. Okay, so next is this question: a current coil of 120 volt, a current coil of a 120 volt 5 ampere Dynamometer type wattmeter, low power factor wattmeter carries a current of this much, while the voltage across the pressure coil is this. Cos and sine, it's like almost like they are phase shifted by 90 degrees. What will the meter indicate? So obviously the meter will indicate 0 degrees, right? Why? Because current coil is carrying some sine omega t, and voltage coil is carrying some cos omega t. So what is the phase difference? The angle between voltage and current is simply 90 degrees. So cos of 90 is simply 0. So my power like the wattmeter will show 0. This will be answer. Okay, simple. You don't even need to do any calculations. Okay, that is the simplicity of these things. Okay, so let's do few more questions are left. Just we'll finish those. So a 5 ampere 200 volt electrodynamometer type wattmeter has a scale of 120 divisions. Its pressure coil receives this voltage while its current coil receives this much amount of voltage. What will the wattmeter indicate? So this is actually not a three phase wattmeter question. This is actually 2-phase wattmeter question. So like, what will the wattmeter indicate? What is the active power? That is what the wattmeter will indicate, right? Active power is what? It will be the voltage into current and the cause of angle between each of those, right? So for this component, I will only choose the like frequency components. I have taught this concept in my network theory classes. I will not explain here. So this component, these two components, the same frequency component will only contribute to active power. Again, 3 omega t and this 3 omega t will contribute to active power. I don't have any 2 omega t in the voltage component, so this current 2 omega t component will not contribute to any active power. That is the concept that I have explained previously in my networks classes. I will not explain here. Okay, so same frequency component only contributes to active power, right, of both current and voltage. So this will be V into I, Im by 2 into cos of angle between these two. So it will be this 250 into 8 by 2 into cos of angle between these two. Cos of angle between these two is 45 plus 46 into 2 again. This is 8, right? Yeah, 46 into 2. 46 into 2 divided by 2 plus what is the angle between them? What is the angle between them? It is 30, right? Cos of angle is minus 30. This is plus 45. This is minus 30. So this is the active power, but they have asked in division. I will come to that. Don't worry. 250 into 8 divided by 2 into 45 cos 707.1, and this one will be 46. Okay, into 2 and 2 gets cancelled. This will be into cos 30. Cos 30 is simply 1 by root 3 by 2, right? So it comes out to be 39.83. So this will come out to be 707.1 plus 39.83. Okay, I have added it twice. So your answer will simply come out to be 747.537 watts. Now this is your power read by the instrument, but actually they are asking me what will the wattmeter indicate, because I know in full scale it has 120 divisions. So what is the full scale? Full scale of this particular thing is Vi cos phi, right? So full scale, P full scale will be at Vi cos phi, and at full scale cos phi will be 1, power factor will be 1. It will be simply V into I. Okay, if my phi is simply 0 degrees. So what is V into I? It is 200 into 5. So this will be 200 into 5. Sorry, not 120 into 5, that is 600. Okay, anything I have done it wrong? So 200 into 5 is 1000. Sorry, yeah, 200 into 5 is 1000. So at max it can reach 1000 watts. Okay, this is equals to 120 divisions. So what will be corresponding 747 divisions be equals to? I will assume here we are increasing linearly. So just have to use the unitary method. So 747 divided by 1000 into 120 will give out to me 89.7. So it's almost equals to 90 divisions, or like closest here I can see is 88 divisions. So I will choose that. Almost equals to 88 division. So I will choose that. Basically 88 division will be simply option A. Option A will be correct. Okay. So that's how, like, this should actually be 90 actually. I think I should change the option because closest should be 90. So it should be 90. So this should be almost equals to 90 divisions. Okay, so that's how you solve this question. These questions are basic. So let's solve this last question of today's lecture. This is the question: for the network depicted in the figure connected to a 3-phase 440 volt 50 Hz supply with a phase sequence of ABC, the wattmeter reading will be. So I have connected again between B and C phase, and A phase is carrying the current. This is a delta connected load. So what I will do, Okay, we can solve this question, or I can give this question as homework, and in the next lecture we'll start a new topic. Or okay, let's do today's topic. Let's finish this actually. Although this is a bit lengthy, let's finish this. So we have this connection, right? Pause the video and try to solve the question by yourself. Then I will solve. So I have to find out the reading of the Wattmeter. So again, what is the pressure call? Pressure call is VBC, right? It is VBC, and it follows the phase sequence of ABC. Okay, so VBC will be what actually? Again, I will assume a reference. What is my reference? Reference is this, right? VB, VA. VA is V angle, let's say 0 degree. VB will be V angle minus 120 degrees, and VC will be V angle plus 120 degrees. This is VC, and what will be my VAB? VAB will be simply root 3 times V. It will lead, right? It will lead 30. And what do I need actually? I am mostly interested in VBC. VBC will be again lag VAB by 120, so it will be minus 90 degrees. That's it. That's how much information I need. Other rest I can do by myself. How will I do? I will explain. So I need this current, right? I need this IA current. What is this IA current? So I can observe that some current will flow through this and some current will flow through this, and that will be equals to the IA current. What is this current? This is VAB divided by this whole impedance, right? So my IA, I can write is equals to I1 plus I2. I will just copy the circuit. Paste it over here. Let's name this one as I1, this one as I2. Okay, so I1 is how much? I1 is equals to this voltage, right? VAB divided by the impedance. So I1 is VAB divided by whatever this impedance is. Let's name this as Z1 for now. And I2 is VAB, not VAB actually, it is VAC divided by whatever this Z2 impedance is, correct? So I can directly write here expressions, right? What is my Z1? I can define my Z1 like this, that I will write the magnitude and the angle. So it will be 30 square plus 50 square whole under root. So it will be 58. Magnitude will be 58.3 and angle will be 50 divided by 30, tan inverse it will be 59 degrees. Okay, so this will be my angle. What is my VCA actually? VCA will be again, VCA will be plus 120 of this, not this, it will be plus 120 of this, right? So it will be 150 actually. So VCA is this, but I am actually interested in VAC. What is my VAC? VAC is simply root 3 angle. I have to subtract another one here, it will be minus 30. So from here I can directly calculate my I1 and I2 in terms of phasors, because then I can simply add those up. So this will be, now what is my V? Have they told me what is my V? They have told me this, right? Now this is what? This is actually line to line voltage. This is actually line to line voltage, right? But I here write whatever I have written, this is in terms of phase to phase voltage. So I have to divide by root 3 as well. So I will write here V actually is equals to 440 divided by root 3. Okay, just remember this. So automatically this VAB is root 3 times V. So automatically this becomes 440. This angle I need to write. What is the angle of VAB? VAB angle is plus 30. So I will write this plus 30. Divide by the Z1. Z1 is how much? Z1 I have just computed. It is 58.3, 59 degrees. So I can actually get this in the next page. Okay. So this is my Z1. Okay. So my Z1 is this. So I1 will be this value. So I can directly write down the I1 in terms of phasor as well. 440 divided by 58.3, 7.5 angle will be 30 minus 59 minus 29 degrees. What about the I2? I2 will be again, this will be 440 only. Magnitude will be same, 440. Angle will be what? Angle will be simply minus 30. Obviously Z2 has also changed. Z2 is magnitude is 40 and its angle is minus 90. It's a leading road, right? So it is something 0 0. It's just 11. Angle is 60 degrees. So this comes out to be simpler. So I can simply add these two up, right? So my IR will be the addition of these two. So I can now compute the phasor sum. So this will be 7.55 into 29 cos. So this comes out with 6.6. Real component is 6.6. What about this? It is cos 60. So it will be 5 plus 5.5. Real component is this plus j. Just doing the complex calculations, right? 7.55 into sine of 29. It will be almost half actually. So it will be 3.6 and this is negative, right? So it will be minus 3.66 and this is plus. So it is sine of 60 is root 3 by 2. It will be 9.526. So if I just subtract 3.66, this will come out to be j 5.866 and this is 6.6 plus 5.5. So this comes out to be 12.1. Okay, so this comes out to be what? If I just take the ratio, right? If I want to find out the angle of my current, tan inverse, this will be 25. So the angle of IR, right? Angle of IR is, this is positive, plus 25.86 degrees. Okay, this is the angle of IR. So I get plus 25.86. Now what do I actually need to find out? So I have got my IR angle, that is the current coil angle, right? That is the current that is flowing through current coil. What is VBC? VBC is this, right? VBC is this, minus 90. So what is the angle between these two? So what will be my wattmeter read? Wattmeter will read VBC, the magnitude, into IA, the magnitude, into the cos of the angle between VBC and IA. The angle between VBC and IA. Okay. So VBC magnitude is 440. VBC magnitude is 440, right? VBC magnitude is 440. IA magnitude is how much? IA magnitude, okay, I have not computed IA magnitude, sorry for that. It will be 12.1 whole square plus 5.866 whole square under root. Okay, this is just hold on, 12.1 whole square plus 5.866 whole square under root 13.45. okay, this will be the magnitude. Angle is this, magnitude of IR is not IR actually, this was supposed to be IA, sorry for that. IA, this is IA, right? This is not IR, this is IA. Have I written previously IR? No, I have not written IR. So this will be 13.45 amperes. So this will be 13.45 and what is the angle between these two? So angle of voltage is how much? VBC, right? VBC is minus 90. So this will be minus 90 and this angle is how much? Plus 20 plus 25. okay, this angle is plus 25. So this angle will come out to be plus 25.86, which I calculated earlier. So now if I want to calculate, right, if I want to calculate this will be into 440, this is minus 64.14. So what is the cos of this angle? It is 0.43 into 440 into 13.45. so your answer will come out to be 2581 watts. So this question is a good question. Okay, try it by yourself as well. This is the power measured by the wattmeter. So like here, right, this is not a standard question, this is some weird random question. So gate can ask this type of question. Just they will show you the connections and show you the load and you have to identify the currents and voltages, and with the help of that, with the help of simple concept that the power or the thing that is measured by the wattmeter is voltage, magnitude of voltage, magnitude of current, and the angle between that voltage and current. Cause of angle between the voltage and current. That is the most important part. And the basis of three phase also you should have a bit of knowledge and idea. Okay, so I hope you understood today's lecture. That was it about today's lecture. All the questions I have tried to solve. And in the next lecture, we'll learn about energy meter. I hope you have enjoyed this lecture. Thank you for watching. And I will see you in the next lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. I am Anish and today we'll start the lecture 4 of our measuring instruments chapter. So today we'll learn about energy meters. What are energy meters basically? So we have learned about wattmeters, which helps us in measuring the power of a particular load. But what does energy meter tell us? Energy meter tells us the energy consumed by that particular load. So what is energy basically? Energy is power integrated with respect to time. So energy meter will be a integrating type instrument because it integrates power over time. So this is the first thing that I wanted to tell, that energy meter is an integrating type instrument, which I told at the starting of our measurements chapters as well. So how does it measure it? Basically it uses the electromagnetic induction effect, or also known as the Faraday's law. What does Faraday's law tell us? So up until now we were using that only, but this actually uses that extensively here. Okay, so this utilizes the interaction between magnetic fields generated by currents in different parts of the instrument. So magnetic field this time will be generated by both voltage coil and current coil, just like the previous case as well. But here few things will be different that we'll learn. Just like the wattmeter, magnetic field will be generated due to voltage and current. They will interact with each other, and through that interaction I will be able to get my energy. So energy meter deflecting force is produced by electromagnetic field. So what will happen if you see this device like this? If you go in your home and you ask your father that where is the meter? Where is the meter of our home? Meter means a place where it shows how many units of energy you have consumed. Okay, because in your home you will get electricity, and that electricity takes some money. So if it takes some money, it will be depend on how much energy you have consumed. According to that, you will be charged. You will get a bill, right? So that bill actually is measured with respect to this energy meter. If you go in your house, wherever your energy meter is, go there and you can see there is a device known as energy meter. There it will show how many units you have spent till now. Basically, how many units you have used for electricity. Basically, okay. So this is basically a circuit like this, where I have two magnets. One is pressure coil. One is a shunt magnet and one is a series magnet. As the name suggests, shunt magnet means it actually has the potential, like it has the information of the potential, and series magnet has the information about the current of the load. And what it does is, as it is an electromagnet, I wind my wires along the magnets. Due to this winding, whatever the current flows, a flux will be generated due to this particular winding, right? And that flux will be proportional to the initial current. Okay, I hope you understand. It is winded here and a flux gets generated. And what is the direction? It is like alternate. As current is alternating, flux will also be alternating. It's not like a fixed direction. It will always keep on changing. Okay. Now current will also due to this current also, this magnet, it will generate a flux. Okay, and that will also be alternating as current is also alternating. Now this flux will come here and cut this aluminum disc, right? And as you know, whenever a flux cuts a aluminum disc, what happens? It finds a closed loop. And according to Faraday's law, if there is change in flux, because it is alternating flux, if there is change in flux, there will be some induced voltage. And that induced voltage will be present wherever the flux is cutting. Here the flux is cutting at the aluminum disc. So there will be an induced voltage. And what will be the direction of the induced voltage? It will oppose its initial cause. So obviously it will oppose it, right? Now, how will it oppose it? So there will be induced voltage here, and if there is induced voltage, this is a closed loop. There will be a current. That current sometimes is also known as eddy current, that I will come to. But there will be current due to that voltage. There will be current. Now there is some current due to this pressure coil. Okay, due to this shunt coil. Now there same thing I can say comment for this series coil as well. Series coil as well. That this will also generate a voltage into CMF. Due to that also a current will be generated. So what will happen is the current generated due to this pressure coil and the flux of this current coil, both of them will actually together try to oppose the current coil flux. Okay. Not the flux, sorry. Both of them will try to oppose the initial cause. basically both of them will try to oppose the current coil, and the pressure and the current coil the current induced through the current coil and the flux by the pressure coil, both of them will interact. That will create a torque on the aluminum disc that will try to oppose the pressure coil, the flux produced by the pressure coil. So I will get to that, don't worry, I'm just giving you an overview, don't worry, I will come to this, all this. So and that interaction within the torques actually will be proportional to the energy, because the number of revolutions that it rotates, okay, that will give me the information about the energy over a period of time. And like that, my energy is directly proportional to the number of revolutions of this particular measuring instrument. So I just gave you an overview. I will slowly explain everything one by one, don't worry about it. Okay, so just few things you have to keep in mind. We use the Faraday's law, and another thing that you need to keep in mind is that my torque produced in a magnetic field is proportional to the current and the flux. So these two things you should keep in mind. Okay, so here I have written the few things. The working principle of an energy meter is based on the concept of electromagnetic induction. It measures the electrical energy consumed in a circuit over time, typically in kilowatt hour. So this measures over time. That's why kilowatt is the unit of power, that is energy per second into hour. Okay, because this is a better unit. Why? Because if I measure power, if I write energy in terms of per second, right, the numbers will become very huge. So as I want to reduce the numbers so I had to choose a particular unit. Like they had to choose a particular unit, they chose kilowatt hour. That was the best unit to choose, because numbers weren't that huge or that low. It was easy to write, and it was easy to tell as well. Okay, so that is the only reason. The energy meter operates on the interaction between the two magnetic fields generated by the current coil and the pressure coil, as explained. So one magnetic field will be generated here, pressure coil, and another magnetic field will be generated due to the current coil. So now let's come to the derivation part. Okay, I will come to the derivation part, so you can listen to me very, very carefully here. So I know pressure coil will have a potential of VL. Okay, this will have a potential of VL, right? Pressure coil measure the voltage, so this will have a potential of VL. And due to that voltage, obviously, current will flow through the winding. That much is known. And that current IPC will be proportional to the voltage. That we already know. Same as wattmeter. Now, I know there is a current that is coiled in a magnet. So if I just curl my fingers, if I just use my right hand finger rule, okay, I will get some magnetic field, right? The magnetic field direction will be something like this. Okay, magnetic field direction will be somewhat like this, and it doesn't have any fixed direction. It can go up or down. Why? Because it is an alternating flux. Why it is alternating flux? Because current itself is alternating. Okay, and because voltage itself is alternating, current will be alternating. Current is alternating, flux will also be alternating. Okay, so that is one point. Now, other formula you can use. What is the formula? My V is equals to L di dt, right? So obviously, if my voltage is alternating, sorry, not this, L di dt is also there. I know my V is equals to d phi t by dt, change in flux. So if I just simply integrate this thing, voltage is sinusoidal, flux will also come out to be sinusoidal. So that basic thing you know. Okay. Now this will generate a phi pc, right? Phi pc. So I'll slowly write things down. So what will happen, as this flux is generated, there will be a induced EMF. So what happens, due to IPC, a flux is generated known as phi PC. Okay, flux gets generated on the metal disc, on the aluminum disc, right? That flux cuts, phi PC flux cuts the aluminum disc. Flux cuts the aluminum disc. And you know, of course, if you remember that whenever flux cuts the aluminum disc, what happens? Whenever flux cuts the aluminum disc, there is some change in flux, right? And if there is some change in flux, it will induce some voltage. Okay, this we have learned in Faraday's law. If you haven't studied electromagnetism for me, our our EMFT course is there on YouTube. You can please go and watch, then come back here, because that will help you immensely understanding the induction part of this derivation and other instruments as well. So obviously, due to this cutting of flux, right, a voltage will get induced. I will get a V induced. Okay, that V induced, I can say as V induced PC. Okay, due to this voltage induced here, as this is a closed loop, right, this is just a closed metal disc, a current will be generated. It will be I eddy current, IPC. Generally they tell this name as eddy current. Generally they tell it eddy current. That's why I am telling you this. It's just the name. This is the same induced current, just the name. So this is the eddy current that gets generated, and what it will try to do, it will get generated as such that it will oppose its initial cause. What was its initial cause? IPC. So how will it will oppose? A current will flow, right? If a current flows, like let's assume a current flows through here, right? A current flows like this. If a current flows, like a magnetic field also will be generated. Again, current is flowing, closed loop, magnetic field again will be generated, and the magnetic field will be opposing this 5pc, and in turn, if this opposes 5pc, in turn it will oppose the IPC. Okay, I hope you understand. So here I will write this current will be generated as such. It will, I can write here, it will generate a flux such that which opposes 5pc. Okay, and obviously how will it generate? This disc will also rotate. How will it rotate? That will come to, don't worry. Now this was the story for the pressure coil, right? So I'll just reduce the size a bit because I want to fit in the current coil story as well in the same page, right? So how do I fit? I don't know. I have to somehow fit all these things in a single page. Okay. Now about the current coil. So if I have a current coil, again a current is flowing through it, through the this core. If it is flowing through a core, what will happen? Again, if I curl my fingers, I will generate a magnetic field. That magnetic field will also cut here as well. It will come here as well. So due to same story, due to my ICC, I will write here actually, due to my ICC, just hold on. Due to my ICC, I will have a flux 5cc, which will in turn generate an induced EMF here, which is known as V induced cc, due to which obviously a current will flow, as this is a closed loop, which is also known as eddy current due to the current coil, right, which is known as IECC. So I'll write here IECC. Okay, now this flux again will oppose this current will again generate a flux which will oppose 5cc basically. Okay, this will generate a flux which opposes the 5cc. So that's basically it. And this induced EMF, right, sometimes it is known as, this is called as ECC, and this is called as EPC. Sometimes, like, they are just, this is the nomenclature you might have seen in your books. So just wanted to say all the nomenclatures. So this is what is happening. Okay, now as the pressure coil is highly inductive, if my pressure coil is highly inductive, so I know my pressure coil will be, this is my purpose. My purpose will be to keep the pressure coil highly inductive. Why? We will understand a bit later on. This time that inductive error will not come. This is a bit different than a wattmeter. So I design my energy meter such that my pressure coil PC will be highly inductive. Okay? So my PC will be highly inductive. So if my PC is highly inductive, what will happen? Like my flux and the current, right, both will be 90 degree apart from each other. How do I know? So let's say the flux is phi, some phi m sin omega t. Okay, let's say it is phi m sin omega t. What will be my induced voltage due to this flux? It will be d phi by dt, right? So d phi by dt will come out to be phi m omega cos omega t. So my sin omega t is what? My sin omega t is here. Okay, sin omega t, sin is in here, cos is here. So my voltage induced is here. Okay, this is my V induced and this is my flux phi, and I want this actually. So actually in turn, what is this telling me? So flux is actually proportional to the current that is flowing through the wire. So current will also be this. So this angle is 90 and I want it. To make it total 90, I need a ideal inductor. If it is ideal inductor, then the relationship between the voltage and current will be like this. If it is not, then the relationship will be like this, but with non-linear. So the flux will be somewhere here. The angle won't be exactly 90. And why I want it to be 90, that we'll discuss. Don't worry about that. Okay, that we'll discuss. So these are the few things that I wanted to talk about. Okay. So now I will come to the phasors. So I want to discuss few things. I will draw the phasor in front of you here. Then I will go to the phasor, actually what is drawn in here. So roughly I will draw the phasor. Okay. So let's say I have a current IPC that is flowing through, right? If I have a current IPC, this is the reference that I am taking. My voltage will obviously lead by 90 degrees because it's a inductive, like totally highly inductive circuit. Pressure coil is a highly inductive circuit. So obviously voltage will lead the current by 90 degrees. Okay. So voltage will lead the current. Now voltage leads the current. This is the relationship between the IPC and VPC. Okay. And the flux will also be somewhere around here. This will be my flux. Okay. This will be phi PC. Okay. Now, what about the current coil? So the voltage VPC is the actual voltage of the circuit, that is VL. Right. So current coil will be like, let's assume a lagging load with a power factor phi. So current will be somewhere here. I will be somewhere here, right? Lagging with respect to phi. So phi is somewhere here. That is equals to IL, and IL is equals to what? ICC. It is just in series with the load, right? This is in series with the load. So this is ICC. This will be I current, ICC. Okay. And in parallel with ICC, what do I have? I have phi CC, right? Current is directly proportional to the flux. So it will be phi CC. Now, due to this phi CC, again, a voltage will get generated, right? A voltage will get generated. One mistake I made here, that I didn't write the relationship properly. It is actually, if you remember, my V induced is minus d phi by dt, right? If it is minus, then minus of this will be simply minus cos omega t. So actually my cos omega t, if you have seen me teach network, I write my cos and sine like this, that to realize in phasor where they are. Cos always leads sine by 90 degrees. This is the relationship. Okay. So minus sign will be somewhere here. So I made a mistake here. Minus sign will be somewhere here. Okay. So if minus sign is somewhere here, so induced voltage will always be totally perpendicular, right? So this was the like actual voltage VL to which it is lagging by 90 degrees. Just wanted to show the phase relationship between the voltages, but my flux and the induced EMF will be 90 degree phase apart, and the induced EMF will lag by 90 degrees, right? So that is one important point that you should know. So here what I can say is that phi PC is here. Due to this, some voltage will get generated, that is here. Due to that, I'm not concerned about that. I'm not much concerned about that. Okay. What I'm concerned about though is that due to this ICC, a voltage will get induced, right? What will be that voltage? That voltage will be 90 degree phase lag with respect to this current. Okay. Because flux is also in the same phase with respect to current. So it will be somewhere here. So this will be the V induced, or also known as ECC. Okay. So I will come to the voltage induced by the pressure coil as well. Don't worry. For now, just understand the current coil. I will come to the pressure coil. Don't worry about that. So this is one thing. I get E induced, and in this E induced, basically current will flow, because this aluminum disc, right, it is like purely metal, so it will be purely resistive, and if there is some inductance, due to that there will be some lag, and that lag angle I can assume it as alpha. So the current that will be flowing through the aluminum disc will, let's assume it will lag some angle alpha, and it will be equals to ICC. Okay, that's it, ICC. Now from this current, right, this induced current and the flux, basically flux is flux of what? Flux of the pressure coil. Both of these actually combining together will create a torque, will generate a torque that will totally oppose the main cause. What was the main cause? The main cause was this induced EMF. The main cause was due to the current, coil current, so it will oppose it. Okay, it will simply oppose it. It will generate another flux that will oppose. So it will rotate as such that it is opposing this ICC. That's the main thing, right? Now this is the phasor diagram for the induced current. I will come to the pressure coil, don't worry. Now just before going to the main diagram, one more thing is that the angle between the pressure coil and the angle in the pressure coil, the voltage and current, right? Angle between the voltage and current of the pressure coil will not be always 90, because I can never get a ideal inductive circuit. So although my VPC will be lying somewhere here, the angle will not be exactly close to 90, because there will be some resistance in the wire. Due to that, my angle will not be exactly 90. Phase difference won't be exactly 90. So what will happen? This IPC will lag, but it will not lag exactly close to 90. It will lag a bit lower than 90. So this is known as the IPC dash, which is the actual current. This is the ideal one, and this is the actual one, due to which I am getting, and phase difference of, they name it as delta. These are just notations. No need to remember the names. I will tell you what things to remember. Don't worry about that. So this is delta. Okay, this is just delta. And delta will be almost close to 90, but it will not be exactly close to 90. So delta will be somewhat less than 90. Okay, but almost near about 90. So this is one thing that I wanted to take away. So my torque, like this is the phasor diagram that I was talking about. I hope you understand, like from the previous phasor diagram I have come here. And for there will be two torques generated. One will be the torque generated due to the flux phi cc, that is due to the voltage induced by phi cc. Another one will be due to the phi pc. So we will do one by one. So what will happen is TD1 will be proportional to the phi pc. Okay, because the flux and the current induced, they need to be of opposite. Like I cannot oppose my own own current, right? This cannot oppose itself, right? So this flux of other coil and the current of my coil and the angle, cause of angle between those two, my torque will be proportional to that. Okay, this is just a basic torque equation. That's it. Not that important. Just try to understand. Like this derivation is also not that important. Just watch this one. That's it. Once you watch what is happening, that's it. Derivation is not that important. I will tell you what are important. So here, what is the angle between phi PC and IECC? So these things I know. What is the angle between phi PCC and ECC? So where is my phi PC? Phi PC is somewhere here, right? Actually, it was supposed to be here, but it will be phi dash of PC, because it is not an ideal inductive circuit. It will be somewhat lower than 90. So my phi PC is somewhere lying here, and my IECC is here. So I need this angle. So this looks like a 90, but this isn't a 90, right? So I know this is 90. This angle is 90, right? This angle is 90, and this angle is alpha. So I need this angle, right? Not this angle, sorry. I need this angle. This angle only. I need this angle. So if I am able to find out this angle, and this is the angle, and this angle is 90, right? If I know this angle is how much? This angle is how much? Let's name this as beta. Beta is how much? This is total delta, and this is phi, right? So beta will be delta minus phi. Okay. And this angle is how much? This angle is simply, this overall is supposed to be 90, but this is delta. So it will be 90 minus delta. Okay. So I have got this angle. Although I don't need this angle, but I have got this angle. I need this angle. What will be this angle? Like this angle is 90, right? This angle is 90 overall, and this angle is beta. So this angle will be 90 minus beta. So it will be 90 minus delta plus phi. Minus delta plus phi. Just have subtracted a 90 from this, right? This overall angle is 90. I've just subtracted 90 minus beta. 90 minus beta is exactly this. Okay, so I got 90 minus delta plus phi. I know this angle. I know this angle. I know this angle. So I can tell the angle difference between these two. What is this angle? This is 90 minus alpha plus 90 minus. Okay, not alpha. Sorry. Have I done something wrong? Just wanted to do one thing. This overall is 90, right? Yeah. 90, 90, 180. Yes. This is alpha. So this overall angle will be simply beta 90 plus. This is okay. Okay. Yeah. This is. I'll just write here few things. Overall angle between these two, right? What will be this? The angle between these two. Okay. Angle between these two is this, right? These three sum. So it will be 90 minus delta plus 90 minus delta plus phi plus alpha. This will be the overall angle, correct? Because just hold on, I want to check. Yeah, this angle is overall 90. This is delta minus phi. Okay, this angle is how much? This angle will be how much? This overall is 90. Okay, this is not okay. No, I have made a mistake here. This is not actually 90 minus delta plus phi, right? Not correct. If I add these two, this will be total 90 minus phi. So this angle is 90 minus phi, right? This angle is 90 minus phi. This angle will be 90 minus of that. Yeah, I'm sorry. This angle is how much? This angle is 90 minus phi, right? If this angle is 90 minus phi, how much will be this angle? This angle will be simply wait, am I correct? This is 90 minus phi, right? Yeah. If this is 90 minus phi, this angle will be simply phi. Okay. Yes, this angle will simply phi. So this angle is phi. So alpha plus phi plus 90 minus delta. Okay. So 90 minus delta plus phi plus alpha. That's it. That is your angle. So you get your angle as 90 minus delta plus alpha plus phi. So this will be the angle and this will be the torque developed. So this just remember this, the torque developed for the case 1 is cos of this angle. Okay, and obviously phi BC and ICC is there. Now let us draw the phasor diagram for the second. Like, I don't want to populate everything in one diagram. For the induced EMF due to pressure coil. So my flux is here, right? Flux of the pressure coil is here, yeah, along this line. So induced EMF will be 90 degree lagging to this, and the current will also lag by alpha. So same thing is happening over here. I just deleted the currents, induced EMF voltage and currents. Here I have just written the pressure coil voltage and currents, known as eddy currents. Now what will be the angle? Now the angles have changed a bit. Okay, because this angle is now 90. This angle is overall 90. This is the angle between the pressure coil current and the induced EMF. So again, this time the torque TT2 will be basically flux due to the other coil, that is current coil, into the current due to its own induced due to its own coil, that is pressure coil IEPC, and the angle between those two. So where is my phi cc? Phi cc will be somewhere here, right? It will lag by phi. So I need to find out this overall angle. How do I find out this overall angle? Again, this angle is how much? This angle is delta minus phi. This angle is delta minus phi. This is alpha. I just need to find out this angle. This angle is simply 90. This angle is simply 90, right? So this angle is 90. So overall angle will be what? Delta minus phi plus 90 plus alpha. So overall angle will be, this will come out to be delta minus phi plus 90 plus alpha. This was much easier calculation, but the previous one was a bit difficult. Okay, plus 90. So you can simply write down that your torque, right, in TD1, in case of TD1, your torque TD1 will be actually proportional to what? This phi PC is in turn proportional to the current IPC, and IPC is in turn proportional to the voltage VPC. So it will be proportional to the VPC and IECC. IECC will remain as what? IECC is proportional to what? IECC is in turn proportional to the flux, right, that was generated. IECC was generated to, like, it is proportional to EECC, and EECC is in turn proportional to phi CC, and phi CC is in turn proportional to ICC. So I can write here ICC, and cos of this angle overall 90 minus delta plus alpha plus phi. Okay, what about TD2? What is TD2? TD2, again, your phi CC is directly proportional to the current, so it will be ICC, again ICC, and your IPC, again I can use the same relationship, it will be proportional to VPC, and cos of this angle, this will be 90 plus alpha plus delta minus phi. Okay, that's the simple equation basically. Now your net torque, right, net torque T net actually will be proportional, like each of the torques are opposing each other. So net torque T net will be TD1 minus TD2, as each of them are opposing each other. And what does torque mean? Torque means rotation. So each are rotating and each of them are opposing each other. So net torque will be TD1 minus TD2. So it is proportional to what? Proportional to VPC, IPC. Remember, the derivation is not that important. The main summary is the important, that I will come to. Okay, so IPC, this is common, just the angles are different, right? So it will be cos of 90 minus delta plus alpha plus phi minus cos of 90 plus alpha plus delta minus phi. So my tau net, let's break it down basically. So this is cos A minus B, so this will be VPC IPC, this will be staying here like this. I can break it down. This will be broken down into what? Cos A cos B plus sin A sin B. I'm just taking this as a whole angle, so this whole is negative now, so this will become minus, just for the simplicity, minus. Okay, so yeah, this will become this. So this will become cos A cos B plus sin A sin B. Cos A is 90, cos 90 is 0, so the first term will go away, just plus sin A sin B will be remaining. Sin A is sin 90 into sin B. Sin B is delta minus alpha minus phi. Okay, good. Now this will be cos A plus B, so here a negative sine of alpha plus delta minus phi will be remaining. So overall what do I get? I get sine delta minus alpha minus phi minus this, right? And this actually overall becomes plus. So here what happens is I get sine, like overall what do I get? I get sine delta minus alpha minus phi plus sine of alpha plus delta minus phi. Correct? Both of them are giving me the minus phi only. Okay, now I can break this down. Actually what I can do is I can write this something like this, that it will be alpha plus phi minus sine delta minus alpha plus phi, and this one is okay, alpha plus phi. I cannot write alpha plus phi. I have to isolate the alpha. Okay, that is my mistake. I have to isolate the alpha. So what I can do is I can write it like this, that this sine delta minus phi, and this is also sine delta minus phi. Yeah. So again I can assume as A, this I can assume as B, right? Not this. This delta minus phi I can assume as A, and alpha I can assume as B. Again, what is sin A minus sin B? Sin A minus sin B is sin A cos B. So this will be sin, I'm just shorting it down, sin delta minus phi into cos of alpha minus cos A sin B. Cos of delta minus phi into sin of alpha. Okay. After this, we actually do few approximations. I will talk about those. So like this, all this is not that important, right? The main conclusions is important, but I will without deriving this, I will not be able to come to the conclusion. So I will do this. So this is one term. Then the other term is here, right? It is plus sin alpha plus beta. This is sin. Again, let me assume this has this has A and this has B. Sin A plus B, right? Sin A plus B will be same only sin delta minus phi cos alpha plus sin alpha into cos of delta minus phi. Okay. So now what I can see is this and this are cancelling each other out, right? These two are cancelling each other out, and I am left with 2 times cos alpha sin of delta minus phi. Correct. And I had previous few terms over here written, right? My tau net is proportional to, obviously this was outside, remember this VPC IPC was outside, right? So we'll write this down, VPC IPC on the outside. This will be VPC IPC ICC, right? This is not IPC, ICC. Oh, this is not IPC, sorry, this should be ICC. Now obviously what you can say is this cos alpha, right, is constant. Okay, because it's the lagging power factor angle. This is a constant angle. This 2 is also constant. So net I can say that my tau net actually is proportional to sin, like actually is proportional to VPC ICC sin of delta minus phi. This is a very, very important equation that you should know. Very, very important result that you should know. Now, in case of ideal, right? Ideally, what would have happened? My delta was supposed to be 90, right? Delta was almost very near to 90. If delta is 90, then this becomes what? This becomes VPC ICC cos of phi, which is exactly what I want. I want the power, right? And this is almost proportional to the cos of phi. But as delta is not 90, there is an error. I will come to that error later on, but for now understand this. Okay, so this is my net torque that is proportional to. So this is the rotation that is happening, and the rotation is happening due to this particular torque. Okay, so this is the point that I want to like stop and then explain bit of theory. So current coil connected in series with the load, it produces a magnetic field proportional to the current. Voltage coil produces a magnetic field proportional to the supply voltage. Aluminum disc is placed between the coils. It is free to rotate, so it rotates with help of the interaction between the magnetic fields of the current coil and the potential coil, okay, or the pressure coil, and the torque developed is proportional to the cos of angle and the current and voltage multiplied between each of those coils. So it will be proportional to the voltage and current. So in turn, net it measures the power, and the rotation actually measures the energy. So if I integrate that rotation, I will get energy. So now I need a braking mechanism. Previously, if you remember, we had a control mechanism, right, where we stopped the torque. Okay, the torque was not acting anymore, so it had to stop, right? We had to reach steady state. To provide steady state, I need a brake magnet. What does brake magnet does? Because torque, what will torque do? It will keep on accelerating the disc. I don't want that. I want it to reach a steady state so that it rotates in a steady speed, right? So that I can measure the number of revolutions, and according to that, I will get my energy consumed. So brake magnet provides the damping by generating eddy currents in the disc to slow down its rotation proportionally to the speed of the disc, thus controlling its motion. So brake magnet actually slows down the rotation. Basically, it provides a torque which is equal and opposite to the deflecting torque, so that it doesn't accelerate and it is proportional to the speed, and that speed actually helps us, it is proportional to the speed, and in turn we get a relationship that the number of revolutions of the disc will be proportional to the energy consumed. I will derive that, there will understand this. Okay, so like the current coil produces a magnetic field based on the load current, and the voltage coil creates a magnetic field proportional to the voltage. The interaction between these field induces an eddy current on the aluminum disc, generating a driving torque. So that's how a driving torque is generated. Now how is the braking torque generated? The speed of the rotating disc is proportional to the electrical power being consumed, and if I somehow break the like disc is rotating very fast. The faster it rotates, my brake torque will be more and more strengthier. It will have high strength, so that it tries to reach a steady state, because it will keep on rotating, and I don't want that. Because let's say my speed initially was 1 meter per second, okay, at t equals to 0. As force is acting, so then it is accelerating, my body is accelerating, so speed become then 3 meter per second, 5 meter per second, and it is never reaching steady state. It is keep on increasing. If there is opposite force, okay, what it will do, it will keep the speed constant. So it will keep the speed, let's say 5 meter per second. It will keep it constant. So I want to keep the speed constant at steady state. That is what we used to do. We provide the control torque. Due to that reason, here we provide the braking mechanism. So let's understand the braking mechanism basically. So I'll have a permanent magnet, okay, and due to that permanent magnet, it will produce a flux. That flux will be some constant flux, right? So this permanent magnet, this is a permanent magnet. This will generate some flux phi m, that is constant, okay, because a permanent magnet cannot change the flux. It will produce constant flux, right? This permanent magnet is placed near, like the disc, if you see in the circuit diagram, if you see here, right, this is the brake magnet that is placed near the aluminum disc. If it rotates, what will happen? If the aluminum disc rotates, the flux will change through the disc. The flux that is cutting from north to south, that will change. If that changes, it will induce the EMF, and that induced EMF will cause a current, and that current will do what? That current will in turn try to generate a flux, which will in turn oppose the initial flux. It will oppose the initial flux. So basically, it will try to make the disc rotate in the opposite direction. So it opposes the initial flux. So braking torque is important to reach steady state, because I want my things to rotate at a constant speed. Okay, then only steady state will be reached. Then only I will be able to do measurements. I hope you understand this thing. Just like the in case of wattmeter. So obviously I can say that my induced EMF EM will be equals to minus d phi by dt. Okay, minus is just the saying that it is opposing the initial cause. So I can say my induced EMF will be equals to what? My induced EMF, as the disc is rotated, right, it has a speed, so it is actually proportional to the what? If it is proportional to the maximum value of the flux as well, proportional to the speed as well. The faster it will rotate, the more change there will be in flux, the more induced EMF there will be, the more opposition there will be. Okay, more braking torque there will be. Correct? So my induced EMF is basically proportional to the speed. That is a fundamental thing. Now I know what is my current due to this induced EMF. It will be EM by the Z, that is the impedance of that particular thing. Okay, and what is this? This is equals to simply EM is simply EM is proportional to, like, current is proportional to the, what I want to just say, that current is proportional to the speed basically. It is proportional to the speed, correct? And the impedance is constant. So my braking torque will actually be proportional to the speed. 0.1. Okay, it is proportional to the speed, because the faster it will rotate, the more flux it will cut, the more opposition that current will give, so that I have lesser change in flux. So my braking torque is proportional to the speed. Okay. Also, one more thing, my braking torque is inversely proportional to the distance. This R distance, right? This is the distance between the spindle and the magnet. The farther away I am from, the magnetic field will not reach the aluminum disc, will not cut the aluminum disc. So obviously, if I am not cutting the aluminum disc flux, there is no concept of changing flux, so there is no induced EMF. So the further in I am, the more flux there is, phi m increases. So if I am near, if R is low, my phi m will be high, right? The flux cutting will be very, very high. If phi m is high, obviously the torque, again braking torque, will be higher, right? This in turn increases the braking torque. That's why my braking torque is inversely proportional to the R. Why is this important? Because in early days, previously, what people used to do was, if you go, what they used to do was, they used to change this distance between the spindle and the brake magnet. So they used to take the magnet more closer towards the spindle. What that used to help them is, there is more braking torque, and if there is more braking torque, what would have happened? The disc would have revolved lesser amount of time. If the disc would have revolved lesser amount of time, then this, right, what actually this displays, like it's a proportional term, that it is proportional to the number of times the disk has rotated. So this will display lower value, and this actually tells that how much energy I have spent. So in turn, when the electrical guy comes and checks that, okay, you have spent this much amount of energy and you're built accordingly, so you're built lesser value. So that's why they try to cheat the electrical generator people who used to supply, electrical suppliers who used to supply electricity. But obviously, you can't cheat for too long. They, like the electricity guys, they got to know that they are cheating like this, so they changed the mechanism. Now we use a new mechanism, okay, that is advanced, that we don't study, that like obviously we can't study here, but the main core principle is this only. Then we change few mechanism. So that's then you later stage you would not be able to change the distance, okay, so you will not be able to cheat. So early days they used to cheat, and now if you try to cheat, obviously you can have legal consequences, okay. So yeah, that's just one fun fact I wanted to say. So this is the main important point is my braking torque is proportional to the speed. Okay, this is the important point. This distance will be constant, right? I cannot change the distance always, but braking torque is proportional to the speed. So like here I have written all those written things. You can read the textual change. That is not that important. Okay, here I have already written that at steady state disk will rotate at balance speed. Okay, so if this rotates at balance speed, my braking torque will be equals to the driving torque. What is my braking torque? Braking torque, let's assume it has like some k1 constant times speed, as it is proportional to speed, and my driving torque is some k2 times the current across the load, voltage across the load, VPC into ICC into sine of delta minus phi. Now if I integrate both sides with respect to dt, what will this give me? Integration of speed over time. It will give me number of revolutions, right? So that's why this integration gives me number of revolutions, and this in turn is energy. How much energy have I spent? Because if delta, let's say, was 90, it was Vi cos phi. So if I integrate Vi cos phi, that is basically integrating power over a time. That means I'm getting energy over the time. So this is the most important part that you need to remember. Okay, that your energy will be proportional to the number of revolutions. Okay, how is your braking torque related? How is your driving torque related? This page is the most important one. What up until now, whatever we have been discussing, this is the most important page. Okay, so try to remember this. This you have to remember. Now, like obviously these are proportional. There needs to be a proportionality constant, and that constant is known as energy meter constant. It is defined. There is a definition for energy meter constant, so you have to remember this. Energy meter constant is defined as the number of revolutions by energy. Okay, total energy spent over the period of time. So it is number of revolutions in time t divided by the energy consumed by the meter, or energy consumed by the load, not the meter. Sorry, why is everything cutting out? Okay, there is some weird thing. By the load. In time t. So energy consumed by the load in time t. Okay. So yeah, this is my energy meter constant. These few terms you should know. So now we'll obviously solve few questions. So first I will do what? I'll just show you the questions. Okay, one by one, and just you try to solve all this. You try to take a screenshot and solve all this. Then I will solve in front of you. Just simple formula you have to use, and you will see like the questions are cakewalk. Questions are not that difficult. Just the derivation type. I had to give you a bit of intuition. So just to give you a bit of intuition, I wanted to do all these things. This I will come to later on. So this few intuitions I wanted to give. Right now, I hope you have taken the screenshot. Now we'll solve the questions one by one, and you will see the questions are not that difficult. They are very, very simple. Okay, let's start with this question. An energy meter is calibrated to complete 100 revolutions of disk for every 1 unit of energy. So what is unit? Unit I have explained here. Unit is basically this, right? Kilowatt hour. 1 unit of energy means 1 kilowatt hour. So this also you should remember that 1 unit of energy is 1 kilowatt hour. Okay, so I can say that I have to rotate 100 revolutions for spending a 1 kilowatt hour of energy, and that is what is written over here, right? So it's like SI unit of energy is constant, energy meter constant is revolution per kilowatt hour. The number of revolutions that was done to spend, like to consume that amount of energy, and divided by the total energy consumed by the load in that particular time. The number of revolutions in time t and total energy consumed by the load in time t by that load. Okay, so this will be 100 revolutions of disk in 1 unit of energy. In like what do I say it? Like indirectly it is telling me that it is the energy constant. This is the K energy constant. Okay, and I know this relationship that K is equals to number of revolutions by energy. This you should know. Okay, determine the number of revolutions of the disk will make when connected to a load drawing 50 ampere 230 volt with a power factor of 0.6 for 1 hour. So how much energy do I spend in 1 hour? So energy consumed by the load will be what? E will be what? This will be VL, that is 230, into IL, that is 50, into cos 5. Now here I will assume they have not provided me delta, so my delta will be simply 90. So most cases delta will be 90. They will not, if they don't specify, you will assume 90 ideal case, and so it will become cos 5. So it will be cos of 5, which is 0.6, right? In our case power factor is given 0.6. And obviously integrated by time, as this is a constant load, right? This is just a DC load, this is not a AC load. So I can simply integrate it with respect to time. What will I get? This will be 230 50 into 0.6 into time. Time is 1 hour. So I will write 1 hour in 1 hour only. I will explain the reason just in a second. Because overall this unit is what? This is unit of power, right? This is watt. And I want to write the unit of time in hour. Why? Because energy we measure in kilowatt hour. And this is hour, right? So we'll write this in 1 hour. I will not change this into seconds. So you have to be careful. Just in like energy meter, just you have to take care of the units. That's the main concept. Anything else you can do. So 1 hour. Now I want to change this into kilowatts because my like this E is generally measured in kilowatt hour because energy constant is measured like that only. So I want to divide by 1000 as well. So overall this will become what? I will just quickly compute this thing. This will become 230 into 50 into 0.6 divided by 1000. So this will be 6.9, right? 6.9 kilowatt hour. Okay, this is the unit. Now what do I want? I want to find out the number of revolutions because they have asked me how many revolutions will the disk make. So again I will use the formula. K I know, K is 100. Okay, K is 100 and E is 6. N is the thing that I want to find out and E is 6.9. The number of revolutions N simply will be 690. Okay, this many revolutions the energy meter will make. So it was that simple. Questions from energy meter will be very simple except for few cases. You will see. Let's do another question. If the energy meter disk completes 30 revolutions in 200 seconds with a load of 850 watts, what is the meter constant? Meter constant generally in gate examination they will say you the unit as well. Don't worry about that. In kilowatt hour. Generally meter constant is measured in kilowatt hour. So it revolves 30 times. So number K is meter constant is what? Meter constant. Try to write down in your short notes. This formula you should know. Meter constant is number of revolutions N by energy, right? Okay. So this will be equals to number of revolutions is 30. Energy, how much energy? Like it is 850 watts connected and per second it is consuming 850 watts, right? Power is 850 watts and energy will be 850 times 200, right? But this is in, remember this is in kilowatt second. But actually I don't want in kilowatt second. I want in not in kilowatt, sorry. This is not even in kilowatt. This is in watt second. I want in kilowatt hour. That is a standard unit. So how will I convert? I will divide this 850 into 200. I have to divide by 1000 to make it kilo and I have to divide by 3600, that is 60 times 60. 60 will convert it into minutes and another 60 will convert it into hour. So this will be equals to how much? So 1000 into 60 divided by 850 divided by 200 and into 30. So the meter constant will come out to be 635. Okay, so it will come out to be 635. Just keep in mind that this is in, like, what is the unit? Unit is revolution per kilowatt hour. Okay, sorry, I mentioned the unit here wrong. It should be, okay, it should be revolution per kilowatt hour. This should be the unit actually properly. I mentioned it wrong. So these are simple questions come, right? So let's solve another question. The meter constant of a single phase 240 volt induction energy meter is 4400 revolutions per kilowatt hour. So K is equals to N by E, which is given 4400 revolutions per kilowatt hour. Okay. What is the speed of the meter disc for a current of 10 ampere with a power factor of 0.8 lagging? What is the speed of the meter disc? Okay, so they are asking me speed actually. So how do I find out speed? So actually they should have asked me revolutions. Okay, we can find the speed as well. I don't think like in the question it was supposed to be speed, but we can find out speed as well. Okay, so yeah, we can find out this as well. What will be the speed? So this is the meter constant. So just hold on. Okay, how to find out speed? Speed is revolution per unit time, correct? So I can write my K equals to N divided by power into time, correct? So this will be, this will make it speed. So overall I will get, this is speed divided by power, correct? And this is in kilowatt hour. So I generally speed is measured in terms of per second. Okay, so we'll convert everything into per second. So this will be, revolutions will be remaining as it is. Okay, or I can convert it everything in terms of hour only, per hour also I can say. So this will be 4400 and this is in kilowatt, right? I want to convert this. Okay, this is also, let's take this as kilowatt only. So this speed I want to calculate. Let's write this omega for now, speed of the disk, divided by the power. Power I will write in kilowatts so that this kilo and this kilowatts gets cancelled. So 10 into voltage. So voltage into current into cos phi gives me the power, right? But this is in watts. I want to write in kilowatts. So if I want to write in kilowatts, I have to divide by extra 1000, right? That will convert this into kilowatts, and overall my speed will come out in proper terms. So omega will be equals to what? It will go on that side. So now it will be simpler. 4.4 into 240 into 10 into 0.8. Okay, speed is quite high. That's like quite high. Okay, so this is 7872. And what is the unit? Unit is revolution per hour. Okay, this is the unit. Now if let's say you want to calculate revolutions per second, because this is very high number, it will revolve very high number of times, correct? But if let's say if you want to find out per second, so how many times it will revolve per second, what you have to do, you have to convert hour into seconds. So this will be 7872. Revolution will be remaining revolution, and if this hour needs to be converted into seconds, that means 60 will convert it to minutes. 60 minutes means 1 hour, and 60 again another multiplication of 60 will convert it into seconds. So to divide by 3600, so if I divide this by 3600, I will get my 2.18 value. Okay, so this will be 2.18 revolutions per second. So whichever unit they ask, just be careful about the units, and rest everything is sorted, right? You will be able to solve all these things, but rest everything is sorted. So have you understood how to find the speed as well? Okay, with the help of that meter constant formula. So we are using the formula in multiple ways. Now next question: an energy meter is calibrated to complete 250 revolutions per kilowatt hour. Determine the number of revolutions it will make when connected to a load drawing 30 ampere at 250 volt with power factor 0.8 for a duration of 85 minutes. Again the same concept, right? It has been calibrated to make 250 revolutions per kilowatt hour. So indirectly the question is giving you the meter constant, revolutions per kilowatt hour. It is 250 revolutions per kilowatt hour. Be careful with the units. Okay, this is equals to what? This is equals to my number of revolutions divided by the energy consumed, right? So I need to find out the number of revolutions, and energy consumed is how much? Voltage 250 into the current 30 into the power factor 0.8 into the duration. Now duration is given in minutes, but I have to write into time is the duration. I have to write in hours, so I will divide by 60. So this will give me in hours. So everything should be in proper format. This will be in kilowatt hour. This should also is in kilowatt hour, right? Everything should be in proper format. So 250 into 30 into 0.8 into 85 divided by 60 into 250. So my number of revolutions actually is coming out to be very high. Am I doing something weirdly wrong? That is what I'm trying to see. 250. Okay, I forgot to write this in kilowatt hour as well. This should be divided by 1000, right? Kilo, right? I forgot to do that. That's why the numbers were coming awfully high. 30 into 0.8 into 85 divide by 1000 divide by 60 and times 250 gives me 2125. So the disk will revolve a total of 2125 times this many revolutions once it consumes this much amount of power for 85 minutes. So just formula based questions. So for energy meter mainly they will ask for formula based question, nothing serious. Okay, so let's solve this question. So this question is a 220 volt 8 amp 50 hertz single phase energy meter has a meter constant of 115 revolutions per kilowatt hour. So again they are telling me the meter constant is 115 revolutions per kilowatt hour. This will be N by E. When connected to a 25 kilowatt unity power factor load, the meter takes 1 minute to complete 50 revolutions of the disk. So when it is connected to 25, okay, 25 kilowatt hour load, it takes 1 minute to complete 50 revolutions. So 50 by 25 kilowatt into 1 minute, 1 by 60. Is it giving me the same? Okay, it is not giving me the, okay, unity power factor is there. Fine. Just hold on. So meter constant this. What is the percentage? Okay. So my assumption was that my energy meter has meter constant this, but actually, okay, sorry, my pen got, okay, yeah, but actually what is happening is that when I'm actually using the energy meter in the load, I am observing that for this much amount of power consumed, right, and for this much amount of plate my disk is rotating 50. So this is my K ideal. Okay, I'll just write few things. K ideal that I actually knew is 115, okay, in revolution per kilowatt hour. Now what is the thing that I'm observing? I'm observing that my disk is revolving only 50 times while consuming 25 kilowatt into 1 minute of power, right? This is what it is consuming. So my N actual is how much? N actual is 50 revolutions. But ideally, how many times it should have revolved? Ideally, is my meter constant is 115. So I will do the computations. What will be N ideal? N ideal will be K times E, right? K is how much? K ideal is 115. And how much energy have I spent? 25 into 1 by 60. This is the 1 kilowatt hour. Or this much amount of energy in kilowatt hour, right? This is the unit. So I'll quickly do the computations. 115 into 25 divided by 60. So it gives me 47.916. Actually my disk should have rotated a bit lower, but you are telling me that my disk has rotated 50 revolutions. So how much, like, what will be the reading? Reading is proportional to the number of revolutions. If you remember, reading is proportional to number of revolutions, right? So obviously my percentage error will be N actual minus N ideal divided by N ideal into 100. So it will be 47.9167 minus 50 divided by 50 into 100. (47.9167 minus 50 divided by 50 into 100 percentage). So minus 50 into 100 percentage, or like into 2, basically into 2. So minus 4.167 percentage. This will be your answer, basically. Okay, so this is the amount of error that I will receive. Okay, so I hope you understand the error concept. So now obviously we'll come to the portion where I will understand why this error comes. So what are errors, basically? So first error what we will learn is phase error. So it's the same error that I have been talking up until now, is that for energy meter to provide accurate readings at all power factors, the field produced by the shunt magnet must lag the applied voltage by 90 degrees. However, due to winding resistance and iron losses, the flux generated by the shunt magnet does not naturally lag the applied voltage by exactly 90 degrees. It lags somewhat lesser. What is that? It is delta. So you remember, right? The term sin delta minus phi comes. Delta should have been 90. So sin 90 minus phi would have been cos phi, right? But it is not the case. So to compensate that, what do we do? To compensate, to correct this, the position of the shading band or shading ring or shading coil around the lower part of the control limb of the shunt magnet is adjusted, ensuring the flux lags the supply voltage by exactly 90 degrees. So like if you observe, if I have the picture, I will just copy and paste the picture here. So in the shunt magnet, right, there is a shading ring here. What it does, it actually generates an extra flux that helps in increasing the inductance of this particular coil, and that helps in making the delta angle more towards 90. So this is the shading ring that we provide. So this is just a theoretical point that you should know, is we provide a shading ring that is connected across the near to the end of the shunt magnet to increase the delta to 90 degrees. So this is one important point, theoretical point, that you should know, because for the students who are preparing for ESC, they may require this, because in ESC this MCQ type question can come. Okay, so that is the thing. Now like what is my measured value? Measured value is Vi sin delta minus phi into time. Obviously into time is there, and true value will be Vi cos phi. That is my true value of the load power consumed into time. So if I divide these two, obviously time will get cancelled. So the error will be independent of time. Okay, error will not be a function of time. Error will be simply this: sin delta minus phi minus cos phi divided by cos phi, or sin delta minus phi minus 1. Sin delta minus phi divided by cos phi minus 1. That will be my error, basically. Okay, this is one type of error, and in this, like from here only mathematical questions will come from gate. For the other types of error questions, like chances of asking questions is very rare, because those are theoretical concepts. Like speed error, sometimes the speed of the meter is either fast or slow, resulting in wrong recording of the energy consumption. So like your disk is rotating, right, and for some reason, due to some environment, due to the atmosphere, a heavy particle that falls on the aluminum disk. So obviously your disk is more heavier, so I will require more energy to rotate the disk, so the disk will rotate less for the same amount of energy consumed. So obviously there is error. How can I remove that error? Remove that particle, right? Or due to dust and friction, all those things can contribute to speed error. To compensate this, the speed of the meter when tested on non-inductive loads can be eliminated by correctly adjusting the position of the brake magnet. Movement of the brake magnet in the direction of the spindle will reduce the braking torque, and vice versa. So movement of the brake magnet in the direction of the spindle will reduce the braking torque. So here, right, what I can say is basically the movement of the brake magnet, like I will calibrate. I have to recalibrate my measuring instrument, and by recalibrating the measuring instrument with respect to the distance, because my braking torque was proportional to the R as well, distance as well, inversely proportional to distance as well. So obviously recalibrating it, I will get back I will basically get back my speed accordingly. So you have to recalibrate the instrument. Okay, this is a theoretical point that you should know, that how will you recalibrate. Previously what you used to get was, for consumption of 1 kilowatt hour, your disk was rotating 100 times, but actually now it is rotating 80 times. So it is rotating 20 times lower for consumption of a power of energy of 1 kilowatt hour. So obviously the braking torque is higher. So what I will do, I will move the disk further away from the spindle, so the braking torque is lower, so that it rotates more. So how much further, that you have to calculate and calibrate. So I hope you understood the example. Then like this is same frictional error due to friction in the bearings, in the all the components, right? Everything is rotating. It is rotating. There will be some friction. Due to those frictions, you can get some error. So for this also we do some compensations. Now these compensations are not that important gate point of view. For ESA point of view, these are important. These are theoretical points. You can study this. Okay, not that important for gate point of view. Next is creeping error. Creeping refers to the slow continuous rotation of the energy meter when only pressure coil is energized but no current flows through the current coil. This error may occur due to overcompensation of the friction, excessive voltage supply, or stray magnetic fields. So like what we do is to compensate this error, right? Friction is happening. So what I will do, I will reduce my braking torque. If I reduce my braking torque, the this aluminum disc will rotate more. Or what we do is we at the outer limb of the shunt magnet, this we apply a short circuit band. This band encloses the flux in the outer limb, inducing an EMF that actually tries that like we induce an EMF that actually is in the direction in the driving torque. So it actually helps the aluminum disc to rotate more. So we induce an extra EMF because friction is there. Friction will not help it rotate smoother. So I will to mitigate friction, I apply an extra driving torque that actually helps it rotating against the friction. But let's say friction was not there. If friction is not there, now I am giving it extra driving torque. Due to the extra driving torque, it will keep on rotating. So even if there is no current coil, right, like no current in the current coil, still the disc will keep on rotating. But it should not, right? It like energy consumption is zero. Because I is 0, so obviously energy consumption will be 0. But due to some stray magnetic fields, because some magnetic fields will be there, due to that interaction of that magnetic field and the magnetic field in the potential coil, the disc will rotate, and it will rotate very slowly, but still there will be some energy consumption. But actually in real life there is no energy consumption. So to prevent creeping under no load, 2 holes are drilled on opposite sides of the disc at same radius from the spindle. This distorts the magnetic field just enough to stop the continuous rotation of the disc. So we place 2 discs, and this what happens is like the magnetic field is not able to pass through this, right? This is hole, so air will provide more reluctance, so magnetic field will not easily pass. So magnetic field magnitude will reduce, hence the creeping, right? Creeping will reduce because it will rotate lower, because driving torque will reduce then. Okay, not that important for gate. Again, this is important mainly for ESC. Okay, another error is temperature error. If the temperature is like higher or lower, it changes the resistance of the disc, and if the resistance of the disc is changed, the current in the disc also changes, right? Because Z is like current is inversely proportional to the Z. So if that changes, again the driving torque will also change. Okay, like we to minimize this error we do something, but obviously we cannot minimize it totally. There will be some error. This error will be lower. Again, if the frequency is vary, right, the impedance of that disc also will change, right? Everything will change then there can be errors, because generally we calibrate the meter usually at 50 hertz, because that is how our like supply frequency is. So we calibrate according to 50 hertz. But for some reason, if let's say the frequency is 60 hertz, then the impedances will change, all the calibrations will change, right? So those things will change, then I will get an error. Okay, so that is the thing. And voltage error, voltage variations can also be there. If there's some, like we generally calibrate the machine for some rating, but let's say 220 volts, but I am giving it 100 volts, so it will not totally work to its 100% capability. So that is the thing. Okay, so yeah, now another concept that we use is phantom loading in energy meter. So what is phantom loading in energy meter? When testing on calibrating energy meters or wattmeters, what we do, actually applying the original load is very difficult. That's why the name phantom comes. We actually spook, or we somehow what do you say, like dhoka dena. We somehow spook the energy meter to think that we are actually loading the energy meter, but we are actually not loading it. Okay, we make it think that we are loading the energy meter, but we are not actually. How we do that? For instance, applying a 230 volt 100 ampere rated continuous load consumes 23 kilowatt. So per second I will burn 23 watts, right? 23 kilowatts. So this is huge amount of current, right? And but this is possible. Let's say like your house or 10 houses near here. 10 houses near here can consume total 100 amps of current at a particular second, and the voltage is 230 volts always, right? So it is possible. So how will I measure that energy? I don't want to measure that amount of energy, right? To calibrate my measuring instrument to that much amount of power, I will not burn 23 kilowatts. What I will do is I can do phantom loading. What does phantom loading means? Simply, I will connect a load which is not like 23 kilowatts, which is a simple low resistor, and through that, what I will try to flow a 100 amps of current. Okay, the load can be a 100 amps of current source. So load is 100 amps of current source, and the potential I have applied 230 volts. Due to that, I will see how many times my disk is rotating, and according to that, the power consumption I will see. So now what will be the power loss actually? Power loss won't be 230 into 100 amps. It will be not that. Why? Because this 230 is an independent source. It is an independent source. It is not the same source, and this is also independent. Okay, these are independent of each other. Independent. So even though it's I will write the spelling properly. So even though its current is 100 amp, but it is not to producing this much amount of current at 230 volts. Previously, this case was I was producing 100 amps of current at 230 volts, but now this is not producing it. Just to mimic this particular operating stage, because I want to calibrate my machine, what I will do is I will have a 100 amp of current source, but the voltage across it will be very low. V will be very low, and vice versa. Again, here this will be a 230 volt source, but the current flowing through will be very low again. Okay, I will be low. So total power consumed will be Vi here. It will be V into I here. Both will be very, very lower than this 23 kilowatts. So I will consume very, very lower amount of power. Right? So I just wanted to give you an example. So here these two are separate sources. So we connect both the pressure coil and current coil are connected to separate sources to simulate rated voltage and current without applying the full load. The power consumed in this method is primarily due to losses. Okay, so losses in this coil and the source. Okay, so what is the loss here? Generally voltage source doesn't have any, like the current will be very low, so it will have very low amount of loss, but current source can have some amount of loss. Let's calculate the loss here. So it's like flowing 50 amperes of current, right? It is flowing 50 amps of current, so the loss will be only in this resistor. So the P loss will be simply 50 square into 0.5. That will be my loss basically. 50 square into 0.5, which is 2500 divided by 0.5, which is 1250 watts, which is still a lot. But if you consider, right, what am I saving? So actual power which was supposed to happen is 230 into 50. So 5 into 23 is 115. This is 00. So it is 1.15 kilowatt. Okay, so it is huge. So it is huge amount of savings, right? Totally, like I am only consuming 10% of the power that was supposed to be consumed, but still I am able to calibrate my machine according to the same conditions. So that is the advantage of this particular thing. So now we will do few questions. Okay, so let's do this first question. Like few will be theoretical, few will be conceptual. In a single phase induction type energy meter, the lag adjustment is made to ensure that the current coil flux lags the applied voltage by 90 degrees. Okay, does the current coil flux lags the applied voltage by 90 degrees? No, current coil flux doesn't lag the applied voltage by 90 degrees. If you remember, current coil flux was in phase with the current ICC, correct? And ICC was 5 degree in lag with the VPC. Okay, so the angle between the flux in the current coil and the voltage is 5. That's it. The pressure coil flux lags the applied voltage by 90 degrees. Yeah, the lag adjustment is made to ensure that the pressure coil flux must lag the applied voltage by 90 degrees. That is my aim, right? That's why the current the current lags by 90 degrees because it is a purely inductive circuit. That is my main aim. So this option is correct, obviously, but still I will read the other options. The pressure coil flux is in phase with the applied voltage. No, I want the pressure coil flux to be 90 degree lag from the applied voltage. The current coil flux lags the pressure coil flux by 90 degrees. No, right? The current coil flux lags the applied lags the pressure coil flux by 90 degrees. Okay, pressure coil flux is somewhere here, but it doesn't lag it by 90 degrees, right? So like there is some other angle that is not 90. So this also is wrong. This anyways is wrong, but the main purpose of lag adjustment is to make the flux in the pressure coil to lag 90 degrees by the from the applied voltage. Yeah, actually one small mistake I made. So I wanted to correct it, because previously I mentioned that the breaking torque is inversely proportional to the distance between the spindle and the magnet. Actually I was wrong. It should be directly proportional. So I was wrong. Why I was wrong, I will explain. Because your breaking torque, right, it's proportional to phi into I, that is the force into the distance, because torque is force into perpendicular distance. So it is phi into I into R. Correct. So I was wrong there. I knew this, that we used to change the distance, but there the explanation was wrong. Okay. So what will happen is, if the magnet is more near, right, I will get more torque. Because as the magnet is more near, if the magnet is near, right, what will happen? The radius R will reduce. If the radius R reduces, I will get lower amount of torque, because the torque will be what? Torque will be moment, right? And the moment has changed. Force will be almost constant, because this phi m will be constant. Previously my explanation was wrong. I'm sorry. So phi m will be almost be constant. Phi m and I will be almost constant. But this torque reduces, because torque is about the spindle, because this R reduces. Okay. So I just told you the opposite previously. What the previous people used to do was, they used to move the magnet more closer to the brake. Okay, more closer to the spindle, so that the distance reduces, hence the breaking torque reduces. So here I was a bit wrong. Your breaking torque will be directly proportional to the distance between the spindle. It will not be inversely proportional. So I was wrong here. Okay, so this explanation was totally wrong. I'm sorry. So because this phi m will be almost constant, and the I will also be almost constant. Okay, so this torque will be dependent on the force into R, that is the torque. Okay, and if F is constant, so if I reduce R, the torque will reduce. Okay, so that was one explanation I just messed up there. Okay, so it should be that. So please remember, that is important for gate point of view, that your torque, you have to remember three things. Your breaking torque is proportional to the speed. Your breaking torque is proportional to the distance from the spindle. Also, what is your driving torque? Driving torque is proportional to VL IL sine delta minus phi. And another thing is that once you derive this equation, you will get back your energy consumed is directly proportional to number of revolutions. So that is what I wanted to clarify. So let's start the questions. I just got this question, right? This question, from reading this question only, I recalled that okay, I had explained there wrong. So the breaking torque generated by a permanent magnet in a single phase energy meter is directly proportional to the square of the permanent magnet's flux. Yes, it is phi m square. If you remember there, my E was what? E is proportional to phi m, correct? Is proportional to phi m. How is it proportional to phi m? Because if you remember, I can show here that my induced EMF will be what? Induced EMF will be minus d phi m by dt. Let's say your flux is some sinusoid, right? I'm just showing you examples. Flux is some sinusoid, not d phi, I'm sorry, d phi by dt. So if your flux is some sinusoid, right, sine omega t, something like that, then it comes out to be phi m will be constant, and it will be some cos omega t, and omega will also be there, and then your torque will be what? Breaking torque will be phi into I. I is proportional to E, so this is proportional to phi, so it becomes phi square. Okay, so just giving you an intuitive example, although this is not the correct way because this is a DC coil, but you should remember these things, that it will be proportional to phi m square. Okay, so it will be proportional to the square of the permanent magnet. It is proportional to the speed. Breaking torque, yes, of course it is proportional to the speed. That was my main purpose, to make it proportional to the speed. So it is proportional to the speed. The distance between the permanent magnet and the center of the rotating disc. The distance between the permanent magnet and the center of the rotating disc. So it is the R distance, right? So again, it is directly proportional. Yes, it is also correct. So all the above options are correct. All the three options will be correct here. Okay, let's move to the next question. Which instrument is designed to read only the average quantity? So these type of theoretical questions sometimes do come. Okay, And like previously I just wanted to say that in summary, my braking torque is proportional to phi m square is proportional to the speed. Okay, this is the speed, and is proportional to the distance, right? Distance from the spindle or R. Okay, this is the main summary that I wanted to talk about. Let's solve this question, which is designed to read only the average quantity. Induction type wattmeter, it is integrated time instrument. Does it read the average? No, it doesn't read the average, right? It is integrated time instrument. PMMC, moving iron instrument, rectifier type instrument. Rectifier type actually fully doesn't read the average, right? Because it only reads for one half cycle. Okay, for the positive half cycle, it reads 0 for the negative half cycle. PMMC is a DC. It is used for measuring DC. And what is DC? DC is the average quantity. So obviously these theoretical questions can come in GATE, very rare chance, but these type of question can come in GATE. And ESC, these type of question always do come. Okay, this type of question always come up. So we have this question. This question is pretty good. The voltage flux adjustment of a single phase 240 volt 240 volt induction watt hour meter is modified, resulting in a phase angle of 86 degrees. 86 degrees between the applied voltage and the corresponding flux instead of ideal 90 degrees. So obviously my delta is 86 degrees, right? It is not 90 totally. What errors are introduced in the meter's reading when the current is 5 ampere at a lagging power factor of 0.9? So what I should have measured, true value should be VI cos phi, right? VLIL cos phi, but measure value will be, time is same, it is VLIL. These measurements will be correct, but this will be sine delta minus phi. Okay, so so what is the error? Percentage error will be measured value. Like if I take everything in common, right? Like the error will come out to be sine delta minus phi divided by cos phi divided by cos phi into 100. This is the total error, right? So did I remember the formula? No. I just simply remember these two expressions. So these two expressions are actually pretty important. So my delta, like it will be sine of 86 and cos phi is lagging at 0.9, right? So what will be cos phi? Cos phi will be something 25 degrees. I will just quickly compute it. So 0.9 cos inverse 25.84. Okay, so it will be, so my phi will be 25.84 degrees. So it is 25.84 minus, this will be cos phi is 0.9 only, divided by 0.9 into 100%. Okay, so plus 86 sine minus 0.9 divided by 0.9 into 100. So this will be minus 3.62%. Okay, so your error will be minus 3.62%. Have they asked in what? If they ask in watts, right, how much error you will get in watts? Okay, so they can ask in percentage or in watts. They have not mentioned anything. So let's say in watts, because in GATE they can ask anything. So in watts I will say. If they ask in watts, what you will do? You can simply subtract this, right? Measured minus 2. That also you can do. So this is in percentage. In watts, error in watts, at absolute error, if they are asking, it will be measured value minus true value. So basically my V and L I will be common. So 240 into I is 5 into sine of 86 minus 25.84 minus cos phi basically. So cos phi is 0.9, right? So we'll do this. So what is my, again the same thing, 86 minus 25.84 into cos and minus 0.9. like this is actually a huge error. Why is there so much error? This should not be that much of error, right? Am I making some mistake? It is a delta minus 5 it is. So it should have come out to be cos 90. Cos 90 is 0.9. So 0.9 cos inverse 25 only. So 25. Yeah, 25 plus delta is 86. If I take the sine of this, okay, that's where I was going wrong. It is 0.86, right? I was taking the cos, that's why I was going wrong. Minus 0.9, so it comes out to be minus 0.032 into 5 into 240, obviously. So it will come out to be minus 39 watts. So this much amount of error there will be. Okay, minus 39 watts. So I will just quickly check whether this was also, everything was correct here or not. Quickly check that this is minus 0.32, right? 0.032 divided by 0.9 into 100. Yes, 3 point. Yeah, this is correct. So yeah, minus 39 watts will be basically my absolute error, and if they are asking in percentage, you will say in percentage. Next question: an energy meter is calibrated to achieve 100 revolutions of the disk per unit energy consumed. So obviously my K is 100 revolutions per kilowatt hour. Okay. When a load of 20 ampere at 240 volt and a power factor of 0.8 is connected, what is the percentage error if the meter registers 400 revolutions? So meter in actual is 400 revolutions, but how much what is the ideal revolutions? So ideal revolutions will be K times E, right? This will be N ideal. K is 100 and what is the energy consumed? 240 into 20 divided by 1000 to make it kilo. Obviously power factor is there 0.8, and to make it hour I have to multiply another 60 into 60 for how much period of time? For 1 hour. So they have already mentioned 1 hour. So if I multiply here, 1 hour means what? 3600 seconds. So if I just multiply 1 hour, the unit will be hour only. Okay, it will not change. Or what you can do, you can multiply into 1 hour means 3600 seconds, and multiply divided by 3600 seconds, and it will be 1 only. It will not change. Okay, so like you can do it both ways. Either way works. So here these two zeros will be gone, 1 0 will be gone. Okay, 240 into 2, that is 24 into 8. Okay, so it will be 192. This is too low. Okay, 192. Am I doing something wrong here? Okay, 240. Okay, 8 I did. Okay, not 240, sorry. Yeah, 192 into 2 also is there. So it will be 384. That's what I thought. So it will be 384 revolutions, correct? This is my N ideal, but it revolved higher. So breaking torque is for some reason lower. So what is my error? Error will be what are they asking? They are asking percentage error or something. Percentage error, right? So percentage error, N actual or N measured minus N true value divided by, or N ideal, I can say N ideal divided by N ideal into 100%. Okay, so this will be equals to minus 400 divided by 384 into 100. So it will come out to be minus 4.167%. Okay, this will be minus 4.167%. This will be the total percentage error for this particular case. Okay, so that's how you solve this question. Let's see another. The induction type energy meter can operate faster by what? Changing the load from leading to lagging. Load changing from leading to lagging, it won't change much. The power consumed will be changed, obviously. That is true, but it will not affect the braking torque. Okay, it will not affect the braking torque by changing the load to lagging to leading. So let's say, what does this mean? This means previously it was 0.8 lag, now it is 0.8 lead, right? Or other way around. Previously it was 0.8 lead, now it is 0.8 lag. Will it change anything? No, right? It will not change anything. Why? Because power is still same. Power is still same, right? Reactive power changes from positive to negative, but active power still remains same. It doesn't change. So same for this case as well. Same. Moving the braking magnet closer to the center of the disc, so my R reduces. So if my R reduces, my braking torque will reduce as it is directly proportional. So obviously my speed will increase now. Okay, so obviously option C is correct. Moving the braking torque further away, no, further away won't be correct. Option C will be correct. So I'm sorry for that particular misunderstanding of the concept. So I hope you understand this point. If my R will reduce, so speed will increase. So actually the point that I was trying to get to there was my R distance is inversely proportional to N. Okay, so if my R increases, speed will reduce. If my R reduces, speed will increase. Okay, so yeah, that is one thing that I wanted to talk about. Okay, so yeah, these are few theoretical concepts only. Okay, this is the same question only. Flux of the square of the meter, square root of the distance between the flux of the is proportional to what? It is not directly proportional to the flux square of the speed of the meter, square root of the distance. Okay, it is done actually. So here it is not directly proportional to the flux because it is proportional to flux square. It is not proportional to the square of the speed. It is proportional to directly proportional to the speed, and it is not proportional to square root of the permanent magnet. It is directly proportional to R. Okay, so obviously it is this question is irrelevant, but still if you want to understand, this question is important for ESC, not that important for GATE. Okay, so I hope you understand these theoretical points. Let's do another point, another question. I think this is the last question. A 240 volt 5 ampere DC energy meter is tested at its rated condition. The resistance of the pressure coil is 5000 ohms, while the current coil has a resistance of 0.1 ohms. What is the power consumed when testing the meter using phantom loading the current circuit excited by a 10 volt source? So I'm separately exciting the current circuit, okay, at this rated condition. So if I apply a 10 volt source, right, what will be my DC energy rated specifications? Okay, the current circuit is excited by 10 volt source. Okay, so my rated condition will be something like this, that this will be my rated condition, right? So this is, I'll share. I'll just write this circuit. Okay, my potential coil will have plus minus 240 volts, correct? So it is plus minus 240 volts, and it has a resistance R equals to 5000 ohms, right? So what will be the power consumed here? The power consumed here will be VPC whole square by 5000, VPC by R shunt. This will be the total power consumed. This is equals to 240 whole square divided by 5000. Okay, so this will be 240 whole square divided by 5000. Just hold on, 240 whole square divided by 5000, 52. Okay, so next is the power. This is the power consumed by the pressure coil. What about the current coil? Current coil circuit will be something like this, right? Current coil will have its turn. It will have its resistance. The resistance is 0.1 ohms, and the voltage is plus minus 10 volts. And this 10 volts is actually producing 5 amps of current. Okay, So you might ask, sir, how is this 10 volts producing 5 amps of current? Because the current what I can see here is 10 by 0.1. It is 100 amps of current. Okay. How are you saying, sir, it is 5 amps of current? How are you saying it? Actually, this source has internally its own resistance, right? I don't know that resistance. Okay, I don't know that resistance. This much I know, that this is being tested at rated condition, and somehow I have found a source which has some resistance, and then due to that resistance I will be equals to 5 ampere at the rated condition. You just hold on. Okay. Charge of this particular thing has been gone. Okay, sorry. Yeah, just 1 second. If somehow this works. Yeah, this pen is working. So it is 5 amperes, right? If 5 amperes is equals to what? 5 amperes is simply equals to my voltage divided by R plus 0.1. Okay. So R, from here I can directly say R will almost be equals to 2. Nearly equals to 2, right? So there is an internal resistance that is helping it to reduce the current. It is not that. So now what will be the power consumed? You can find it out two ways. Either directly do the voltage into current. So power consumed in this process, right, in the current coil will be voltage into current, that is 10 volt, that is a source 10 volts, and the current is rated current is 5 amperes. So it will be simply 50 watts. Now what is the other way also you can do. What you can do is power consumed will be simply I square into R. So I square, this is very small, but I can take this, but this is very small, so we can take this as well. It will be equals to almost 2 this I square is 5 square into 2, right? Overall resistance should be 2 almost, because then only the current, then only KVL will satisfy, then only the current will be 5 amperes. So I square into 2 will be simply 50 watts. So either way you get the same result. Okay, don't need to remember any formulae or something like that. Okay, so simple power thing we're doing, nothing out of the world or out of the blue we're doing here. Okay, we're doing the simple things only. So it is simply 50 watts, correct? So yeah, so overall what will be the power loss now? Overall the power loss, P total, right? P loss or power consumed to mimic this situation is simply 50 plus 11.52 watts. So it will be 61.52 watts. That's it. Okay, but if I just wanted to show you the difference between phantom loading and actual loading. If I was actually loading, the source would have been a single source, right? And that source would have provided me 250 volts and 5 amps of current. So it would have been 250, P actual. How much power would I had to consume to test the energy meter? It would have been 240 into 5, and whatever the time it is, just I'm measuring the power. So 5 is 1200 watts. Okay, so the power, actually how much power did I say? Except huge power, right? This is 61 watts and this is 1200 watts. So I'm consuming a very less amount of power to test the meter in the same condition. So I just have to have an extra source that can give me this voltage, right? So that is the thing that engineers use to test or calibrate the energy meter. They don't simply use that much amount of energy to test a, let's say 5 kilowatt hour energy meter. Okay, they will use the phantom loading situation. Okay, so that's it basically for this measuring instruments lecture of energy meters. In the next lecture we'll wrap up the measuring instruments chapter. Few basic measuring instruments are left, and that will be it. And measuring instrument has the has the highest weightage along with the bridges chapter. So these two chapters are very important. So practice as many questions as possible. I tried to bring here as many questions as possible, theoretical as well. Theoretical are for ESC, and the mathematical portion is for gate. Okay, so thank you for watching, and I will see you in the next lecture. Until then, happy learning. Hi everyone, and welcome back to PrepFusion. I am Anish, and today we'll start with the lecture 5 of this measuring instruments chapter. So today we'll learn about hot wire instruments, mainly which use the principle of thermal energy. So hot wire instruments will mainly use the principle of thermal energy. So we will not go too much into the theory. Mainly we understand what is the underlying equation that satisfies the control torque and the deflecting torque. Then we will understand about electrostatic voltmeter. As the name suggests, it follows the principle of electrostatics. Electrostatic energy. Then I will summarize the whole measuring instruments, which are the important points that you should know, and with the help of that single slide, you will be able to solve most questions of this chapter and the most important chapter of electronic and electrical measurements. Okay, and few miscellaneous topics that will be left, which are low priority, which are not that important. That's why I have put them in miscellaneous topics. So first of all, let us understand what is heating effect basically. So bit of theory: involves heating of a conductor due to current passing through it. Okay, this is known as the heating effect, causing it to expand. That results in deflection. So if I have a hot wire instruments, okay, so what it does, the current flows through a wire, and due to that flow, right, due to current flow, heat will be generated. What will be that heat? That heat will be simply I square RT. I square RT. And if you know a bit of mechanics, you know anything will have a expansion coefficient, right? And whenever the heat increases, it also the particular element or particular object also increases in size, so it expands, and as it expands, we use it somehow to convert it into deflection, and that deflection helps us in measuring the how much amount of current is flowing. So the current is actually proportional to the expansion. Now, is it linearly proportional? No, it is not linearly proportional, because here it is square. Okay, I hope you understand. There is a square here. Okay, so like this is what like our hot wire instruments do. So what is the working principle of a hot wire instrument? So working principle of a hot wire instrument is hot wire instruments are devices used for measuring current by utilizing heating effect. So they utilize the heating effect of current. So remember, my deflecting torque will always be proportional to I square. Okay, as it utilizes that heating effect, it will always be proportional to I square. The key components include a fine wire made of platinum indium alloy, which expands when heated due to current flow. As the current flows through the wire, it generates heat, causing the wire to expand and sag. So it will, like this wire, right? If we say this is the hot wire, okay, so it will expand. As it expands, what will happen? The spring, like there will be some like sag. There will be some sag in the wire. So what will happen? This point will go down. As this point goes down, this will deflect this rotation, and this rotation will be placed on the pointer. So pointer will rotate on the right. So that's the basic thing. So which is linked to the current value. So this will be proportional. So this deflection, right, will be proportional to my current square. And there will obviously be a control, which will be spring control. So theta will be proportional to I square. That is the only thing that you need to know. Now, what are the key features? The main feature is it has a slow response. Why? Because first of all, it is a mechanical system, right? It's a mechanical system. It's not a fully electrical system. Okay, so it will, like, once the current flows, the wire has to take some time for it to expand, then again retract. So that's why the response is very slow, because it is taking some time to expand, because it relies on heat buildup. So there will be some, like, will require some time for the heat to be built up. Controlling torque. A spring is used to provide the necessary controlling torque. So theta will be basically my deflecting torque is proportional to I square. My controlling torque TC will be proportional to theta. So my theta basically will be proportional to I square. That's the main important point. Air friction damping. We use air friction damping to prevent oscillation. So obviously we have to use some type of damping system. We use air friction damping here. Like eddy current damping can also be used, because this is not an electromagnetic system. So we can use eddy current damping. Don't worry, I will talk about this damping after finishing up until the summary. And don't worry, it is not that important. Damping portion is not that important. Gate point of view. For ESC, it is important because they can ask theoretical questions. Now, another few features, it can measure both AC and DC, as current is proportional to I square, right? So we have learned up until now, if current is proportional to I square, it can measure both AC and DC. Okay, so RMS and DC value, both it can measure. Frequency independent. The instrument is ideal for measuring high currents, and it reading is independent of frequency, making it suitable for both low and high frequency applications. Now here, as there is no electromagnetic effect, flux is not sinusoidal, right? So it is not depending on some current or like being sinusoidal or something. It is not depending on that. So that's why only heating. So heating doesn't need any sinusoid function, something like that. So it will be suitable for both high and low frequency applications. So bit of this things can be asked in ESC. So 4 measuring instruments will be given, and in the question they will ask, like, which instrument is more suitable for measuring current at high frequency. Okay, measuring AC current at high frequency. Then like let's say PMMC is there, MI is there, then this hot wire instrument is there, and dynamometer type ammeter is there. So you will choose this because this doesn't have any frequency dependency. All those things are actually flux dependent, magnetic field dependent, and magnetic field has some frequency component, right? So frequency dependency. So that's why we don't use. And PMMC anyways we used to measure for DC, not AC. Okay. So that was about for hot water instrument. Like that is it. Just a bit of theory. Next we have to learn about thermocouple instrument. What is a thermocouple instrument? A thermocouple consists of two different metals joined at a junction. When exposed to different temperature at hot and cold junctions, a DC voltage is generated due to Seebeck effect. The voltage produced is proportional to the temperature difference between the two junctions as described by the equation. So basically, if I have two junctions, right, two different materials and which are connected together, and there is a junction, what will happen? They will have some induced voltage if they have some temperature difference. So when exposed to different temperatures, they will generate a voltage. That effect is known as Seebeck effect. You can go and search. I don't have time to explain all this. Just basic things. Two different materials are there. If there is some temperature difference between those two materials and there is a junction, then a potential difference will be generated, and that potential difference will actually be proportional to the temperature difference between the two metal junctions. Okay. Now here, right, it is not exactly proportional. It will be K1 into T1 minus T2, then plus K2 into T1 minus T2 whole square, K3 into T1 minus T2, T3 whole square. So it will keep on increasing. But for all intrinsic purposes, I will assume it has a first order relationship, because I will assume T1 and T2, the difference is very, very less. As the difference is very, very less, this quiet term will also be not that high. Okay, so that is my assumption. So what we do is basically current flows, right? As current flows, different metals will react differently. So this will have some temperature, this will have some temperature, and the temperature difference between those two will ultimately develop voltage, and that voltage will be measured by some meter, like let's say PMMC meter. Okay, then it this temperature difference is actually proportional to the current that is flowing through both of the metals. And yeah, so my voltage that I measure will be proportional to the current basically. So that's how I measure the voltage. That's why voltage is written here. So that's how I measure the voltage. So remember here, generally we use for DC application. For AC application also it can be used. So DC voltage is generated at the cold junction, which is measured by a PMMC. Thermocouple instruments are used to measure both AC and DC. For AC they provide RMS value of current. So for AC it will provide simply RMS value of current, right? Because there is a square term here as well. Although this term will be 0 because DC term, average term will be 0, but as there is a square, so we will get AC as well. The test current is passed through a heater which produces heat to raise the temperature of hot junction of the thermocouple, generating necessary voltage. So like what we do is, there is the current is passed through a heater, and due to that heater, the heater is placed near the hot junction, which will make the temperature of the hot junction very high, and which will be proportional in turn to the I square, which will be proportional to the heating. And heating is proportional to I square. So that's why I square will be proportional to the voltage. So that's how I get the RMS value. So both AC and DC both can be measured. Theory is not that important, but the crux that I am explaining, that thing is important. This setup ensures that both AC and DC currents can be accurately measured using the thermocouple and PMMC combination. Okay. So I hope you understood this one. Now let's do a basic question on this. A thermocouple ammeter reaches full scale deflection at 50 amperes. So it's full scale. I is full scale, right? Is 50 amperes for a current of 20 amperes. So if the current is 20 amperes, what will be the new deflection as a fraction of the full scale deflection? So if the current is 20 amperes, what will be the new deflection as a fraction of full scale deflection? What will be the new deflection as a fraction of full scale deflection? So what do I know? I know my current, right? Like the deflection is proportional to heating, right? Deflection theta is proportional to T1 minus T2. I know my temperature or the heating is proportional to I square. So my theta in turn is proportional to I square, correct? So this is the main crux of thermocouple instrument that you should know, and for hot water instrument as well, that your deflection will be proportional to I square. So if my theta is theta full scale, then my current is 50. If my theta is theta theta, whatever they have told me, it is deflecting 20 ampere, then what will be my deflection basically? So it is giving 20 amperes, right? So basically this will be theta fs will be 5 by 2 whole square, so it will be 25 by 4. It will be 4 by 25 into the initial deflection. So what is asking, what will be the new deflection as a fraction of the full scale deflection? So my theta x by theta full scale, right, as a fraction of the full scale deflection, it will be equals to 4 by 25. So answer will be simply A. So these simple questions can come. I think generally they ask in ESE, they won't ask in like GATE, very rare chance, but still this can be asked. Now let's move on to other type of instrument known as electrostatic instrument. As the definition tells that it uses the electrostatic forces between two charged plates. It uses that principle to measure the voltage. Okay, so electrostatic voltmeters which measure voltage based on the attraction between the charged plates. So as there are like this A and B charge plate, both plates are charged. So there will be electric field, and due to the electric field, what will happen? There will be a force, and that force will basically attract. So one will be the movable plate, another one will be fixed plate. So this movable plate will be attracted, and which will be proportional to the voltage, right? So here a electric field will get generated. If you remember, if you have studied electrostatics from me, you know, right? Electric field will be generated, and that electric field will be proportional to voltage times the distance between this plates. Okay, voltage, and it is directly proportional to the distance, correct? And due to that, a force will be generated simply, correct? If you have studied capacitors, go and study capacitors if you are not understanding what I am saying here. So obviously, this electrostatic field brings a force. So there will be a force on this moving plate, and due to that there will be a controlling torque, controlling force, that is the spring will try to keep it in the same position, but this will move, and at steady state what will happen, the deflecting torque and the controlling torque will be same. What is the deflecting torque? It is F is equals to Q times E. E is V times D, so F will be equals to QVD. F will be equals to QVD. D is the total deflection. Okay, D is the deflection, right? And this deflection will actually tell me what is the voltage, because F is equals to what? F is equals to K into X, right? So this X, my deflection is proportional to this QVD. However, it has like extended. So I hope you understood this concept. So electrostatic voltmeters use this principle, and electrostatic voltmeter operates based on the principle of electric field. It measures voltage by force of attraction between the charge plates. As the voltage will increase, electrostatic force will increase. So this plate will move more on the left hand side. So will be the deflection. Deflection will be more. Okay. So the same thing is written here. So it is a linear motion. That linear motion is converted into a rotational motion, and after that we simply show on the pointer on the measuring instrument with the deflection. So controlling torque here will be again be a spring, through a spring. So if you remember, the energy of electrostatic voltmeter is du by U equals to half CV square, right? If there is some capacitance, like we can write it like this as well, or you can write it like that it is equals to half E epsilon whole half epsilon E square. Okay, that also you can write, or this is also possible, right? If there are two plates, the energy between those two plates is half CV square, if you remember. Now I know this, that my torque, right? Torque will be equals to how much? Torque will be equals to simply this du by d theta. Change in energy per unit theta. This is the fundamental definition of torque. Okay, I hope we know this. Now theta is what? Theta is the pointer deflection. Okay, theta is the pointer deflection, and like I hope you understand this one. Now we can simply do this dv by du by d theta. So obviously, what I know, my voltage will be constant, right? That the thing that I will measure, that will be constant. But what will happen? Voltage is the applied voltage, but this capacitance will change, right? Why will this capacitance change? Because the distance between the plates are changing. There are two metal plates. So where did it go? Where did the picture go? There are two metal plates, and the distance between them are changing. As the distance is changing, the capacitance will change. So I'll just take this picture. Voltage is the measuring thing, right? That I want to measure. So that won't, like, that will be V only. It doesn't depend on theta. But the deflection actually depends on theta. As this distance, right? Distance reduces. Okay. So what will happen? My capacitance will reduce. Right? Capacitance is a function of theta, because capacitance is equals to epsilon A by D, and D itself is a function of theta. Okay, that is my assumption. So obviously it will change. So it will have a term dc by d theta. So that's why my deflecting torque is not directly proportional to only voltage square, but it has a capacitance component as well. And at steady state, what will happen? At steady state, my TC will be equals to TD. So my theta will be proportional to V square. So only this much you have to remember. Okay, this much stuff. This is the most important stuff. And another stuff is that my capacitance is function of theta. These two things you need to remember. Okay, so that is like only thing. And from here I can say my theta, right? Theta, like exactly if I want to write my theta, theta will be 1 by 2 k V square dc by d theta. So my scale, even though if I assume that my dc by d theta is like constant, my scale won't be linear. So that is one disadvantage with electrostatic voltmeter, like any square law voltmeter, any square law instrument, that my scale will not be linear. Assuming my dc by d theta is constant, okay, this is my theta, but scale is not linear, right? Scale is non-linear. So in the like gate exam they won't ask, but in ES examination they can definitely ask. What they can ask? They can ask that like there are 4 instruments: PMMC, MI, electrodynamometer type wattmeter, not wattmeter, sorry, electrodynamometer type ammeter, and let's say this electrostatic voltmeter, right? And they will ask which instrument has linear scale. You will say it has PMMC, because PMMC the theta and current were directly proportional, but here it is square, it follows square law, so it is non-linear, right? So which term makes it non-linear? So basically what do I need to do to make it linear? Okay, to make it constant. So basically one thing I have to do is my dc by d theta or my capacitance C should be a linear function of theta. If C is linear function of theta, then dc by d theta will be constant, then it is not ISO. Okay, so my capacitance has to be a linear function of theta, then only my dc by d theta will be constant, and then only I will get at least it proportional to square law. It will follow square law, else it will follow some other non-linear relationship that I don't know. Okay, so this needs to be constant. So now obviously we'll solve few questions on electrostatic voltmeter, few simple questions. Okay, an electrostatic voltmeter has a full scale of 1500 volts. So VFS is 1500 volts. Okay, and is controlled by spring with a constant K. So spring constant is K micronewton per micronewton meter per radian. Okay, at full scale deflection the needle subtends at an angle of 75 degrees. So theta SC is 75 degrees. The capacitance at 0 voltage is 12 picofarad. So C is 12 picofarad, and at full scale deflection it is 30 picofarad. So this is C full scale is 30 picofarad. Initially C initial at 0 deflection is 12 picofarad. What is the like at 0 voltage, this is C initial, right? C0, C naught. What is the value of the spring constant K? So okay, so one assumption I have to make is that my assumption is it is linearly varying. That is my assumption. Thing is linearly varying. So if it is linearly varying, what will be my ds upon the dc upon d theta? So what is the value of the spring constant Kc? The needle substance at full scale, needle substance at 50. So what can I say is that if I am reading full scale, right? If it is giving full scale reading, what will be the equation? So K into theta full scale should be equals to half V full scale whole square dc by d theta. So from here I can identify the K. But what is dc by d theta? How do I identify dc by d theta? So I know C is equals to some m into theta plus C naught, because at theta equal to 0 I will have some C naught, right? That C naught is equal to 12. This is not that important, but this is important, right? So what will be this? So from 0 to full scale, my capacitance is changing 30 picofarad. So how will I do this? So I can use the simple y1 minus y2, that formula. So my M will be equals to C full scale. If I am starting from 0, C0 divided by theta full scale minus theta 0. So obviously C full scale is how much? C full scale is 30 picofarad and C0 is 12. So 30 minus 12 divided by theta full scale is 75 minus 0. So this will be 18 divided by 75. Okay, this will be my dc by d theta, because here dc by d theta is simply 18 divided by 75. Now do remember, this 18 is in picofarad. Okay, don't forget, this 18 is in picofarad and this is in degrees. But is it in, what have they asked? They have asked in micronewton per radian, right? So I have to be careful. So I want to convert this into radians. So how do I convert this into, because okay, anyways, this theta will be here still. Okay, how much deflection is there? This will be theta square actually. Okay, yeah, 10 per radian, because this will give me per theta will get cancelled. Micronewton meter. Okay, so you can find out the units, but what I am interested in, I will convert everything into radians, right? I will write everything into radians. So this converted into radians will be 75 into pi divided by 180. That's the radian thing. Okay, and I want to convert this into micro so that it will be easier for me. So this will be converted into micro. So this will be 10 minus cube whole square, 10 raised to the power minus 6 micro, right? If I want to convert this into micro, this will be 18 into 10 raised to the power minus 6 microfarad. Okay, so my theta fs, like, actually the units, I think here something is wrong. This should be radian square, I think. Yeah, this should be radian square, or does it need to be radian square? Because this, whatever unit I get, this should be in torque, right? This torque, then yeah, it should be by theta. This unit is correct only. This unit is correct because this is the unit of torque. Okay, so what will be my K basically? So K will be VFS whole square. What is VFS? It is 1500. So 1500 whole square into divided by 2 into dc by d theta. So the dc by d theta is this 18 by 75 into pi by 180. So 180 will be here, and obviously I have multiplied a minus 6 to make it micro, correct? That is there. This is my dc by d theta, and that's it. That's the only equation, right? So now I simply have to solve this. And obviously don't forget, there was a theta as well, right? In the bottom there was a theta. So this will be theta full scale, right? Theta full scale is this only. This is theta full scale. Theta full scale will anyways get cancelled, as theta full scale is the bottom. No, it will not get cancelled. This will be 75 into pi into 180. So this will be twice. So I will just calculate this value. Okay, so this will be 180 divided by 75 divided by pi whole square. So this will be 0.5836 into 18 into 1500 whole square divided by 2. Okay, and of course the 10 raised to the power minus 6 is obviously there, right? 10 raised to the power minus 6 is obviously there. So this will be 11.82. If I just write this directly, you can solve this. This will be 11.82 micronewton meter per radian. Now whenever you get confused, right, what type of unit conversion you need to do, whenever you get the answer weird, like you are getting some huge value, 11 raised to power 10 raised to power 6, 11 into 10 raised to power 6, or very small value 0.00001, then that means somewhere you have messed up with the units. So you have to be careful with the units, that you are converting everything perfectly. In the question they have asked me in micronewton per meter radian, so I will convert everything into radian and I will convert the pico into micro. That's the only conversion that I will do. I hope you understand the question. I hope you are able to solve this question. Okay, so torque is Newton meter. Yeah, so yeah, that's it basically for this question. Let's solve the next question. A current of this value is passed through the circuit shown in the figure below. Calculate the reading of the electrostatic voltmeter across a 5 millihenry inductor. Okay, the inductor is 5 million. Okay, this is not a 5 millihenry, this is a 1 million inductor. Yeah, sorry for the interruption, I had just had a typo in this. It should be 5 millihenry. So basically current is passed through a electrostatic voltmeter, and calculate the reading of the electrostatic voltmeter across a 5 millihenry inductor. So what will be the reading across this 5 millihenry inductor if the frequency is this? So what does my electrostatic voltmeter measure? It measures basically the RMS. So first of all, I have to write down the expression for voltage across the 5 millihenry inductor. If the current is this, right? Current, this is the current flowing. So what will be the voltage across the inductor? We know this relationship, that VL is equals to L DIL by dt. So L is 5 millihenry and DIL by dt. So I will differentiate this thing. So this will become, differentiation of sine is cos 0.2 into omega into cos of omega t, and differentiation of sine is again cos. So this will be 0.1 into 2 omega into cos of omega t. Okay, and remember this is in 10 raised to minus 3, and this omega is 10 raised to power 6. So overall I will have a 10 raised to power 3 at the outside, correct? Okay, 10 raised to power 3 at the outside. So overall what will this become? My voltage across the inductor will be simply a minus sign will be outside. 5 will get multiplied here. So if 5 gets multiplied, this will be 1 only. So this will become minus cos of omega t, and this will again, if 5 will get multiplied, this will be 10 into this. This also is the same thing only, right? This also is the same thing only. Yeah, so this also will be plus cos of omega t, okay, into 1000, correct? There are 2 cos of omega t into 1000. So remember, this is not simple cos of omega t. I cannot simply add here. There is the frequencies are different, right? This is cos of 2 omega t. Okay, remember. So how will, this is not 10 cube, how will you write down the RMS value of this? So if you remember, for multi-tone signals, right, I have to individually write the RMS, then square each of them. So what will it become? So this will 10 cube will be outside. This will be 1 square plus 1 square, then whole under root. What is the, sorry, not 1 square, sorry. What is the RMS of this? It is 1 by root 2. So I have to take the square of the RMS. So 1 by root 2 whole square. So 1 by root 2 whole square, 1 by root 2 whole square. If I take the whole square of this, if I take the whole under root of this, I will get back my RMS. So RMS will be simply what? It will be 1 by 2 whole square, 1 by 2 whole square. This is the RMS, this is RMS whole square 1, and if I take the under root of that, it will be totally 1000. So my electrostatic voltmeter will simply measure 1000 volts, right? It will simply measure 1000 volts because this is my VL RMS, and my electrostatic voltmeter measures RMS. So this will be my answer. Okay, it's that simple. Like here, right, these type of questions can come in easy. Which of the following instrument is least affected by frequency of AC supply? Moving iron, no, it has frequency dependency. Hot wire, let's see. Induction, it goes on the effect of induction. Inductance is there, so inductance will change. And electrostatic also, there is a frequency dependent, right? Capacitance is there. So if capacitance is there, capacitance will change with respect to frequency. So here C is there, here L is there, and here also L is there, right? Only hot wire doesn't have any frequency dependence. So it is totally like independent of frequency. These type of question can come in AC. Okay. So now let's come to a very short topic about range extension of electrostatic voltmeter. So how do I extend the range of electrostatic voltmeter? To increase the measurement range, a series capacitance is used, effectively multiplying the voltage range by a factor depending on the added capacitance. The new range can be, I will compute that new range. Okay, so basically my measurement electrostatic instrument can be considered as a capacitance, right? It has some capacitance, so it can be considered as a capacitance Cm. So what is my Vm basically? My Vm, if I want to measure, like Vm is the maximum value that the Cm, like the voltage that can be applied across the Cm, right? That is the breakdown voltage. If you have studied the concept of breakdown voltage from me, you will understand exactly what I am talking about. So it will be equals to what? It will be simply voltage division in capacitance, and voltage division in capacitance is just the similar as current division in resistance. So here at the top it will be C series divided by Cm plus C series. Okay, I hope you understand all this. I will not go through this basic network. In networks we have done this, so I will not go through this here. Okay, so basically I can say my Vm by V, or my V by Vm, which is the multiplying factor. No need to remember this. You can remember this, that's good, but no need to remember M, like this is by how much I'm magnifying the range, will be equals to 1 plus Cm by CAC. Okay, it will be equals to Cm by CAC. So definitely this is the relationship, that this much you should know. Okay, this is the old range and this one V is the new range, and this V new range will be this much. So if I want some range, let's say my initial range is 200 volts, and if I want 1000 volts as my range, so it will be 5. So Cm by CAC will be 4. So my series capacitance has to be 1 by 4th of the meter capacitance. So I have to add a series capacitance which is 1 by 4th of the meter capacitance, and obviously it can sustain that much amount of voltage. So you have to take care of that as well, that its breakdown voltage is not exceeding than whatever this voltage, right? So it's what should be the V breakdown, minimum V breakdown of SC, it should be V minus Vm. Okay, so this should be the minimum breakdown voltage of VLSI, right? I cannot exceed this value, so just have to be careful. So let's do a basic question on this. An electrostatic voltmeter with a meter capacitance of 2 microfarad. So it has a meter capacitance of 2 microfarad. Okay, can measure voltages up to 1 kilovolt. So voltages up to 1 kilovolt. Okay, so it's full scale voltage, right? Vm is 1 kilovolt equals to 1000 volt. Okay, so calculate the required series multiplying capacitance needed to extend the measurement range up to 200 kilovolts. So calculate the required series multiplier capacitance needed to extend the range up to 200 kilovolts, right? So my required range is 200 kilovolts. So obviously I can directly use the formula, or you can draw the circuit as well. This will be my series capacitance. This is my, no need to remember any formula, right? We can directly do this. The potential here I know. What is the potential here? Maximum potential, that is 1 kV. But potential here needs to be 200 kV. Huge, right? Huge. Not here, sorry. The potential totally, sorry, this not this. The potential here must be 200 kV. So simply I can apply the voltage division again. So 1 kV will be equals to 200 kV into CSC by CSC plus Cm. So from here I can directly say what will be my if I take this, that it will be 1 plus Cm by CSC. Cm by CSC is equals to 199. So this will be equals to, Cm will be equals to CSC will be equals to 199 divided by CSC. So it will be 199 less than CSC. So it will be very, very low. We will quickly calculate that. So if I just quickly calculate this thing, it will be 2 divided by 199, and if I multiply 1000, it will be 10 nanofarad. Okay, so I need a capacitance of 10 nanofarad, but do remember it has to have a breakdown voltage of how much? 199 kilovolts as well, and getting that type of capacitor is very, very difficult. Okay, the capacitance value is low, but the breakdown voltage is really high. So these type of things we can do mainly theoretically, but in actual life implementing these kind of things is really, really difficult. Okay, so now let's move to the next, that is the Hall effect. So Hall effect is involved in deflecting force. This is not that important. Okay, not that important gate point of view. I can say you can ignore this, but you should know what is Hall effect basically. Deflection is based on the Hall effect, which occurs when a magnetic field is applied in a current carrying conductor, produces a voltage perpendicular to the current. So in Hall effect, what happens is when a current carrying conductor is placed in a magnetic field, it will produce a voltage perpendicular to the direction. So current is going like this, and a magnetic field is also there, right? So what it will do, it will produce a potential here. So once it produces a potential, that potential is directly proportional to the current. So that's how we measure the current. Okay, so this is the basic Hall effect that you should know. Just this much amount of summary. For ESC, this is important. If you want to know more, please go through the AK Sahani book. There they've explained more, so you can go through there. Not that important for gate. Now we'll come to controlling force, because the only type of controlling force that we have learned is only the spring control. But there is another type of controlling force as well, which is gravity control, which sometimes we use, but mostly we will use spring control only. But gravity control, what is gravity control? That you should know. Okay, because a mathematical question can come from this. So what is gravity control? A balanced weight is used to ensure the system remains a state. So what happens when your spindle tries to rotate, right? When your spindle tries to rotate, what will happen? This point will try to go leftwards, right? This point will try to go leftwards. As it rotates, this point will try to go leftwards. As it goes leftward, I have a balanced weight which will oppose the rotation. This balanced weight will oppose the rotation, and in turn I have a control weight which actually controls the rotation. So I will write down the forces, then you will understand. So what will happen? Your pointer is here, right? So your pointer is here. Your pointer is, let's say, has from this position has rotated theta degrees. So it has rotated theta degrees. Okay. It has rotated theta degrees. So if this has rotated, right, this whole thing is a single piece. So this will also rotate. It has a control weight here. This whole thing is a single piece only. This will also rotate like this. Okay, theta degrees. This whole thing is single piece. Okay. Now, if this mass rotates here, right, this was the balance position. If this mass rotates here, this is the mass, right? Now mass is here, and I know there is always a mg acting downwards, gravitational force acting downwards, right? That has been provided by earth, that earth is providing me. Okay, so mg is there, and I know this mg can be broken down into two components. What are those two components? Because this angle also will be theta, correct? So one of the components will be this, that is mg cos theta, which will not be of much use to me, but other component will be this, right? That will be mg sin theta. Okay, and I can see directly my pointer is here and my mg sin theta is here, right? So what it will try to do, mg sin theta will try to get it back to this place, correct? But pointer is rotating in this place, so it will try to go more on the right hand side. So pointer is telling this block to go on the left hand side, but mg sin theta, the weight of its own block, it's telling it to go no. You cannot go on the left. You have to stay at this rest position. So at somewhere at steady state, this two forces will be equal. So basically, my deflecting torque will be equals to mg sin theta. Like this is the controlling torque, right? At steady state, deflecting torque should be equals to controlling torque. So deflecting torque TD will be equals to mg sin theta force into the perpendicular length. What is the perpendicular length? It is simply this, right? L. Perpendicular length is L. So mg into L sin theta. So this will be basically my deflecting torque equation. Okay, steady state equation. So this you should know. Now I will just copy this thing. Okay. Now if you see, like there are a few drawbacks. That's why we mainly don't use this. What are the drawbacks? First drawback is my scale is non-linear, because it is not directly proportional to theta. It is proportional to the sine of theta, correct? It is proportional to the sine of theta. So I get a non-linear relationship between the theta and the torque, right? So it is not a proportional. So that is the one issue. Next is it may not be ideal for precise measurement. The meter must be positioned vertically for effective gravity control, as the control mechanism depends on the weight's orientation relative to gravity. So it has to be placed vertically, because the weight the vertical mg has to act downward, right? Then only this will work. So this instrument needs to be placed in a particular manner, then only I will get a proper measurement. So there are a few drawbacks. That's why we generally don't use this kind of controlling torque. We generally use spin control. So, but question can come, numerical question can come. So we should learn this. So let's do a question on this. So we have a question. A 15-gram weight is used to control the weight in an upright gravity control zero center deflection. Zero center deflection means when my pointer is at center, right? That means it is zero center. So it can go left and right. It can be negative and positive. Both is possible. With an input signal, the observed deflecting torque is 4 millinewton 4 Newton meter into 10 raised to power minus 3. If the control weight is position 32 meter mm from the spindle and the acceleration due to gravity is 10 Newton per kg, what will be the deflection in degrees? So they have told me that acceleration due to gravity is 10 Newton per kg. Acceleration due to gravity is 10 Newton per kg. So why are they giving me A? Like it is 9.8 meter per second. Newton is mass into gravity, right? Mg is equals to force. Weight is mg basically. So 10 Newton per, like, okay, 32 mm from the, so what they have given me A, right? A is 10 Newton per, because mass into acceleration is so G, they have given me G is meter per second square, 10 meter per second square, and L they have given me 32 mm. So this will because 10 raised to power minus 3. Okay, next what you can do is what else they have given me? They have given me deflecting torque is this, and weight also they have given me, right? 15 gram. So weight also they have given me is 15 gram, or weight, or this is actually the mass of the object. So mass is, weight actually is given in newtons only, 15 gram. If I want to convert this into SI units, it will be 10 raised to power minus 3, 15 to 10 raised to power minus 3 kgs. So all this information is there. What will be the deflection? So basically I will equate. So I know my at steady state TC will be equals to TD. So what is my TC? TC is mgl sine theta equals to, and they have given me TD is 4 into 10 raised to power minus 3 Newton per meter. Everything is in SI units. So I will write everything in SI units. So this will be M is 15 into 10 raised to power minus 3 into 10. Okay. And into L. L is how much? L is 32 into 10 raised to power minus 3 sine of theta equals to 4 to 10 raised to power minus 3. This. So this and this will be cancelled, and this 4, this theta will be cancelled. So this actually becomes 8. It becomes this gets cancelled, and I'm just checking what things are getting cancelled here. Is there anything else that are getting cancelled? Okay, nothing else is getting cancelled, so everything is here. Anything am I missing here? 10 per kg milli. Okay, does your deflection? Okay, so I think this should be actually okay, 15 into 10 into 10 cube, and into 8 is also there, right? Yeah, okay, yeah, this is correct only. So this will be 15 into 10 into 8 and into 1000, and if I do sine inverse of this, I will get 56.44 degrees. So my theta will come out to be 56.44 degrees. Generally, like we tell answer in radians. So if I convert this into radians, it will be or 0.985 radians. Okay, so this will be the answer basically. So that is the case, right? Now let's solve this question. Match the following. So permanent magnet moving coil it will be a DC only instrument, right? So it will be DC only. So option like for this one will be match. So match the following. This came in 2015. Right now I don't think they will give this, but still this is a good practice, right? Moving iron currented through current transformer. So if moving iron is currented through current transformer, it can measure only AC. Why it can measure only AC? Because current transformer is there. Current transformer can only measure AC, right? It cannot measure DC. So it can only measure AC. So as transformers there, AC only. Rectifier instruments, obviously it will measure only both AC and DC, right? Rectifier instruments can measure both AC and DC, because if I even pass AC, it will give me some average value, right? It will give me some average value. Current will not flow in the negative direction, because rectifier instrument helps for the PMMC current to flow in the negative direction. So rectifier can measure both AC, but what is the accuracy of that measurement? I don't know, but it can at least measure. From that relationship between theta AC and theta DC, I can find out the theta AC value, correct? Now electrodynamometer type instrument, it can measure both AC and DC. So this also will be 3. So correct answer will be option C. Option C will be correct here. Okay, so yeah, that's about it. 1, 2 or just be careful about this, because you can think rectifier can only measure DC. No, right? I can give AC signal and it will only show me the first half cycle. Okay, only the positive half cycle. Negative half cycle it won't show, but it will give me some measurement, right? It's not like I cannot give a AC signal in a rectifying instrument. I can give the AC signal, right? I can give it. Okay, it will not damage the instrument. So this is the most important page that I wanted to emphasize on. Okay, that you should remember. Okay, about the torque equation of each of the instruments. What applications are they used? So PMMC, the deflecting torque equation is BINA. B-I-N-A. B is the magnetic flux density, which is fixed because I have a permanent magnet. It is not depending on the current. I is the current flowing through the coil. N is the number of turns of the coil. A is the cross sectional area that the particular coil is covering. Okay, Kc and theta. For all of this we use control torque. We don't use gravity control. Okay, we don't use gravity control. MA instrument, again remember the torque equation was half I square dl d theta. For electrodynamometer type, it will be just dm d theta, and there won't be any half here. Why there won't be any half? Because I have 2 coils now. Instead of single coil, I have 2 coils. Okay. Yeah, sorry for the interruption. So as I was saying here, so this will be I square dm by d theta, and your controlling torque will be Kc into theta, and it is used for measurement of both DC and DC. So this page is the most important one. This page you can put in on your short notes so that you don't forget which instrument is used for what. Okay, you can also include the thermocouple instrument, hot couple instrument as well. Hot couple instrument is also important. Okay, so after this we will study about few miscellaneous topic which is not that important for gate point of view. So first one is air friction damping. So basically what we do is we provide some damping, right? So eddy current damping, like I haven't taught you damping yet. So what is damping used for? Damping is used like whenever this pointer will move and reach steady state. Assume it's reached steady state here. What will happen is it is a second order system. So there will be some oscillations because the control torque will say no, I want you to go back. The deflecting torque will say no, I want you to go right. So before reaching total steady state, total still, it will just oscillate near a steady state point, right? Just like a second order system. Just like a second order system. If you remember the response, unit step response of a second order system for a underdamped second order system is something like this, right? So basically I want to damp out this oscillation. So I have very high oscillations around the steady state point. I want to damp this out. I want to reach to my steady state much faster. Basically I want to have a critical damp system where it doesn't oscillate, it directly reaches to the steady state point. Okay. So now like what does air friction damping does? When the pointer moves to the right, the vane shifts to the left. So pointer is moving to the right, the vane okay, sorry, it moves to the right. Yeah, this is the air chamber and this is the vane, right? So if it moves to the right, the vane shifts to the left. Okay, this movement causes an increase in the volume of the gas. Basically what it does is it actually moves here, and if it moves here, there is a huge number of gas here. Okay, the gas increases. So as the gas increases, the air will provide a drag. Basically the air will provide a drag because air itself has a drag force. So it will provide a drag force which will damp out this movement. The more it moves, the more force air will give, right? More it oscillates, the more force air will give to oppose these oscillations. So that's how I basically oppose the oscillations, and that is what my air friction damping is. So bit of theoretical points are here. You can read this and you can understand what is air friction damping, or you can go through the book as well. Next about damping is fluid. So if I place this particular object in a fluid, right, then I try to if you move any object in fluid, it will be difficult than to move it in air. If you observe, don't put your phone, put anything else. Let's say this no, I have everything electrical. So let's say this cellotape, right? If I'm moving here like this, if you do the same experiment in water, if you move, you will see you are facing more difficulties to move it like this. So the oscillations will be lower because it will need more force to oscillate it. So that's what we do. Basically, we place the pointer, one end of the pointer in fluid, and that's how it reduces the damping. But that's how it reduces the oscillations. But obviously that type of arrangement is very difficult, because if I try to move my instrument, right, there will be some fluid inside the instrument, that fluid can come out. Okay, so all those things are very difficult. So we generally tend to avoid fluid friction damping. Either we follow air friction damping, or we use electromagnetic or eddy current damping. So what does eddy current damping means? So it just uses the Lenz's law. So we know whenever a current is flowing on a magnetic field, okay, so EMF will be induced, and EMF will be induced as such to oppose its initial cause. So as my pointer is moving more, so it is cutting more flux. The flux is changing very fast, but due to the change in flux, EMF will be induced, and that EMF will actually oppose the initial change, that is cutting very fast. As it was cutting very fast, eddy current will say, what are you doing, man? I don't want this change. Please slow it down. Please slow the damping down. So it will slow the damping down, and hence slow the oscillations down, and hence there will be more damping and oscillations will be away. So we generally use this eddy current damping wherever there is no inductive effect. Wherever there is no effect of induction or magnetic effect, there we will use this eddy current damping. Else we will not be able to use, because already we are using the induction principle to get deflecting torque. We cannot use this again. Okay, so just be careful about that. Okay, so yeah. What are the components of eddy current damping? What are the components used? All those things you can read. I don't want to bore you here. I don't have enough time to explain all these things. Okay, so now let's understand another type of instrument, that is power factor meter. So what does a power factor meter do? Is basically it has like two coils, same as electrodynamometer to wattmeter, but it carries actually the same amount of current. Whatever the load current is, that is what it carries, right? And what we do is we have this first coil, which will be a purely resistive coil, and the second coil will be purely inductive coil. So the currents will totally, the angle between this coil and this coil will be totally lagged by 90 degrees. So they will have an angle of 90 degrees. Okay, so that is the concept that we will use here. So let's say the inductance of the first coil will be M max cos theta, then the inductance of the second coil will be M max sin theta, because the angle between them will be simply 90 degrees. So theta is the what is the angle between them, right? Angle between the plane of reference. That is what my theta is. Okay, because this inductance will have two components, one will be along the plane, one will be opposite the plane, right, perpendicular to the plane. So I will have two components, and this is how my inductance will be. So if you want to go too much in depth of the theory, so you have to go through the book. I don't want to go into the book right now. That is not that important, and this is anyways not that important. Just few basic things you should know. So yeah, so that's it about. So a current coil will be connected in series, so which will carry the load current as well, and voltage coil will be connected in series again, but this time the current will be quadrature. It will be quadrature of the this particular current coil. Okay, so if I find out the derivative of the mutual inductance, it will be M minus M max sin theta, and this will be M max cos theta. So just the differentiation of these two. Okay, so if you know one thing, if I have a voltage here and current is here, right, this is the load current and this is the load voltage. Now I know I have a coil which is carrying IA, which has some IA current. Okay, and the other coil will carry current IB, which will be quadrature to the initial current, right? It will be totally 90 degrees. So this angle is phi. So what is the torque in a dynamometer type wattmeter? So there are two types of torques acting here. So this is again the current into the, it is proportional to the voltage as well. This current is proportional to the voltage into cos of phi. This angle between the voltage and current, this ICC, angle between this ICC and the voltage, into dm by d theta. So there are two types of coil here, right? There are two interactions here. So let's say there are two dynamometers. Okay, one is carrying the voltage and another one is carrying the load current IL. Okay, So the angle between them is cos phi. Then I have another dynamometer or wattmeter which is totally 90 degree apart from this voltage. Totally 90 degree apart from this voltage, and it is carrying current of IB, and the angle between this IB and IL, because it is also carrying current IL, will be 90 minus phi. This, as this is 90, this will be 90 minus phi. So this will be cos of m max into sin theta. This will be cos of 90 minus phi into cos theta. Okay, and at steady state, what will happen? These two torques are actually opposing each other. At steady state, my TA will be equals to TB. So I can say my TA will be, what is my TA? TA is simply cos 90 cos this. So steady state, this, right, cos phi minus sin theta will be equals to plus sin phi cos theta will be 0, right? These two talk will cancel each other out. So I can observe that basically if I break this down, right, if I break this down, the angle will come out to be, the condition will come out to be it will be sin theta minus phi equal to 0. So theta is the deflection, right? Theta is the amount of deflection. So theta, I can say at steady state, like this has to be 0. So theta has to be equals to phi. From here I can say the theta has to be equals to phi, and theta is directly proportional to the angle. So then I have to take the cos. So that would be another task, right? So the angle moved by the pointer corresponds to the actual phase of the between the current and voltage, but the scale is calibrated in terms of power factor, that is cosine of that angle. So we calibrate the scale, okay, and then we get basically the answer. So this here, right, air friction damping is used. And don't worry, this is not that important. Just understand the basic principle, like how I derive the torque equation. That much is important. Everything else is irrelevant. And most cases they will not ask this in the examination. In gate exam, this will not be asked. Okay, just this torque equation you should know. Okay, that your deflection is directly proportional to the phi. That much you should know. Let's understand another type of meter, which is Megger. Okay, so similar to power factor meter, a Megger also contains two moving coils which are 90 degrees to each other. Both coils carry current and are subjected to magnetic field of a permanent magnet. This time it is subject to a magnetic field of a permanent magnet. This moving coils experience force and torque, and when torque produced by two coils balance each other, the point comes to steady state. So what will happen? Again, there will be some, due to this magnetic field, right, there will be some torque, and due to that torque it will deflect, and there will be some controlling torque that will control the steady state. Okay, so what we do is basically this indicates that the system achieves a stable position when the torques from the two coils cancel each other out, just like the previous power factor meter, allowing the Megger to provide an accurate measurement. Can measure from very low to very high resistance, that is insulation resistance. So it can, like, that's why the name Megger, because we can measure here very high resistance, not just any resistance. And here also air friction damping is used. Okay, so like, although the torque equation is not that important, I will write down the derivation later on, and you can go through that, because in this case, right, the torque equation is bit typical and will not be most probably asked. So the torque equation is not that important for this Megger thing. So I'll just, one thing you should know, the angle of deflection, this much you should remember for this, because it's better to remember. Angle of deflection of the pointer will be inversely proportional to the meter resistance. This much you should know. This you can put in your short notes, that angle of deflection will be inversely proportional to the meter resistance. So what happens is, the Megger, right, if the angle of deflection is 0, that means I have infinite resistance. So that's why at 0 deflection it will show infinite resistance. At almost full scale deflection it will show 0 resistance. So this term you should know, that theta equals to 0, it will show infinite resistance, and theta equals to 90, or theta equals to 90, or full scale, theta equals to theta full scale, right? It almost shows 0 ohms. Okay, so this is the only point that I wanted to explain, because everything else is not that important. Okay, because they will not ask working principle and it's not that important. So that's it basically for the measuring instruments portion. I hope you enjoyed this lecture, this chapter, and just practice questions, just practice the torque equations. Only mathematical portion is important, theoretical not that important. You can understand the theory later on as well. So from the next lecture onwards, we'll study about bridges, both AC and DC bridges. So thank you for watching, happy learning, and I will see you in the next lecture.